like the one that Victor is probably going to show us very soon, cannot be achieved quantum mechanically without having entanglement everywhere.
We have a paper.
But this is quantum arguments, very device-dependent arguments.
It's quantum, yes.
Maybe it's then the end.
Can I?
Calculation was that.
Maybe it's better to move this to the questions or the after.
One notion of genuine non-locality is the so-called full network non-locality, where you require really that all the links, all the states and the measurements are really somehow entangled. Yeah. But okay. Anyway, so here this is more like an intuitive notion, right? I'm not going in deep into that. So anyway, yes.
So what is wrong with the RGB to the fourth?
So it's nothing is wrong. It's a beautiful example.
In what sense is it not nice?
So one aspect which is not so nice is that it's not really experiment friendly at the moment, right?
Right.
So this is one aspect. The proof, I mean, what I'm going to describe now is also not experiment friendly, so I'm not claiming to do better than that. But just, yeah. Also, I mean, if we are to understand this type of network well, we should know more than 2 examples somehow, right? Or, I mean, yeah, have somehow, systematic techniques as well, right? So, yeah. And somehow having more examples requires to develop new techniques. So, yeah. So now, the winner of the game, the elegant jot measurement. So this is a 2-qubit measurement that was introduced by Nicolas Gitton in 2017. So when I say the elegant jot measurement, actually I will refer to a distribution that you can realize in a triangle network using that measurement, right? So the way you realize that distribution in the triangle is by having each source distributes 2 qubits in a singlet state. And then each party, Alice, Bob, and Charlie, they implement this elegant jot measurement, which corresponds to measuring the 2 qubits in highly symmetric, partially entangled basis. Yes, which I don't describe here because it was given to you on Monday on Nicolas' slide, and you all remember, obviously, what it was. What matters for us is the resulting distribution, which I call PEJM. So this is a distribution with 4 outcomes per party because each party measures 2 qubits in the basis. And that distribution is very symmetric. It's characterized by only 3 numbers, or 2 with normalization. So you have the probability that the 3 parties get the same outcome, and the probability that the 3 parties get different outcomes, right? So yeah, can we prove that this distribution is non-local, right? So this is sort of the first step. There is the intuition that this distribution is not only non-local, but somehow also genuinely non-local according to different notions of genuine, right? This will not be covered today, but yeah. Also, there is some evidence that this distribution is presumably not only non-local, but non-local even under some reasonable experimental noise. Yes. So this makes it an interesting example. Yes. So that was the presentation of the problem. Now we go into the techniques that we use. And the technique is inflation. So luckily, Otfried introduced the technique a bit before. So let me just sketch what the technique gives you first, and then I describe briefly what the technique, what it is. So here again, I have my local set, which is inflation gives you a way to characterize a superset of the local set. So in blue, I have the inflation compatible distribution. And the point is that if you can show that the distribution is not in the blue set, then it's also not in the green set, right? So it gives you a way to prove non-locality, right? So inflation comes in different forms for different types of networks. If you have a classical network, then inflation gives you a linear program. If you have a quantum network like those that Otfried was describing, then you get semi-definite programs. And if you have a non-signaling network, you get, again, linear programs. So the way inflation works, more or less, is, so it's kind of a trade-off, right? The idea is to go to a larger scenario than the scenario, which sounds a bit complicated, but in the larger scenario, we want to have simpler constraints than this complicated non-convex, yeah. Sorry?
What is opt?
Sorry, optimization type, sorry.
Oh.
So more precisely, I meant what type of optimization problem do you get by using inflation in the different types of networks? Sorry, yeah. Yes. So yeah, we go to a larger scenario with simpler constraints. How does that work? Let's do the simplest example I could think of in detail. which is this network. So admittedly, it's fairly simple. So here we have two copies of Alice, Alice 1, Alice 2, and they share a lambda, so a classical variable. Right? The idea is that we want to characterize the distributions P of A1, A2 that can be written as the average of the product of marginals, where these two response functions are really the same. Right? Suppose we want to characterize that. So for this slide only, the local set is the set of these P. Okay, just to explain how this works. So how do we do that? Well, let's use the technique of inflation. So we go to a larger network, a larger graph, which is this one where we just have 3 Alices instead of 2. And now let's think about, knowing that P can be achieved in that network, what do we know about this network, right? Well, we know that we can find a distribution Q, an inflation distribution Q, over the outcomes of the 3 Alices, such that this Q satisfies some relaxed constraints, right? So we just impose that Q is symmetric under the exchange of the 3 outcomes, right? Which from the graph is kind of intuitive. And we also impose that the distribution Q, when you trace out or marginalize the third Alice, well, you should get the same as the distribution P, right? And this again from the graph is kind of clear. Like if you remove A3, then you get the same graph, right? So how do we prove this statement that if P can be achieved like that, there exists this Q? Well, we can just define the Q as this average of the response functions for 3 Alices this time. And this will have the desired symmetry properties and the desired marginal property. So what really matters for us is that if there does not exist such a distribution Q, then the distribution P cannot be realized like that, right? Which means it's non-local. It's like the fake local set. Right. Is this clear so far? So this was for this very simple artificial network. Let me tell you briefly how this would work for the triangle network. So here we have again the triangle network. And let me just draw the graph. Okay, there it is. So this graph consists of 2 copies of the source, right? And then if you think about Alice, Alice is a party that receives the beta and the gamma. So there are 4 ways to plug in an Alice into this network, right? So we have 4 Alices, 4 Bobs, 4 Charlies. And remember that we want to characterize the local set, so the set of classically compatible distributions. So whatever relaxation technique we use, it better capture something about classical sources, right? And here I claim that it's apparent that it does. Why? Because here the beta source, for instance, was sending out 2 values, right? 1 to Charlie, 1 to Alice. Here the beta source is sending values to 4 parties. And what we mean by that is that the output of the beta source is being copied and sent out to 4 different parties. This would not make sense in quantum mechanics because of no cloning. So here it's sort of clear that we are doing something classical, which is good because we want to characterize the classical set. Right, so just briefly, what are the properties of this graph? For the marginal constraint, we can see that if we trace out the off-diagonal parties, we just get 2 independent copies of the triangle. This will give us a marginal constraint. And for symmetry, again, just looking at the graph, there's a symmetry corresponding to exchanging these 2 rows of parties, a symmetry corresponding to exchanging these 2 columns, and also this symmetry here. This is a so-called 2-to-2 inflation graph because we've copied twice the alpha source, twice the beta source, twice the gamma source. We can go to larger graph in this notation. For instance, we can consider the 2-to-3 inflation graph where we have 3 copies of the gamma source, right? And we can go larger. So now, the first time I learned a bit about this technique, I thought this is bad, this will never be useful. Why? Because you are only imposing these very relaxed constraints, right, on the Q here, right? This is just like a bit of symmetry, a few marginals. How can this be, how can this really capture the essence of this difficult non-convex problem, right? But then I was made aware of some work on, let me just skip that for now, on the convergence of inflation. So this is some work that was done by Miguel, who is there, and Eli. And this really blew my mind because it was a very surprising result. And essentially the question is, what happens when we look at larger and larger inflation graphs, when we add more parties? So if we let n be the number of parties in the inflation graph, maybe this is the set of compatible distributions with an inflation of 10 parties. Then if you go to 20 parties, maybe this will be the outer approximation, right? So when you increase this n, you get a tighter and tighter approximation. And in fact, in the limit, the outer approximation converges to the local set. And this is really surprising because it looks like a really weak relaxation, but it does converge. And importantly for this project on the non-locality of the elegant jot measurement, what it means is that if the distribution is non-local, then there exists an inflation that will detect the non-locality. It's only a matter of looking at a large enough inflation. So, okay, it sounds like we can do it, right? Except that now comes the problem, how do we actually solve large inflation problems? So yeah, how do we solve inflation problems? We have to turn to a computer-assisted proof. That's kind of, the only way to do it. Normally, the way you do this is by formulating the inflation problem as a linear program, and you just feed that linear program to a commercial solver, and the commercial solver gives you, an answer which is either like compatible or incompatible. And if it's incompatible, you know the distribution is non-local. But the problem is that if you think about it, just to store a distribution on n parties that each have 4 outcomes, you have 4 to the n events, right? So you have 4 to the n probabilities to store in memory. And this is just to store a potential inflation distribution. Then you have to solve all these constraints on that distribution, right? So yeah, it's pretty bad, right? And this is probably why existing codes that were appealing to commercial solvers were stuck to the 2-to-2 inflation graph, which is unfortunately inconclusive for the elegant jot measurement. So we have to go to bigger graphs. But how do we do that, right? And this is the technical slide. It fits on one slide, so okay. It's not too big. So the first step is to turn the inflation problem, so this compatibility, find a distribution Q on the graph such that blah, blah, blah. We need to formulate that into something that we can visualize to have any chance to understand a bit how to solve it. And it turns out that you can recast the problem into a polytope membership problem, which is a problem where you are given this red point, and you're given a bunch of blue points, and you have to check whether the red point is inside the convex hull, so the polytope formed by the blue points. Right? So here it's clear. I hope that the red point is outside, right? Why is it so clear? Because it's 3 dimensions and points also, right? In practice, we have to do this type of problem with like lots of dimensions and lots of points. So it's a bit harder. And just for the correspondence, the way it works, if we can certify that the point is outside, that means we can certify the inflation problem has no solution, which in turn certifies that the distribution is non-local, right? So really what we want to certify is that the point is outside. So to tackle that problem, the first step is to use the symmetries of the problem, so both the symmetries of the distribution and of the inflation graph, to reduce the number of dimensions. So here I went from 3 dimensions and 8 blue points to 2 dimensions and 4 points, and in a way where you don't lose generality, right? Like the problems should really be mathematically equivalent. It turns out you can do that. So just to give you some numbers, the problem we had to solve in the end had 10 to the 6 dimensions and 10 to the 12 points, which is large. After symmetrization, this goes down to 10 to the 4 dimensions and 10 to the 8 points, which is a massive improvement. So yeah, we might as well do it. But it's still too large. This, you can still not feed that to a commercial linear program solver. It's still, in particular in terms of the memory. The memory will just run out. So then the next step is to solve this without directly calling a solver, right? And to do that, we can use the Frank-Wolf algorithm to find a separating hyperplane. So separating hyperplane is just, okay, it's a line, right? That just on one side of the hyperplane you have the red point, and on the other hand, on the other side of the hyperplane you have the blue points. If you can find such a hyperplane, then clearly the point is outside, right? And the Frank-Wolf algorithm lets you do that by sort of clever iterating and finding the relevant blue points iteratively, and eventually you sort of converge to a facet of the polytope that's pretty close to the red point, and that lets you find the hyperplane somehow. And importantly, we can do all of that using exact arithmetic, which is kind of nice. So the reason why this is true is that all the points that we care about, they are given to us in the problem as vectors with rational entries, right? There's no square root of 2 going around, and so we can compute everything using exact arithmetic. So there's no floating point error. And this was quite important to us because, I mean, if the red point is very close to the polytope, right? We still want to find a separating hyperplane without floating point errors affecting the result, right? I mean, so this is nice. Okay, so now the results are more, actually, it's more, because in the end the result is like a yes/no answer, right? So it's more the timeline of the result to make it interesting. So it was known that the 2-to-2 inflation thing was inconclusive. So then in February of last year, the coding adventure started. C++, which is a great language that I recommend to everyone because it's really nice. And then in August 2022, we were able to consider the 2-to-3 inflation, which was bigger than what people could do before, so we were so happy, except that it's actually inconclusive. And this test took already 1 day. And back then it felt like going to a larger inflation would take months, right? Without any guarantee that it would work. Yeah, so I wrote this email to Nicola and Renato saying that I had sad news for the EJM and that I was a bit demotivated, it would probably not work. But then I remember I'm a PhD student, it's my job to struggle with code, right? And I still had a couple ideas, right? So, okay. So I went to implement further optimization of the code. Most importantly, a branch and bound multi-threaded iteration over the blue vertices that you saw before. That was really a key. And with that, finally, in December, we could say that the distribution was non-local. And so we had a better email to send around. Yes. So let me conclude briefly. So this is still not an experiment-friendly proof of non-locality. So this still lacks. But in principle, with more computational resources, we could probably do it. So this is one possible direction.
What you call really experimentally friendly doesn't mean it's experimentally feasible or easy, but just that it has some noise robustness.
Yeah, I guess you can divide it in different ways. One, I mean, ideally, what you would want is that you can take the statistics from the experiment, and somehow have a tool that tells you, yeah, it's non-local, right? Yeah. So this we don't really have. It would be interesting to use this sort of techniques to look for quantum advantages. So, like, yeah, example of quantum locality in more general networks and causal structures. This seems interesting as well. And also, we have some tools to characterize quantum networks, but they could also benefit from further development. So it would be interesting to look at quantum networks and hybrid networks as well, where you have some quantum links and some classical links, and try to implement similar techniques than those presented here. And yeah, special thanks to Elisa, Sebastian, Nicola, Tamas, Alex, Renato, Marco, Destiny, Eli, and others for this project, and thank you for your attention.
So, since you asked the question already once, maybe you'll start with Bori and then come to Marco. Plenty of time, please.
Me? So I'm very unfamiliar with the entire topic, but it looks like very painful to do this inflation technique because resources blow up. But
That's true.
there must be some other way. After all, is this set that you want to characterize this L set? It should be a compact set, isn't it? Or
It is compact.
it is compact. Is it like some manifold with boundary or something like this? Is there some way to do some nonlinear inequalities or something like that? My question is why the entire focus is on this. Is it the entire focus on inflation techniques? Is there some other trickery to do this stuff?
That's a very good question.
I mean, there must be like some room to do some other trickery.
Absolutely, and we are counting on you to find it.
Thanks, bro.
Many other things we tried and failed.
Really? Okay, so
Information threading methods and so on.
okay.
Let's say there are lots of methods, but I would say the inflation is the best. I mean, okay, it's subjective because I've been using it a lot, but it's the best for the following reason. It's the only technique that gives you a systematic way, like basically a converging outer approximation scheme. This is the only scheme that we know. For instance, there are these entropic methods that also give you outer approximation of the set you want to characterize, but there's no knob that you can crank up and get a tight thing, right? So of course, in practice, because you can never like go to infinite inflations, this is kind of more like a motivating thing, right? But yeah, I would say it's maybe one of the best methods for that reason. But there are lots of different methods which are sometimes useful and sometimes better.
Well, let's say, I mean, with this tempo, you will never characterize this set in the simplest possible case, right? This is the, so I mean, so it took you a couple of years to get one point. Is it outside or inside, right? So this is a, Do I understand correctly?
Probably the second level detects lots of points. It's just that it didn't detect that particular point. That point must be very close to the local set, I guess.
Yeah, that's correct. So there are ways to, so here the test I was describing was really a feasibility test where you test for one distribution, is it feasible or not? So of course you can sample the space around the local set to have this sort of, you can have this grid thing, but there are also techniques that are slightly less, how can I say, accurate, like slightly less close to the local set that gives you actually inequalities. So the analog of Bell inequalities in the triangle or in more general causal structures are polynomial inequalities in the probability. And this you can get using inflation as well. And in principle, with infinite computational resources, you can get all the inequalities that characterize the local set as a manifold. I mean, the boundary is a manifold, I guess. Yeah.
But it's extremely difficult problem.
I hope. I mean, if someone tells me it's easy, I would be sad because.
Maybe as difficult as inequality were when CHSH wrote the inequality. You know, Pareto existed, but we didn't know the connection to it. So initially, when you 40, 50 years ago, when you had a new Bell inequality, you could publish a PRL. Today, you can produce billions of Bell inequalities. But at that time, finding one and you write a PRL with it.
Is this the status now?
Yeah,
Good to know this.
This expression, right? Experimentalists, like yesterday's Nature paper is tomorrow's calibration, right? I guess it's kind of this version of this. Marco Tullio?
Thank you for the talk, very nice. So from the technique you used, I think you also have some robustness, right? So it's not only in-out from this polytope method, like you can also say that it's like you can add some noise, no? You have some more information, not only this net outside, right?
Yes.
Can you say a bit more? So you didn't like white noise robustness, or do you have some numbers?
The only I have some numbers, but it's not very.
Yes, like
I have this number here. So here we have a model where there's a visibility, and the JN is at 75%. And it's a family of distributions such that the transition from local to non-local is 1. You have the critical visibility. Inflation gives you upper bound on the critical visibility. And the best upper bound we were able to find is slightly below the JM. So we have like, okay, so this is not directly, this is sort of physical noise, but it's more or less like physical noise. So you get, if you think of white and robustness, you probably have like, maybe, you get a finite number. It's not very large, right? But of course, if you were to go to higher inflation with more computational resources, you would get down to the true. There's a true bound somewhere, right? We don't know that. But yeah. Yes?
So you told us about the local, which is better called classical,
Yes.
and the quantum regions. How about a non-singling counterpart?
Yeah, that's a very good question. This has been extensively studied as well.
So one slide about it being optimization linear, but other than that, you didn't say anything, I think, about it.
Yeah, I didn't say much about that. So you can define an NS set.
it's on your graph. It's 100% here. But then you can do with no signal with NSI correlations or something.
Yes, 100% you can do it. So you can define it. The way you define it is again using inflation typically, and there have been, I mean, Nicolas Antoine as well, and I mean, probably others have worked on that. And you can also characterize a non-signaling set, and yeah, you can do it. And
you have people, I mean, points in the non-signaling, which is not in the quantum.
Yes, do you? Yeah, I guess, yeah.
Very nice.
Thank you.
Okay, well, I guess if there are no more questions, let's
How many flights?
Er hat das anders dargestellt.
Tu parli romano adesso?
So the recording okay?
It's going. Fantastic.
We went again to the bar until 5 o'clock this morning.
Everything was closed. We went around in the frozen Les Diablerets.
Well, closed. We didn't wait for you.
Not yesterday. To have a deal. We had a poker deal.
Play soccer?
Let's get started. So hi everyone. It's my pleasure to introduce Flaminia Giacomini for this first of the one session. So Flaminia, please.
Thank you very much for the introduction, for the nice invitation to this conference that is, I'm enjoying really very much. So this talk will be about the following question. Let us imagine we have a quantum system and we prepare this quantum system in a quantum superposition of positions. And this quantum system is massive enough that it is a source of gravity. Then the question is, what can we learn from this situation on the nature of gravity? So I was thinking for some time how to do this talk and what exactly to tell you. And in the end, I decided to give you a message that is not strictly contained in one paper, but that rather links a different set of papers on which I've been working on in the past few years. So my goal is not really to explain to you technically a single result, but more to let you understand what the context is and what the bigger picture of this work is. So let me start very basic. So we have our two pillars of modern physics that are quantum theory and general relativity. And they famously deal with different phenomena. So quantum theory deals with entanglement and superposition, while general relativity with the relations of gravity and matter. And very famously, these two theories are also radically different in their foundational aspects. And now the effort to try to put them together usually goes under the name of quantum gravity. But here we have immediately the first bad news, which is that we have no experimental evidence that we should give up a classical theory of gravity, because all current observations are compatible with quantum theory and general relativity taken separately. So this doesn't look very promising, and typical quantum gravity research has looked for quantum gravity effects at the Planck scale, which is extremely far from experimental observations. So to give you an idea, if we consider LHC as our best microscope, this gets to 10 to the minus 21 meters. So we still have many orders of magnitude to go. But this is not the only way to look for quantum effects in gravity. There is another way that has nothing to do with the Planck scale, and this will be the topic of this talk today. So we will be in the low energy regime, where gravity is weak, and we can meaningfully talk about quantum particles. And this regime is interesting to me, at least, because there are some conceptual questions that are shared with quantum gravity, but we can identify concrete physical situations. So let us start from Einstein's equations, the fundamental equations of GR. They connect gravity on the left-hand side to matter on the right-hand side. But it is important to stress that the matter context, the stress-energy tensor, is classical in general relativity. But now, if we look at quantum theory tells us that matter is quantum. So it would be tempting to take this object and plug it here. But we immediately see that these equations are inconsistent if we do that. So now, how do we solve this? So there is no single way of solving this problem. What most approaches that want to quantize gravity do is to say, well, this should be a quantum object, and this part should also be quantum. But this is not the only possibility, logically. There is also the possibility that actually the left-hand side stays classical, and that we have to modify quantum theory in order to account for classical, for a classical metric. Or there is also the possibility that we're totally off track and that this is totally something else. So the reason why this question has been revived recently is that experiments have made huge progress, and now they are planning to test this effect in the next decade. So you've heard Marcus's talk already, and he talked about the experimental counterpart to that, so I will not focus on this. But basically, you can see the experimental effort as experiments in gravity with no quantum, where the goal is to measure the gravitational field associated to lighter and lighter objects. And on the other hand, quantum experiments with no gravity, where the goal is to test quantum properties at more and more macroscopic scales. And in the end, you want to bridge these two regimes and test the gravitational field associated to a quantum source. And now the question is, what will this tell us? So this is not a new question. This has been around at least since 1957, where there was this Chapel Hill conference that gathered all the major experts in gravity at the time. And there were many discussions, and at some point, Richard Feynman proposed a thought experiment, where he claimed that it seems to me that we are in trouble if we believe in quantum theory, but we do not quantize gravitational theory. So this experiment goes as follows. This is a Stern-Gerlach apparatus. We don't really care about the details. The only thing that we care about is that this is needed so that this ball, that is a 1 centimeter ball, and this is important that it's 1 centimeter, because at the time they knew this was a source of gravity. The gravitational field had been measured. So this Stern-Gerlach apparatus prepares this ball in a quantum superposition of position up and down. Then Feynman says, since I know there is a gravitational field, there is an amplitude that the gravitational field is up and an amplitude that the gravitational field is down. How do I test that? Well, Feynman knew we need to see interference. It's not enough to just look at the deviation of the ball or of some other object. So he wanted to put a test particle, let it interact gravitationally with the big ball, and then they would become entangled, basically. So he didn't use the word entanglement, but that's what he had in mind. And then he concluded that if you believe in quantum mechanics up to any level, then you have to believe in gravitational quantization in order to describe this experiment. Good. So now, let us see. So there was a lot of debate. So there were many results and many discussions after this conference on this topic. And recently, so I don't have time to go through this discussion, but recently this has been revived. And there is a new proposal. So this is currently the two proposals that are discussed the most, where instead of one source of gravity, you have two sources of gravity, this blue one and this red one, that are initially prepared in a product state of two positions, and each one is in two positions, x1, x2, x1 plus d, x2 plus d. Now, you let them interact by the Newton potential. And if you write the Schrödinger equation, just the usual Schrödinger equation in quantum mechanics, what you find at the end is an entangled state where the relative phases here are basically the Newton potential where I and j labels the distance between each path, each possible combination of paths of this interferometer. There are 4. And so you can look at the entanglement rate. So just believe me that this is the equation that you get. And if you take two masses that are like the blank mass, 10 to the minus 5 grams, separated by 100 micrometers, and each one delocalized by 1 nanometer, then you find an entanglement time of 0.1 seconds, which is not the age of the universe. So for this type of research, it's very good news. But there is immediately like a criticism that is that to obtain this result, you only use the Newton potential. That is the only element of gravitational theory that you needed in order to get to this conclusion. So let me just briefly explain why the Newton potential is a limit. So first, let me say that if we embed this experiment into a theory of general relativity, so we take general relativity, and we know that the Newton potential is not the end of the story, basically. And on the other hand, we take quantum mechanics, then classical general relativity as a field theory and quantum mechanics does not generate entanglement. So this is, to me, this is the best statement that we can make at the moment on the significance of this experiment. So you know that you have to go beyond, but this is a very theory-dependent statement. So is it possible to just list a set of assumptions that lead to this experiment that do not depend on the theory itself? And how general is this statement? But now, let us look instead at the experiment itself. Let's imagine that we are in the lab pressing buttons and collecting data. So in this case, we use the Newton potential and quantum mechanics. And that's all we need to derive the results. And the Newton potential is still compatible with a weak field and non-relativistic limit of general relativity. So if I want to know what gravity is at a more fundamental level, usually I have to look for the deviation from a behavior that I have tested and that I'm currently using for my usual description of the physical theory. And this is not the case for this result because it's still Newton potential. So the question is, can we find effects that cannot be explained within a limit of GR? And in the rest of the talk, I will tell you how to answer these questions following two different paths. The first one is what I will refer to as a theory-specific approach, where we use a specific model of gravity in the quantum regime. For those of you who are familiar with it, linearized quantum gravity, that is basically the only widely accepted model for describing gravity as a quantum field. And on the other hand, I will use a theory-independent approach, which is inspired to the logic of Bell's theorem. And so basically it relies on coming up with logical arguments that do not assume the theory. And each of them has pros and cons. So in particular, this approach is useful because it allows you to derive precise predictions. And so to tell you exactly which quantum aspects of gravity we can test in this regime. But on the other hand, it assumes the theory, so we cannot prove what the theory is, just logically. On the other hand, this approach is the pros are that it is robust against the modifications of the quantum formalism because it doesn't assume it. It allows us to verify the internal consistency of the theory, and it also allows us to classify alternative models for gravity. But on the other hand, so it's like this is very new research, so there are still many notions that yet have to translate to a quantum information language, and it is very abstract, so it's very hard to get concrete results, to put numbers. So these are the two main results that I will talk about, and this one in particular is with Mirjam, who's there in the audience. So let me start from the theory-specific approach. Here, remember, we assume the theory, and we want to ask which quantum aspects of gravity we can test. And we want to look for something beyond the Newton potential. So let me just review the classical solution of Einstein's equations. So we said that it is necessary that the It's okay. So here the matter is classical. So if we take a classical state of matter, then ideally this is a point in phase space. So it means that I can arbitrarily localize it in X and P. And this arbitrary localization in phase space is very important for what follows. So now, you can see that actually, if we want to recover the Newton potential from this, then it is not enough that we have weak gravitational field and non-relativistic limit, but we also have to put in that the source is classical. So when it is not, when this one fails, we have to reassess. And if we take a quantum state instead, this quantum state is not a point in phase space. It will be more like a blob in phase space. And very famously, we have to satisfy the Heisenberg uncertainty principle. So a quantum source is not necessarily in the limit of the Newton potential. So we have to show it still, but in principle, we cannot just assume it. So now let's see what is done in the literature. So what people do in the literature typically is to consider a superposition of localized states, and they write it as a superposition of position eigenstates. Clearly, this is not a physical state. So what people actually mean, also because this has is completely spread out in momentum, which is not what we want. This is a superposition of Gaussian states, of coherent states. And each one of these coherent states is very well localized in X and P. So this means that the localization, the width of this coherent state is smaller than the experimental resolution. And under these assumptions, only under these assumptions, if I take the T00, so the stress energy tensor, and I apply it to each one of these coherent states, then I obtain approximately the classical energy density.
I don't understand what you mean by the experimental resolution here. I mean, yeah.
So if you want to measure, for instance, the delocalization of the coherent state, you cannot measure it. So it is effectively a classical distribution.
I don't know. I mean, is there some particular experiment that you mean?
No, I don't have any in my any particular experiment.
Okay, so you're just saying about why things look classical?
Yeah.
Okay, okay, that's just right.
Okay, so under this assumption, I can approximate this as the classical energy density. Now, what happens to the state of gravity? Let me just make an analogy. So this will not be precise, but it's just to give you some intuition of what is happening in the description of gravity. So roughly, the Hamiltonian of the gravitational field and with this type of sorts looks like a quantum harmonic oscillator, that would be the gravity side, with a constant external drive, which would be basically Fi labels the position of the source, so R1 or 2. So if you solve the ground state of the harmonic oscillator, then this will be a coherent state that is displaced due to the classical force. And the same happens when I consider, well, very similarly, we will have the description of the gravitational field. Except that of course, it's a bit more complicated because we have a gauge theory. So what we do is to take the gravitational field, expand it as a Minkowski background plus a perturbation, like you do in gravitational waves, then quantize the perturbation. When we quantize the perturbation, then we can solve these equations with the T00. And what we obtain, if we run through the machinery, is that we have a state of the source and the gravitational field, and each one of these HI is such that basically would correspond to this coherent state with some classical solution. And the only difference between different i's here in the expression is that, So they differ basically only by the classical solution of the Gauss law, which is the Newton potential. So it's basically like taking a coherent state, centering it in a different point, and superposing that, where the center is given by some classical equation. So it is quantum, but in a very limited sense. So now the question is, how can we generalize it? So we have seen that this is really fundamental in order to get the result, this approximation. So the idea is, well, what if we use a state where we cannot apply this approximation here, so something more general. So let's just consider a general quantum source. And this will, in general, so it will have some spread in position and momentum that can be appreciated experimentally. Now, the first naive attempt that you can do is, well, great, I know that coherent states are an over-complete basis of the Hilbert space. So let's just expand it in coherent states. So I will do this expansion, and then I can even choose the coherent states in such a way that I fall in the same condition as before. And if I do that, I still find the Newton potential. But there is a problem. Let us zoom in, and let us consider two such coherent states, and I can take them so that they are arbitrarily displaced by a very, very small amount, so that I know that the scalar product of these two coherent states is different to 0. And in general, they will be in that expansion, two of them. But now, if again we compute the gravitational field associated to that, we find that as soon as we put the gravitational field, these two become orthogonal. So this is a non-physical situation. So this means that when I expand the coherent states in this way, I'm making a mistake in my approximation. I'm missing something. So then we have to use a trick, which is to change basis. So we have to abandon the local intuition that we have from classical physics and gravity, and to use a non-local basis of the Hilbert space that is a basis in which it is convenient to write the T00. So it's the basis of eigenstates of the T00 operator. And in general, this E of x is a function that will be different to the classical energy density. If we do that, then we find a good scalar product.
Flaminia, is the same basis for no matter what the value of x is?
No matter what?
The value of x is?
So it is a basis that lives everywhere, basically. It's a non-local basis.
Okay, so all these T00, they commute with each other?
Yes. So in general, it wouldn't. There is a result by Stringer that says that the T00 at different locations does not necessarily commute. Sorry, the T00 does not necessarily commute with itself. But since here we have that all the Tij's are 0, it commutes. Okay, so now let us do an experiment, the simplest one that we can think of. So we take the source in the simplest state possible for a gravitational field. Sorry, for the simplest state possible, so it can be, just to fix the idea, white Gaussian. And then we take a test particle here. We let them interact gravitationally, and at the end, we recombine the state in such a way that we detect interference. So we will have a total Hamiltonian that the only thing that I want you to notice is that this gravity Hamiltonian has an explicit expression, but it depends on the operators of gravity and its canonically conjugated momentum. And this is just a standard interaction Hamiltonian between gravity and matter in linearized quantum gravity. So we find two effects. The first one is that the relative phase, this delta phi with capital delta, at the end of the experiment has a functional form that is different to the Newton potential. And in particular, we checked whether we could reproduce it with another known model, at least to us, where gravity is kept classical, and we couldn't. So we cannot reproduce it with the Schrödinger equation. We cannot reproduce it with any classical quantum coupling, for instance, with Jonathan Oppenheim's model. And the only way in which we thought we could reproduce it is by choosing an ad hoc non-local potential. But this, we have no idea where it would come from. And the second effect that we found is that since now we have a Hamiltonian for the gravitational field and that depends on h and pi, and there are field operators here that canonically commute. This alpha is just a bookkeeping device. So and hence this means that the free Hamiltonian of gravity does not commute with the interaction Hamiltonian. Then we find a correction to the relative phase up here that depends explicitly on the gravity commutator. Already in the same regime of all these of the experiments that people are thinking about, because it's still G. So in the gravitational field, these are both G effects. So this will be probably more challenging to test because it scales like t squared here.
These Tij are not supposed to be 0?
So, okay, no. So it's a little bit complicated, but if you only have the sorts, then you have a static sorts, and you have a T00 for the sorts, and the Tij's for the sorts are all 0. In the moment when you put a test particle on it, then you have the gauge becomes more complicated. So you have to resolve everything again. And then the Tij of the probe particle, because this is the probe particle, are not 0. And so it's like,
Just believe.
Okay. So just let me conclude on that. So basically, the take-home message is that if you do an analysis with just a general quantum sorts, and you put in linearized quantum gravity, all the machinery, then you find that not necessarily you have the Newton potential at the end of the interference experiment, but you can have a more general phase. And this is what we were looking for, to look for deviations from classical gravity. And a commutator effect, a quantum commutator effect of gravity that you wouldn't get even if gravity was a classical field. Now, this is for what concerns the theory-dependent approach. So the answer was yes, we can find more general effects than the Newton potential. Now let me go to the theory-independent approach. Yeah.
So before we go to this theory-independent, so you also mentioned Jonathan Oppenheim and before that Lajos Joshi and Antoine Tilloy, but they all had that as a consequence, and I think you too at some point, that when this classical gravitational field has to contain some randomness and indeterminism.
Exactly.
You didn't mention that, or did I miss something here?
So okay, so you have that gravity. So you have some randomness and some stochastic behavior if you couple classical gravity to quantum matter. Here we're coupling quantum gravity to quantum matter.
Okay.
So here everything is unitary. So there is no mystery here.
I'm trying to understand. In the last one, you resolved your source into these little packets. Okay. But there was, at the beginning, there was the idea, I'm going to have a source, I'm going to put it in a superposition of macroscopically different states, right? There's nothing about that here, is there?
No, this is just a general quantum source,
okay. and
so we solve it in this E basis.
Yeah, so if I just think in terms of GR and normal semi-classical stuff, it's instead of doing it flat, if I do it in GR, I'm going to put a source in, I'm going to get some curvature, that curvature will affect this phase, right? Just by doing this thing on a curved manifold. Is that correction to the relative phase going to be different than what you've got here?
It's not a correction that you would obtain in classical GR, yes.
It's a different one.
It's a different one.
Okay.
Okay,
Yeah. Just one thing, it's related to this Jonathan Oppenheim. Which are you using like the model of Diossi, the one of the?
No, we are not using any. So what we use is just we took the Schrödinger-Newton equation as is defined by Angelo Bassi and collaborators. Yeah. So that's one model that we used.
Doesn't make any sense. Okay, so no, but I mean the one of that is linear, right? I mean. And
yeah, none of them is linear. So collapse models are linear in the density matrix.
But Diosi's model is a type of collapse model. You just make a weak measurement of the position and then you make a.
No, the Schrödinger-Newton equation is not linear, not even in the wave function.
I'm not speaking about the Newton-Schrödinger equation.
You're not talking about the Schrödinger.
No, I'm speaking about Jonathan Oppenheim's work, right? I mean,
it has randomness. It has decoherence and diffusion.
Yeah, exactly.
Yes. So you
calculate things with
So with Jonathan Oppenheim's model, you would have these decoherence and diffusion effects that we don't observe here, because everything is unitary. So in principle, you can recombine everything unitarily with, I mean, of course, then up to experimental precision.
For a finite time, is okay. I don't know if anybody has solved numerically this kind of equation, because if you like to put, say, two masses, it's already 6 degrees of freedom and they're continuous, and no computer can stand it unless you use Monte Carlo or something like that. That's why I was asking, right? I mean, if you do the simulation with a finite time, I wouldn't know how to do it.
But with Jonathan Oppenheim's model, you mean?
Yeah, yes, yeah.
So I know that they're putting, so for instance, even for classical gravity, they would observe a deviation. So they would observe this diffusion effect. No decoherence, of course, but still diffusion. So even just with a drop tower that is being done nowadays, they would observe a deviation from the effect that we expect.
You must be doing some approximation where you drop some kinetic term or something like that, because otherwise I don't understand how we can solve the equation.
Could we let the speaker talk about her work?
No, it's about her work, because she's saying that she's had a result related to Jonathan Oppenheim. I think
but it's not.
I'm just saying that it's different to Jonathan Oppenheim's.
Well, you said that you couldn't find the face in the work of Jonathan Oppenheim. So I don't with the model of
our
Jonathan.
face is, so our result is different to what he would get.
Okay.
That's my
Okay,
statement.
so you didn't calculate anything. Okay.
Okay, so here the question is, let us imagine we are in the lab, we make measurements, and then in the end we want to make some statement on the nature of gravity without assuming the theory. What can we say? And to do that, we used, so this is work done with Thomas Galli and John Selby, who are the real experts on GPTs in this work, so with general probabilistic theories. And you can see general probabilistic theories as a way of leveraging the reasoning of Bell's theorem to the level of the whole theory. And you start from the perspective that a theory is a set of rules that allows you to deduce probabilities of experimental outcomes. And in particular, you can characterize any GPT system using 3 procedures: preparation, transformation, and measurements. So preparation, you can see them as the set of operationally equivalent procedures that in order to prepare some state. And transformations, you can see them as whatever happens in the laboratory with devices acting on your system. And these are linear transformations that preserve the same states. And finally, measurements are all the operationally equivalent procedures that allow you to derive a classical outcome. And if you can characterize abstractly these 3 sets, and with these 3 sets, you define your physical theory. So this is very abstract. I know, but so for instance, let me give you 2 examples. If we have a bit, so a classical bit, then these 2 bits has a state space that has 2 pure states, this delta 0 and delta 1. And all the points that connect these 2 states are the mixed states. And then you have one measurement. If you throw a coin, you can either have head or tail. And then the pure states are perfectly distinguishable. If you have quantum theories or a qubit, instead, you have that pure states are all distributed on the surface of the Bloch sphere. You have 3 measurements, the Pauli matrices, and then only the states that are on opposite side of the Bloch sphere are perfectly distinguishable. So this, you can characterize the set in this abstract, classical and quantum theory in this way. And one thing to notice is that while we usually think of quantum and classical as 2 alternatives, in GPTs, these are just 2 possible theories among many. And this, for instance, allows you, so I don't think that this is interesting because I think that there is some other theory that is currently relevant for us that is out there, but because it allows us to test the internal consistency of the theory at once with just one single argument, so without assuming the theory. And also, hybrid models can also be put here, and as long as they admit a probabilistic description. So the theorem that I would like to tell you today is related to the generation of entanglement. So in particular, we consider 2 systems A and B that are our sources of gravity, that we initially prepare in a separable state, and the gravitational field G that is initially in a product state. Then we assume that there is no other interaction except for gravity that can basically that can influence A and B. And then we find that there are 3 statements that are incompatible. So at least one has to go. So the first one is that the gravitational field G is able to generate entanglement. The second one is that A and B interact via the mediator G. And the third one is that G is classical. So let me just comment on that. So G is classical means the usual definition that one takes in GPTs. So it could be that you want to loosen that, and then you would have to revise this theorem. But this is the definition that we took. Then the second one means, so if we write it in circuit notation, basically that A only interacts with G, and B only interacts with G. There is no direct interaction between A and B. And then what you obtain is that you can start thinking about other models of gravity. So the easiest thing is all models that want gravity to be quantum clearly violate the third condition. If you take models such as gravitational decoherence or collapse models, then they would violate condition 1, so they would not generate entanglement. And the Schrödinger-Newton equation is a little bit more tricky because there is no GPT model at the moment that corresponds to the Schrödinger-Newton equation. The only thing we could find is some old work by Bogdan Milnik in the 70s, where he shows that for the single particle picture, the state space of nonlinear models, such as the Schrödinger-Newton equation, are basically simplex, so they are operationally classical. So if there is such a model that corresponds to a GPT model for more than one particle, which we do not know whether it exists or not, that corresponds to the Schrödinger-Newton equation, this would violate condition 2, because there could still be entanglement, but this entanglement is not due to the gravitational interaction that mediates it, but to the fact that the state knows non-locally what happens at a different position.
Can I ask a very brief clarification question? What's the difference between the assumption we assume that the systems A and B only interact gravitationally and 2 below?
So here it means that there is no hidden other source like electromagnetism or any other. So it's a more general.
That's not implied by 2.
No.
Oh, okay.
No, because you could still have some unknown thing that operationally you do not know that there is some other interaction, and so at the operational level you can still have to consider it and can still give some effective behavior.
See, okay, I read 2 as A and P only interact via the mediator, but you
Ah,
didn't
no,
write the
no.
only.
Yeah.
Yes, right. Okay. Thanks.
Is it known that the DOC model, which is a decoherence collage model, does not satisfy condition 1?
Yes.
We can discuss this because I think it's not that clear. Huh?
It's an open system model.
Yes, but it starts with a measurement of the 2 masses that can
So
be
there are
entangled.
different versions of that. So it's we were really looking at the literature when we were working on this paper, and it's very confusing because different papers say different things.
Okay.
But so in the end, at least the references that we cite seem to agree that it's an open system dynamics with noise, and so it would not lead to generational entanglement.
I think that DOC's model, the one he likes the most now, would violate 2 but not 1. Possibly it satisfies 1.
So, but I think that that version of the model is closer to the Schrödinger-Newton equation than to the collapse models.
So you're referring to this paper with Antoine Tillot.
Yeah, exactly.
I think Miguel is correct. But anyway, that's not your problem here.
Okay, so there is another theory that I'm not going to talk about in the interest of time. So let me just summarize what I said. So we have seen that if we generate entanglement by the Newton potential, so the best statement to me that we can make is that it cannot be explained with general relativity and quantum theory as separate theories. But we can do better than that, and in particular, we can do better if we follow these 2 approaches, and I believe that both are necessary for different reasons. So, in a theory-specific formulation, that is the first part of the talk, we can find effects that cannot be explained with the Newton potential, nor a non-model to us, at least, of classical gravity. And these are effects that are non-relativistic, so they are in the same regime of current proposals, and do not depend on graviton emission, which is the other typical regime in which the people are looking at. The other approach is instead the theory independent, so it's inspired to the logic of Bell's theorem, and it implies basically coming up with no-go theorems where you list assumptions that do not depend on the theory, and you come up with at least with a result, and then you know that if you violate one of the assumptions, so you know that based on the experimental outcome, you can see which assumption has to be violated. And this is, to me, interesting because it is a test of the internal consistency of the theory, it is robust against modification of the quantum formalism, and it allows us to classify alternative models. And so the reason why I'm interested in this is that I think that if we will have experiments that test this regime, and we will have experiments that will test this regime, then we cannot just be happy with saying, okay, we generate entanglement via the Newton potential, and then we show that gravity is not general relativity. But it is very different if we can say something more, and we can test quantum aspects of gravity in a broader sense than what has been discussed so far. And with this, I would like to thank you for your
Can you just go back 2 slides? I just want to understand something conceptually. Yeah, here. So you've got condition 1 is gravitational field is able to generate entanglement. And then under the first thing, you've got that that's violated under gravitational decoherence. And I don't understand that because decoherence usually requires entanglement, right? So if it's a decoherent solution, it must be relying on entanglement. It's not denying it, right?
That's correct. So what we refer to when we make this statement is that these are models of gravitational decoherence that are fundamentally assume a quantum description of gravity, but also fundamentally assume a decoherence mechanism. So it is operationally impossible to test any quantum feature of these models because everything decoheres.
Okay, all right. So that's very operational.
Yeah,
I mean,
it's
theoretically,
very
it's the other way around, kind of. You know,
It's
it's
very
because there's so much
So
entanglement
if
that you can't see it.
If you want to make an ontological statement, then you would say that these models are ontologically quantum, but at the operational level, all these quantum systems.
Okay, yeah. All right, thank you.
Yeah, could you go back to the first part of your talk and I guess the new predictions? Maybe around here. So so I understand so it's theory dependent and you're making a new prediction. And presumably this is much harder to try to measure accurately than just a phase shift as like the sort of naive.
So we do not know yet. So that's the
Right.
part that we're listing at the moment.
Yeah.
And we're in touch with Markus Aspelmayer to try to look at that.
Okay, so my question was, I mean, I understand, it's sort of real physics that you make a prediction and you test it, but if you had in mind testing this hypothesis against the sort of more naive calculation which you put up first, is there a problem that the sort of more naive calculation is just not really well defined because we don't know how to calculate it in general?
So the calculation, the more naive, I guess you mean the Newton potential. So you could write the Newton potential, but it wouldn't. So you're missing some terms. So basically, you would not detect. So you have additional terms in the phase. So the naive calculation only holds in a specific regime. It's a limit of this calculation.
But I guess, is there a Newtonian theory, Newtonian potential mediated theory in general? You're saying yes, there is. There's no problem to just write that down.
Formally you can write it,
right?
But it will be accurate only in a specific limit of this calculation.
I mean, that's good. It means you can, in principle, distinguish them then.
Yeah.
I was just trying to clarify whether the other theory did give, in fact, a definite prediction.
It does. It gives a definite prediction, but you can show that it's functionally different from this.
Did you have a very short question?
Well, I'd like to understand a bit better what this energy basis is, which was maybe a slide before. What was the stress tensor supposed to be the stress tensor of?
So the stress energy tensor is the stress energy tensor of the field that describes the source.
Right, so that could be a standard quantum field
Yes.
theory. Right, yes. And so you're looking for a basis that supposedly diagonalizes this at a point.
Exactly.
And you know that the spectrum, if such a thing existed, the spectrum would extend all the way down to minus infinity.
Yes, but then you only consider some specific states.
Okay.
So you just restrict it operationally.
Yeah, okay. I want to think more about whether they really do commute. So the statement they commute is that they commute at space-like separation. No, space-like separation or at all points.
In our case, so the T00 just commutes because the expression has only Tij's in the commutator. So all the terms that would not make it commute vanish in our case. In our limit, because we have a static mass.
Very good. So thanks, Flaminia, again.
I don't understand what these coherent states.
Now move on to the talk of Gilles.
Not a well-defined theory of the Newtonian potential.
I think she said this is just introduces this energy.
Yeah, okay. All right. It's just it's a foil. Yeah, okay.
So Gilles.
Okay, vote tests.
This worked. Oh. All right. So I changed the title of my talk to be more in line with this workshop. So it's the same talk, but it's a more relevant title. What did Bell really say? And since this is the 60th anniversary, 40, I really mean what did he say 60 years ago? All right. And the answer is not this, because that obviously is CHSH, which was 5 years after Bell.
And in fact, if I can believe something I found on the internet, this picture was taken in 1982. So he didn't say that. He said this. Fine. And before I start, I must tell you in all humility that I'm not going to tell you anything about my own work. Everything I'm going to tell you is other people's work, in particular my former student Paul Raymond, but not only. So I'm more like a messenger here. I want to communicate to you something in which I believe rather strongly and which is not, I think, the consensus in this room. All right, so you all know that the Nobel Prize laureates in 2022 were in chronological order: Clauser, Aspect, and Zeilinger. And this, in fact, happened exactly 100 years after Einstein got his Nobel Prize. Now, if you're good at history, you know that Einstein got a 1921 Nobel Prize, but that was attributed in 1922. There were no Nobel Prize given in 1921. And like after the fact, in 22, the Nobel Committee gave the 21 Nobel Prize to Einstein. So it really was 100 years later, which I find quite remarkable. All right, so they got the Nobel Prize, as you all know, for experiments with entangled photons establishing the violation of Bell inequalities. And what does it mean? Let me first show you a few slides from Alain Aspect. He gave a talk just last week at ETH. And I took a few pictures of his talk. So in Aspect's talk, it's all about a failure of local realism. And local realism must be abandoned. Just to set the stage, the point of my talk is to say this is not the case. He also wrote a paper in 2017, I think, after the so-called loophole free Bell experiments were conducted, saying that we should renounce local realism. All right, so Aspect is very clear about that. And sorry about that. In Scientific American, after the Nobel Prize were awarded, the big headlines, not only Scientific American, but all over the place, including New York Times or whatever, the big headlines were that the universe is not locally real, and the physics Nobel Prize winners proved it. And if you look at the small print, the universe is not locally real, where local means that objects can only be influenced by the surroundings. Any influence cannot travel faster than light. This is not true, according to at least this journalist interpretation of the Nobel Prizes. Evidence shows objects are not influenced solely by the surroundings. In other words, non-locality. And therefore, sorry Einstein, but there is spooky action. This week, we had lots of great talks. Chris? It's not necessary to assume that the state actually changes when there's a measurement. I'm not exactly sure what he meant, sorry. Is he here?
Yep.
Yeah. But I don't know if it meant that there's no collapse.
So what it meant is that in order to interpret the update rules, you do not need to actually say that there is a collapse. You say that the question has changed. Yes. That
I have a picture.
I think that going from a computation of conditional probability to computing the same answer using an updated state. And so you think of it as bookkeeping. And that's consistent with the model we have. It's all that's necessary so far. It's not.
Yeah. What was not clear for me reading this is if you believe the collapse happens or not.
Well, you can infer that I am collapse skeptical.
All right, collapse skeptical. So very good. And then Tim Mullen gave a remarkable talk on ten-dimensional relativity and quantum theory. In particular, no local causal theory can predict what quantum mechanics says. Quantum mechanics says, and indeed, the Nobel Prize winners 15 years ago actually showed experimentally that quantum mechanics is correct, at least in terms of its predictions, and therefore, conclusion, no local causal theory can be correct. Well, not exactly sure here either what about the meaning of local, about causality, because I don't think in terms of causality, and I don't think nothing that this is wrong at all. But if by causality you mean that, if by this statement you mean that when you do something here, it could be that there's an instantaneous effect over there, if that's what you mean by this sentence, then I don't agree. But let me continue. But since I was on the topic of causality, I just want to make a small announcement that there will be a workshop on causality, causal worlds, at Perimeter Institute in September. I'm not involved in that, but my very new colleague, I have a new colleague who just going to start immediately after that at the Université de Montréal, and he's the main organizer, so that's why I'm making this plug. Now let's come to the main point of my talk. Does Bell's theorem imply that our world is not local realistic? Of course not, because Bell's theorem is mathematics, not physics. So now we also have to add plus the experimental vindication of quantum theory. So do these two together imply that our world is not local realistic? And I sort of figured from all the discussions so far that most of you believe this is to be the case, that it's not local realistic. And the point of my talk is to argue against that. Now, I'm not saying that the world is local realistic. I believe it probably is. I like to believe it is, but that's not what I'm saying. What I'm saying as a certainty, not as a belief, is that none of these experiments can be used as evidence that our world is not local realistic. In other words, all right. And this is not new. Back last century, in 1999, on the archive published in 2000, David Deutsch and Patrick Hayden published a remarkable paper. Really, from last century, not new at all, 25 years ago. Showing that all information in quantum system, notwithstanding Bell's theorem, is localized. In other words, measuring or otherwise interacting with a quantum system does not affect distant systems from which it is dynamically isolated, even if they're entangled. So what this says, you have a pair of entangled particles, you do something here, it has no effect whatsoever there. So that's the Deutsch-Josa thesis, sorry, Deutsch-Hayden thesis, 1999. And I'm going to talk about, not about their paper, because it's, but their result, yes, it's great. I couldn't assume that their paper is easy reading. But fortunately, one of my former students, read it for you. And if you're curious about the Deutsch-Hayden paper, I recommend you read this first, in which the Deutsch-Hayden idea is explained in easy terms. Deutsch-Hayden also, in fact, talked about teleportation. In their paper, they show how teleportation can be explained as a purely local process. If you don't know teleportation, that's here in my back. So Deutsch-Hayden explains completely how you can understand the entire teleportation process as a local procedure with no active distance whatsoever. And back to my former student, he explained that as well. So this is not new work. This is really explaining the Deutsch-Hayden version for teleportation. Very well. Now, you all know, I suppose, that David Deutsch is a major proponent of many world theories. And we know from Renato talk that many world doesn't work. So if many world doesn't work, and what I told you about is the work of someone who believes in many worlds, then maybe we shouldn't believe it. Well, not so simple. Not so simple because the Deutsche idea can be rephrased in a way that is not many worlds. That's what I'm going to tell you about. Not exactly. That's standard many world, at least. It's a version of many world that does not suffer from Renato's objectives. Very well. Now, what's the usual argument against local realism? It goes in two steps. One is quantum theory cannot be described by local invariables. Two, if you want to be local realistic, you must be described by local invariables. And from the two, the conclusion follows that quantum theory cannot be local realistic. And the first statement is true, that is Bell's theorem. But the second is false. There are other ways to be local realistic than local invariables. And therefore, the conclusion does not follow. Doesn't mean it's false, but it means that the conclusion doesn't follow. But that is false. So, to do that, I have to tell you what I mean by local, or what Paul means by local and realistic. So a theory can be local or not. It can be realistic, and it can be non-signaling, which is different from locality in an important way. So let me tell you about what we mean by all these terms. Starting with non-signaling, then I'll tell you about locality, and then realistic. In fact, I will start with signaling rather than non-signaling. And I will do that with a cartoon. In a signaling theory, you have Alice and Bob, and they have this, Alice has this magical device. She can turn a dial to a banana or rabbit. And if she turns the dial to banana, then instantaneously a book about bananas appears on Bob's. Now, this is Jeff Bob's beautiful world, Banana World, where he explains Bell's theorem with bananas and primates. All right. The subtitle is Quantum Mechanics for Primates. Quite funny. But if instead Alice had turned the dial to rabbit, you guessed it, a book about rabbits would appear. In this case, Bruce's book, Schrodinger's Rabbits. Rabbits. And the point, this is signaling because Bob instantaneously will see what Alice has done. That's what's meant by signaling. Now what's, I go the wrong direction. Yes, I went the wrong direction. Sorry about that. I'm sorry about that. What happens to suffer this? I don't know, I don't have my mosaic. Sorry about that. Almost there. All right. Anna. All right. So that's about signaling. Signaling because Bob knows what Alice did instantaneously. How about non-signaling now? In a non-signaling theory, when Alice turns a knob to banana, a ghost appears at Bob. But Bob cannot see ghosts. A ghost is there, but Bob cannot see it. And if instead Alice had turned to rabbit, then the same ghost would appear, but just at 45 degrees. And Bob can't tell. Bob doesn't see ghosts, doesn't know a ghost appeared, doesn't know if a ghost appeared.
This is already non-local causation.
This is non-local, and it's not signaling. It's not signaling because Bob cannot tell, and of course you all understood that this is quantum theory when you replace ghosts by polarized photons. So Alice can make a polarized photon appear at her choice, rectilinear or diagonal, if she manipulates half an EPR pair, and the other half is at bounds. And if you believe in academic distance. Come back to Alain Aspect, we have to accept that measurement at one place changes instantaneously the situation in another place. And that's what non-locality is all about. But this is done in a way that's not signaling. What's a local theory now? In a local theory, when Alice turns to banana, nothing happens at bounds. And if she turns to rabbit, the same nothing happens at bounds. This is locality. You do something at A, and nothing happens at B. If something happens at B that B cannot measure or distinguish or notice, then it's not local, but it's still non-signaling. So that's the important difference between locality and signaling. About realistic. There are many ways to define realistic. One could consider that the first sentence in the EAPR paper is an attempt to do that, or not. But, and you don't have to agree. I'm going to give you a definition of realistic with which you may not agree. And if you don't agree, then what I'm going to say afterward is irrelevant, without being false. So in my point of view, or rather Paul's point of view, we go back to Plato or Kant, and we define something we call the noumenal world. The noumenal world is philosophy. We don't know if that exists. But what it's meant to be is the objectively real physical world. All there is in a noumenal world. Us, we don't have access to it directly. We only have access to what's called the phenomenal world, which is the world of perceptions. And here it's perceptions, of course, not only with our senses, but with any apparatus, as long as it's not limited by laws of physics. That's the only limitation on what sort of perceptions we can have for the phenomenal world. And in a theory that wants to, that this is the only thing that we have access to as experimentalists. And we can posit without ever being able to know if it's true, as Plato did already, we can posit that this exists. And we can try to infer what this looks like from what we can actually observe, without ever being able to know if we got it right. Again, because we want to have access to the phenomenal world. But if we do that as a mathematician, we want to do that to define a noumenal world in purely mathematical terms, and to define a function that maps the noumenal world to the phenomenal world. So that if you knew the state here, then through this function you would know what is perceptible. It's not one-to-one. The same perceptions could come from an infinite number of different noumenal worlds. That's why we can never tell what's the real one. So in a sense, this is the realm of physicists, and that's the realm of philosophers. Well, I talk about perception, but if we go just a bit further, what really exists is here. Therefore, these perceptions, in a sense, are illusions. And if you allow me a little joke, this was not meant initially. I chose red and blue for no particular reason until someone pointed out to me, it was red and blue because of this. Well, no, but I'm glad I did. Some of you recognize Morpheus, who is offering Neo in the Matrix to either take the blue pill and then go back to sleep in his world of illusions and live happily thereafter, or take the red pill and wake up to reality, and that's going to be painful, very painful. Well, I'm offering you the same here. It's not too late to walk out if you don't want to wake up to reality. Close your eyes. But, back to serious. So the state of a system, the state of a system. Before I talk about the world, we can also talk about a system. I don't want to define a system. It could be a particle, it could be a planet, anything can be a system. But any system has a noumenal state which maps to its phenomenal state. So let's talk about, and systems can evolve. I can, at time t0, I do some operation u, and I evolve to the nominal state at time t1, which by the same epimorphism gives rise to the phenomenal state. This infers a transformation at a phenomenal level, but in a sense we cannot manipulate the phenomenal state as such. We have to manipulate the reality, and we see something phenomenal. But we get something here, which is denoted here by the same U, because in fact it's a group element, it's our group actions in real mathematics, and doesn't really matter. But the point is that we use in experimental physics or in standard quantum theory, we use up to thinking at this level. And we may think as philosophers that what really happens up there. Again, not knowing if it's true. Very well. So a system A, I'm going to call n for nominal, the state of a system, at time 0, at time 1. And for nominal, the phenomenal state, again, this is all that can be perceived. It's not what you have observed, it's what is perceivable. And in quantum theory, you all know what it is that can be measured, that can be perceived, that can give rise to to measurements. It's a density matrix. So in this theory, the phenomenal state is the standard density matrix. Now, that's where it becomes interesting. For a theory to be local, you need to be able to do this. To start from the nominal state of a joint system AB, and to take A and B apart, and still have the nominal states of A and B. That's what local realism means. That there is a real state for the part of an integral system, even if you are integral. And it's more useful to use projectors than tracing out operators. Mathematically, it's more general. It doesn't really matter. So you can project AB to A or to B, or both, and get the nominal state. But the difference with density matrices is that in A, you have all there is to know. All there really is about system A. And therefore, you can put it back together. It has to be the case in a local realistic theory that this operation, which is invented for the purpose, what we call the joint operator, can get it back the way it was initially. So you must be able to separate a system in its two parts, or more than two. You must also be able to manipulate each part independently, and whatever you do on one part has no effect on the other. But anytime you want, you can bring it back together and get what you would expect in standard quantum theory. I'm not saying this is possible. I'm saying this is what one would want to have for a theory to be worth called local realistic. And this is what's not possible with quantum theory, standard quantum theory. Because as you all know, each of these nominal states give rise to density matrices, but and you can also go from the joint density matrix by tracing out usually to the local density matrices. But what you cannot do in standard quantum theory is go back to the original. That's what's missing in standard quantum theory for it to be local realistic. Very well. Now, this setting the stage, what do I mean now by non-signaling? Non-signaling means it can be defined mathematically, and somewhat surprisingly, without resorting to probabilities. Non-signaling means that if you have the phenomenal state of joint system AB, and Alice does something, and so you could project it to what Alice sees. This is all that Alice can perceive about her part of the joint system. Now, if Bob does something, Alice does nothing, but Bob does something, and I'm not using a tensor product here because it's more general algebra, but you may think of it as tensor product. So Alice does nothing, and Bob does something, so the joint system will evolve at the phenomenal level. And non-signaling means that if you project back to Alice, nothing has changed for her. So non-signaling really means that these two states are identical. And again, non-signaling can be defined without resorting to probabilities. Now what happens if you take this diagram and go from blue to red? What does this mean? Before it meant that no matter what Bob does, Alice cannot detect any change on her state. That's what it meant at a phenomenal level. At a nominal level, it means that no matter what Bob does, nothing changes at Alice. And that's realism. That's local realism. So this is the drawing that defines local realism. Very well. Now that stage is set, let me tell you what are the principles of local realism in our language. Realism, I said it already, there is a real world whose state determines the outcome of any observations. That's realism, through the fine epimorphism. The principle of locality, no action taken at some point can have any influence on the state of the world at a different point.
Determines is determines with probability 1?
This is all probability 1. But it doesn't matter. It could be, no, I retract. All this works just as well if you consider that the density matrix gives you probabilities. So it's okay that a phenomenal state gives you probabilities only with it. Yes?
What kind of state are you using to state that the real world determines the outcome of our observation?
Well, this has to be built mathematically, which I will not have time to do in detail, of course. But I'm just telling you that the complete details have been worked out by my student. It's about a 62-page paper. But again, at the phenomenal level, he takes the standard density matrices, and then from that he builds his way up to a nominal world that does exactly what you want. It says it's local and it gives rise to the standard density matrix. All right. Now, local realism, you might think it's the union of the two, but not exactly. You need more than that. For local realism, you need not only it's local and it's realistic, but you also need that the observation at point A not only depends on the state of the world, but on the state of the world at point A. But this is exactly what you would think, I think. Local realism means that. There's a real world. It has a nominal state for each system, and any observation of that system, the outcome can be deduced from the nominal state at that point, which could be probabilistic. And no matter what you do at point A has no effect on the nominal state at point B, like no immediate effect. Well, non-signaling is the same as locality, but for observable effects. There's a big difference between non-signaling and locality, as I said before, but I say it again. Non-signaling, Alice does something, it could have an effect at point B, not an observable effect. In other words, with non-locality, non-signaling means that the phenomenal state doesn't change, whereas locality means the nominal state doesn't change. And of course, local realism implies non-signaling. If nothing changes, then nothing observable will change either. So that's obvious. It's obvious, but in mathematics, it's too often the obvious theorems that are false. So it's worth giving a proof. So first theorem, any local realistic theory of physics is non-signaling. Again, this is totally obvious, but here's the proof. Now, oops, I went too fast. Couple clicks here, unfortunately. All right. I'm not going, of course, I don't want to explain this proof. I just want to show you that there's some real mathematics beneath all that. And it's not just empty words, I'm telling you. There's a complete mathematical theory around all this. Your red part means local realistic. If you do U on A and V on B and project on Alice on A, you get the same thing as you project on Alice initially and do only U on that. So this is, because it's red because that's the nominal version. And what the theorem proves is that the same statement is true at the phenomenal level, just replacing n by rho.
May I ask a clarification question on the previous slide, which is connected to that? So you had this first point on the previous slide, which says that it determines all outcomes.
Yes.
But technically, because you haven't spoken about outcomes in the framework, so technically does it mean it determines the phenomenon?
It determines the phenomenal world.
Yes. Which is not necessarily what everyone would understand as outcomes, because
Well, but the phenomenal state is a density matrix, and it's
yes, it's a density matrix, but it's not like the measurement outcome.
It's not every it's not every outcome. It determines what
Yes,
could
I
be.
understand, yes. But I think the terminology, like
No,
outcome.
it's very important. The phenomenal state is not the epistemic state. Nominal in ontic is essentially the same, but phenomenal and epistemic is not the same, because the epistemic state would be what you have observed, whereas the phenomenal state is what you could observe.
So you're not determining the epistemic state, but phenomenological state.
No.
You understand outcomes as the phenomenological state.
No, all right, so phenomenal state is represents all that could be measured, or could be observed.
Yes. Okay.
But hasn't necessarily been yet. All right, now the whole point of this talk is theorem number 2, which is the one that's shocking. And you get all non-singular theories, all probabilistic. So again, the first theorem is totally obvious, not surprising. The second tells you that no matter what theory you have at the phenomenal level that is non-signaling, you can always build your way up from there to a local realistic version. This is what it says. Not just quantum theory. Any theory of physics whatsoever that is defined at the phenomenal level, meaning that you define mathematically what are the states that can be observed and how they're manipulated. As long as that theory is non-signaling, it can be lifted up at a nominal level being local realistic. There is a caveat. Sorry, that's what I just said. So given the very definition, the caveat is that for the theorem, for the proof to work at the moment, we need reversible dynamics at the phenomenal level. So in particular, it includes unitary quantum theory. So that quantum theory, I told you already that the fact that you could do quantum theory local realistically is Deutsch in 1999. This theorem of Paul is much more general, but it includes that. Any theory of physics whatsoever that is non-signaling at the phenomenal level can be explained local realistically. That's what it says. So again, in the quantum theory we have that. And in fact, I wasn't too sure about my timing, so I wanted right here to give you the take-home. The take-home is that no experiment whatsoever whose purpose is to violate Bell's inequalities can be taken as evidence that the world is non-local. Unless, of course, unless your experiment goes against what quantum mechanics would predict. But as long as your experiments agree with quantum mechanics, and because quantum mechanics can be explained local realistically, then your experiment is consistent with the local realistic explanation. Good enough?
Isn't it also, or that the dynamics is not reversible?
Oh, yes, that's right. No, yeah. I was careful to say.
I'm old enough to tell you that dynamics is not reversible.
Yeah, I know that you do. I know that you do. I know that, but I'm going to address it. So here, Nicolas' objection is that because of the caveat that the dynamics at the phenomenal level had to be reversible, if you don't believe in a reversible quantum theory, if you believe in the collapse, for instance, then it doesn't apply directly. Which doesn't mean that we're still hoping to fix that, but it's not yet. What this shows is that as long as you stay at the unitary level, you can do it local realistically. All right. But doesn't Bell's theorem preclude this? The answer is no.
The answer is yes.
No, that's fine. We can discuss afterwards. And this is no why. What did Bell say? Did he say?
He never used the word realistic anywhere.
Never use the word realistic.
He never said anything like that.
He never said that. I agree with you.
But why do you have it coming out of his mouth then?
because the next slide will say that he didn't say that.
I've got the quotes right in front of me.
That's good. So, but I believe that he said something like that later, much later. If this is false, then I will have to check that. But we agree on one thing. He did not say that in 1964. We agree on that. Right? All right. Do we agree that he said this? In 1964, he proved that with local invariables, we cannot get quantum theory.
He said you can't do it with any local theory. Adding hidden variables is pointless.
Well,
you could say you can't do it with any local theory written in English. Right, that follows because you can't do it with any local theory, period.
No, but obviously we disagree on that.
I've got the quotes here.
That's all right. We'll get to that afterwards, if you will. But my point is that local realistic and local invariable is not the same thing. And there are other ways to be local realistic than using local variables. And for this, there are two keys to do that. Each of them is a bit hard to swallow. One is that the tests of inequalities are not complete until Alice and Bob compare their results. Meaning, Alice and Bob, they are far apart. They share entanglement. Alice chooses randomly which measurement to make, and she takes down the results. So Alice builds a big table, input-output. Nothing surprising there. It just looks purely random. Bob, far away, does the same with his sharing entanglement, big table as well. That table is nothing special. It only becomes strange when you bring them together. But that requires the data to move no faster than the speed of light. So you need a speed of light delay before Bell inequality is actually violated. So the claim, I repeat, it's hard to swallow. The claim is that the Bell violation was not, there was no Bell violation at the time Alice and Bob made their measurements far apart. The violation only appears once the data is put together. That cannot be faster than light. And now, before you protest, right, this makes no sense whatsoever if Alice and Bob's data is definite. That's where Nicolas will protest. So you also, for this to make any sense, you also need to believe that measurement outcomes never have to become definite. And my dear Nicolas, I'm going to, Nicolas. Oh, sorry. I thought that. Oh, there it is. So
measurements have absolute outcomes.
So we know from Nicolas, we know that Nicolas believes that that measurement outcomes are definite, that measurements have outcomes, these outcomes are definite, and if you believe that, then it doesn't, then what I'm telling you doesn't work. But
thank you.
Nicolas goes even further, saying that what I'm doing is not physics. That's fine, I'm a computer scientist. But we also have this slide from Howard, which I found really interesting, where he gives 5 statements, and at least one of them must be false. If I remember, he said that what would probably likely to think that it's Reichenbach's principle that fails. And then he gets superpowers and doesn't need it. Well, you've understood, of course, that from my point of view, the one that should be abandoned is number 3. Right? Absolutist observations. If you believe in that, it's fine. So friends. Okay. So for that, you need to believe that all possible results occur simultaneously. And this I must admit, smells of many worlds. And again, we've seen that's a problem. But not exactly. Because many worlds, as most people think of it, if they think of it at all, is an extraordinarily non-local theory. Let me change Renato's starting state. For an entangled state between the cat being alive and the observer being happy, and the cat being dead and the observer being question marks. So I change the state here now. So let's assume that the cat and the observers are in separate locations and they share this entangled state. Then in Everett's standard version of Everett, if you measure the cat, then in the branch in which the cat is alive, in that branch, the observer is happy. And in the branch in which the cat is dead, the observer is whatever, question mark. How could it be more non-local than that? There are two branches that appear magically. And in one branch, the cat is dead and the other, the cat is alive, that's fine. But no matter how far apart, in the branch where the cat is alive, the observer is happy. That's totally non-local. What we need is something else if we want to be local. And in fact, there's a third theorem that Paul proved, which I think is the most interesting, which is that a non-local realistic interpretation of quantum theory cannot be based on a wave function. If you believe, as an Everettian believes, if you believe that the real state of the universe is its quantum wave function, if you believe that, it's a theorem that there is no way you can be local. So we need to do something different than standard mini-world. We need to add more stuff, which some people consider sort of wasteful. But if you want to be non-local, you don't have to. But if in your checklist of things you want from life, if you want the world to be non-local, you want it to be local, then you have to admit, it comes with it, it's a burden. To be local, you need to add stuff to the standard wave function, and a lot of stuff. And in particular, and if we come back to EPR 35, can quantum mechanical description of physical reality because they're complete? Well, the answer is, as Einstein wanted, the answer is no. With one metaphysical assumption. If you make the metaphysical assumption that of locality, then this becomes the answer. The answer to Einstein EPR question is no, it's not complete. But you can complete it. That's what Paul did. That's what Darkin Hayden did. Quantum theory can be completed to become local realistic. And Bell, this I'm sure is correct, in 87 wrote either wave function given by Schrodinger's equation is not everything or it's not right. And the answer is, it's not everything. All right. What I told you about is this paper by Paul Raymond-Robichaud on the equivalence of local realistic and no signaling. It's easy. It's a long paper. I think it's 62 pages, but it's easy reading. It's really well fleshed out. So I really recommend it. But just a couple more minutes to tell you that it's also true for the PR box. What is true? The PR box can be the Popescu-Ulrich non-local box. It also can be given a completely local realistic interpretation. And that's what Paul started from initially, actually. And it doesn't follow because the PR box is not reversible. It's sort of a parallel theorem. But the point of telling you this is that if you think in terms of non-local boxes, and if you look at how it can be made local, it's much, much, much easier than quantum theory. And that's the simplest possible proof that violating Bell's inequality does not rule out local realism. What I mean here is that you don't have to believe anything I said about quantum theory having a local explanation. Because it's somewhat complicated. And you might even object because of measurements. But what this says, and this you cannot object to this because it's about a fantasy world. Paul built a fantasy world which is not meant to be reality, therefore you can put whatever you want in it. And in his fantasy world, we have perfect non-local boxes, and his world is local realistic. And perfect non-local boxes violate Bell's inequality even more than quantum theory. And therefore, even if you didn't swallow anything I said until now, the thing that you cannot reject is that it is possible for some other physics. It is possible to violate Bell's inequality and be local realistic. And therefore, a mere violation of Bell's inequality as such can then be taken as a proof of non-locality. And so this paper is really easy reading. I recommend it, even though I'm a co-author, but it's really all Paul's ideas. I was just his supervisor at the time. And it's really neat because it's all explained in one big poster. Okay, so again, that's the conclusion. It proves that it's wrong to claim that any world that violates Bell's inequality has to be non-local because that fantasy world violates Bell's inequality more than quantum theory, and it is local realistic. All right, I'll stop here. Thank you.
Czeslaw, do you want to start?
Yeah, you said that there are two keys towards the solution. One is a test of Bell's inequality are not complete until Alice and Bob's data are compared. And second, measurement outcomes never have to become fixed and definite. And now I think like, if I would like somehow to give a support to this or to test somehow, then I imagine the following situation. I'm Alice and I write down my outcome and somehow, you know, I wanted to have at least for myself, and that's where I start to do physics, to believe in what I see. And I write down this result and the setting chosen, and I go on to meet Bob, and all the time I look at this just to be sure it's fixed and determined. And then we meet each other. Now, how should I understand that? That what I was, there are two possible outcomes of these situations, I guess, to be in line with your thoughts, that what I am seeing is not.
Now, let me try to answer. I think I got the question. Yeah. Which makes me realize there's something important I didn't say. I told you that in fact, when Renato asked, show of hand, who believes in many worlds, I did not raise my hand. Because I don't believe in many worlds as in Everton defined it, because it's not local, and I believe in locality. The difference between the difference between I'm almost there. All right. Between Everett's many worlds and what Paul calls parallel lives is that in parallel lives, when you do a measurement, or when you think you do a measurement, then there is a split of the universe, but it's a local split. Instead of the whole universe splitting, which is not local, only you, initially only the particle splits, and then the measurement apparatus splits, and then you split with it. So there's a bubble, like a bubble that grows around you, that doesn't grow faster than the speed of light. But when you do the measurement, you see both outcomes. And there's two bubbles. In one bubble, you see one outcome. In the other, you see the other outcome. The two bubbles are in the same physical place, but in parallel. They don't interact in any way. But nothing happened at Bob's. If Bob measures, then there are two bubbles at Bob's as well. And the Alice's bubbles grow at the speed of light, and the Bob's bubbles grow at the speed of light. It's only when the bubbles meet that something happens. That's the example.
And they meet.
So exactly, if you were, so that's what I think you were saying. If you keep looking at, so you make the measurements and then you keep looking at it as you travel towards Alice. Well, you also keep looking at the other answer when you travel towards Alice.
Okay, thanks.
Good.
Max, you want to question?
Yeah, a small clarifying question. You described this splitting and recombining property of quantum states and of states, and then said that quantum mechanics doesn't satisfy this, which of course it doesn't. You know, you take the two reduced density matrices for A and B, and then combine them, and it's not the same thing as the.
Sure.
Isn't this also true of a classical probability distribution? If you give me two marginal distributions,
Sure, it's true as well.
So, I mean, I don't get the point you were making then. If it's also true for classical, then what's the? Can't we?
Well, the difference is that in order to think of local realism, you need to be able to bring the state of the partial systems back together and get back the original. If you cannot do that, then you don't have a complete theory that's local and realistic.
I mean, for a general theory, any theory described by probabilities, if you associate, you make an equality between, you know, some list of probabilities and the state, as you know, in GPTs, for example, then there's no theory for which this will ever be the case, including classical mechanics. No?
It could be, but maybe I'm just inventing here. But perhaps GPTs can be completed as well. I never thought of that. Perhaps it might be interesting to complete a GPT into something that would be splittable and putting it back together able. I don't know.
Okay, so we now have a 20-minute break, so I suggest we discuss the rest of the questions during the break. Let's thank Gilles again.
I just have Bell. Can I read Bell?
People can leave, but
no. Can I just read? What I would like to read. Your first picture was the introduction to Bell. Read it. Sir, then you won't let Bell speak for himself at a conference about Bell. Let Bell speak for himself.
The correct analysis, the matching properly. It's just that, so, but that table was not very clear. We end up rejecting. It's not by them, it's a different, it's a different person. I wanted to. But then I thought, yeah, exactly.
Aber wenigstens hat er gesagt, ich kann sie lieben. Das ist sehr wahr.
Didn't say must be. It's just can be. It must be. Yeah, it can be completed as a local.
Read Bell.
Quickly see what they're
It's absurd.
It is absurd. Just leave.
You have a conference in honor of Bell, and you don't allow Bell's own words. You say during
Oh no, they finished. Still next.
No. I mean, this is just words. This is supposed to honor Bell. And what has just happened is Bell has been silent.
I also have a very strong complaint. You completely misinterpreted my answers.
Yes, please.
No, your cat has never done.
Oh, that's why I never.
You see how important that is?
Because I couldn't figure out what the dots were in your.
Oh, if you look it closely, they're paws.
They're paw marks.
Yes.
Yes.
So the cat
Right.
just,
Okay.
just walked away.
Did you insist on it?
Ramona insisted.
He was very unhappy.
No, but actually I have a more serious complaint. I'm not complaining, but the word outcome, that's like the word outcome.
Yes.
The lexicon perché siamo capaci di lavorare.
It was very, it was not really scientific.
Performance was very religious.
It's very...
Outcomes are real.
He's very atheist, like he doesn't believe in God, but he's so sure that God doesn't exist, and he becomes a believer.
But you're in the year.
So I don't know, he's, yeah, that's my grandfather.
Yeah, here are just the people who believe that.
So yeah, I don't get emotional. Like, I don't know if you have like
You say both happen.
I mean, to get so much emotional.
A single outcome. I think that's the.
We all agree in the main stance. No? We just have different interpretation, different view. Like I don't.
Outcomes is not what one would think.
I forgot to send you the postdoc the scripts of Reconstruction.
Is it determined? Phenomenal field is a dense matrix.
No, This question was, that's clear, it's still probabilistic. But your theory determines the phenomenological state. And because the phenomenological state doesn't determine the outcome in Nicola's understanding.
What I mean, it determines all that can be apprehended.
Here we go, Fabian, some challenge.
Yes, I can reset it. And also this
Range of the border, it's that. So it's just that's it. And if it determines that understanding of outcome. It is claimed that the outcome doesn't.
But I think that unrelated to entropy, I think that's okay.
I have to think about it.
So,
I see what you mean, and I have to think out.
I think it's nice that in this non-local box version, it's very clear what happened. Because there you have this. I think it was the non-local box.
It's a private thing. It's the
Oh.
agent who is doing the research.
Different.
So it doesn't necessarily make sense for other agents. But then we have consistency to say that equal, then it also makes sense for other agents.
The realistic thing is there are these two branches.
You can say, because I think it's a relative protection. Actually, it's what we mean by absolute relativity. That's our original version. It's absolute. And I think
Outcome is like in one branch.
I think it's okay.
You're talking about someone in one branch.
I understand.
Yeah, people think of an outcome as a single outcome. It's more a terminology thing, but I think this was, I found this extremely clear. Apparently not everyone agrees, but I think everything is completely clear except this sentence.
No, she almost had only.
Now tell me, when you read this, do you read local invariables? I do.
I think it's okay. Yeah, I think it's okay. Yeah.
Yeah, that would happen.
Fine. And then here we can keep the same thing.
Like, I mean, he's so emotional. I know him, and he's always like that. I understand his usual level of. It could even.
Cannot be for A, all these things.
So your question is whether it has.
Yeah, these are
variables.
I see local invariables.
Yeah, I think it's okay.
I see.
Even the word variable.
I don't understand what is. I mean, first sentence is about local invariables.
Yes, it is.
So what's this?
I think he, yeah.
Yeah, look, the first sentence is about
Yeah,
local
it
invariables.
clearly says additional.
Yes.
What
I
is-
know.
what is it complaining about?
Yeah, I've had huge arguments with Tim about this as well. Yes.
Yeah.
Okay. But you understand why he doesn't read variables here when he reads them?
Yeah, so he reads very particular parts of the paper and draws an interpretation from that.
Yes,
that
was
the
my
way
impression
I
as well
would-
from his
okay.
talk.
I'm
But
really,
here it's so explicit.
I'm really sorry
Right.
that I didn't have
And
the,
then the next
that I didn't have the.
Yes.
I know, and
Yes.
as I
It's
and the quote that I
more
put up,
explicit.
I know, and the quote that I put up, which is from the conclusion of the paper, says, you know, basically says predetermination and separable. Like he uses, Bailey in this paper, he uses words sort of all over the place. Like he uses, determinism, predetermination, causality, all these things mean roughly the same. But it seems very clear that he has, to me, that he has two assumptions. One which is like determinism or hidden variables.
You're talking about
yes, and the other which is just locality or non-separability or something. Yeah, but Tim totally does not see it that way.
But then,
But I think there's no way you can.
What I'm really sorry about at this moment is when he asked, "Did you read Bell's paper?" I should have said, "Yes, did you?" It's really too bad.
Oh, but then that might have become a fist fight.
Because he didn't read the first sentence.
Yeah, we should have asked, did you read the first sentence of the introduction of it? Did you manage at least the first sentence?
I mean, so I do understand Tim's idea. If you read the next paragraph,
maybe. But
then
he pointed to this specifically.
Did he?
Yes.
Okay.
Specifically.
All right.
He said, "What I flashed." I didn't even read what I flashed. That's what he said. And that's what I flashed.
The first sentence, yeah. Yes. Okay.
So the second, I mean, I read, yes. So the second paragraph is where he references Einstein again. So I read it as a heuristic argument for why you should consider hidden variable theories. Because if you look at the EPR paradox, the natural resolution is to have local hidden variables. Right. And so that seems to be, and then you know, and there's some sort of argument about locality behind that, right? If you think the world, like Einstein did, that the world is local, then, and if you look at the EPR paradox, well, the obvious conclusion would be that quantum mechanics is incomplete, therefore hidden variables, right? And then he goes on to prove the theorem but that doesn't work.
Yes.
Right? Okay. And this is the way I read this first sentence as well. It's just saying that this was an advanced as an argument, right? So he's not saying.
And that's the argument that he contradicts. He doesn't say that in the first sentence, but.
Well, the fact that these additional variables, So
his point is that it cannot exist.
But Tim's reading of this is, you know, EPR assumes locality. They prove that hidden variables must exist. Bell proves that that doesn't work. Therefore, the original assumption of locality must be wrong, and that there's only one assumption that's being considered. And I don't read it that way at all. I read this as being like he talks about EPR not as part of his theorem, but just as a heuristic, just as a motivation for introducing hidden variables, right? Because EPR were the first to suggest that there were, So Tim just reads it in a very different way. And I've looked at all of Bell's papers, and I think there's almost all the evidence is in the favor of the way I look at it, which is the way that most people look at it. But Tim just sees things
But you are
really
very
differently.
specific and refer to that particular thing.
Yeah.
Okay.
Oh yeah, I was. That's right. That's right.
Okay. I always take pictures of slides.
I was very proud that I managed to tweak your.
I don't know, that could be misrepresentation.
Thanks.
It's amazing how different people can read the same text from different perspectives and come up with I guess that's what philosophy is. Of course, it's what philosophy is.
It's really cold.
Yeah, now that you
Yeah,
don't
it's
see
a
it
bit
run
hard.
down by the
Yeah.
University.
Yeah.
Yeah, now you see it.
So I took this, and I was able to do this with it.
That's nice. Okay.
But you can see the, now if you look
No, it's
closer,
not
you
perfect.
can see the editing, but
It's not perfect.
from the distance you don't see.
Yeah. I should.
yeah.
I should
It's almost perfect. Yeah.
That's right. That's
Yeah, not bad.
Yes.
So can I ask, do you know the work of Kai Weigel at Chapman?
Yes.
Okay. So what's the relationship of what he's done to what you and your students do?
Well, Kai was influenced or how should I say? Inspired by the non-local box version. So that's what Paul discovered initially, I think 12 years ago.
Right.
And he talked about this in many places, and Kai really liked it and was inspired by it for doing parallel work. Parallel lines.
Right. But
so yes, I'm familiar with him, and I've talked to him several times, but I couldn't say I'm familiar with the specifics of his work.
Okay.
So I'm not sure how.
If you want to get coffee before the next
Yes.
Überhaupt diese This is getting comfort zone. It's not too bad actually.
Like just all the chairs right here.
Exactly, all backs. Yeah.
Reconstruction of quantum particle statistics.
I mentioned they were not working in this field when they had this conference. They were just mathematicians who wanted to also go for make a report first.
Ja, ich bin
Eigentlich sieht es aus.
Aber das ist einfach, dass er denkt, also ich sehe nicht wel, was man sieht.
Das ist das Problem mit dem Bau.
Genau, also es ist mehr ein pädagogisches, dass du eigentlich so sagst.
Ja. Nicht nur sagt, eigentlich interpretiert hat. Das ist nicht Wort, sondern wie lange
And then she said, you want some wet?
Genau, und jetzt hätte sie da das so allgemeine zum Observer. Mit dem Observer. If you work
Yes, yes.
It's a box thing, by the way. It's a box thing.
So it's changing the color.
If you pass, yes.
And
it's very weird.
What's if you touch it with these?
Yeah, I don't know what function is this.
Research Zurich.
Okay, so let's start again. So we have the last talk of the morning. Borivoje will tell us about the construction of quantum particle statistics.
Thank you. I'm very happy to be with you. So I would like to present the content of this work of my student and myself on the operational reconstructions of quantum particle statistics. This is greatly motivated by the work that some of us have done in the past on operational reconstructions of quantum mechanics. I will come back to this point. And now, in the similar spirit, I would like to say something, starting with some reasonable assumptions about particle statistics, about this and this. But it turns out that we found also some other solutions, some generalized statistics, which we call transtatistics, and I will come back to this by the end of my talk. This is related somehow to one of the main subjects of the workshop on on the theory of measurements in quantum fields and no signaling principle, things like this. So I give you one example why particle statistics matters in this context. So let's consider fermionic operations. Suppose we have Alice as an observer and she can perform some operation on her fermionic system here. So she has in her hand some pool of modes which are defined with ladder operators, this kind of things. And you could imagine that these are like paths of fermions that can propagate here. And she can do some measurement down here. So what is kind of like signature of fermionic statistics is the anti-commutation relations of these two guys. It's really like different with bosons. And now the question is like what kind of operation she can perform here. Sometimes people get confused. This is not a unitary operation ladder operator. It's just a convenient tool to do mathematics with fermionic statistics. But we can make it unitary, for example, in this way. If I make this combination of the ladder operators combined with identity with some prefactors there, so you can easily check that this is a unitary operation. The question is whether this is somehow physically allowed operation. So likewise, we can introduce Bob, who can do something like this. For example, B plus B dagger B is Bob's mode. And this is again a unitary operation. And if they perform this on separate locations, so let's say Alice does U and U dagger and two times, and then somewhere in between Bob does this, so it turns out that this is causing a signaling on Alice's side. So that means somehow something goes wrong here with this let's say, unitaries. They should not be physical unitaries, but at least they should not be interpreted this and that as a local operation. So the whole trick is about this state, so vacuum plus single particle state. And then it turns out, so all operations that could perform this, they're fine for bosons. However, for fermions, you cannot superimpose particle, let's say, sectors of different parity. And that's the famous celebrated fermionic superselection rule that you can actually derive directly from a no signaling principle, right? So somehow, on the top of particle statistics, although we have the entire algebra, have a mathematics, one has to be really careful when we speak of physical implementable operations, what can, what cannot be done. And a lot of these things can be deduced from just some basic laws of physics, like a no signaling principle. So this was a motivational slide, but let me go back to the foundations of particle statistics in general. So everything started late 19th century with the famous Gibbs paradox. So how does it go? So you have an ideal gas with particles, and then you introduce some kind of artificial barrier here. You divide the box into two halves, and then it turns out that the entropy jumps with the square root of 2. And the question is, why is this happening? So we have a paradoxical situation that the entropy is not extensive. The resolution came with this famous n factorial factor that you introduce to the number of microstates, and then if you do that, so then everything goes back to normality. So some people claim that this is a genuine signature of quantum statistics that is somehow already present in the case. But, so I really recommend the article by E.T. James arguing that this is pretty much a nonsense. And as a matter of the fact, even Bose-Einstein or Fermi-Dirac statistics, you don't really need a machinery of Hilbert spaces or superpositions and so on to derive those. So from some very simple rules, you can derive various types of statistics. The question is, of course, why do we have in nature these two types only of particle statistics, or maybe something else like fractal statistics, parastatistics, and so there is a really huge list. Since the birth of quantum mechanics, maybe every few years people invent some generalized particle statistics. The question is, why only these two, why not some of these? And there are in the literature three main, let's say, arguments to argue why this or that. So I'm going to briefly present all three of them. So the first is just a celebrated symmetrization postulate that is from Dirac and Heisenberg. It says you start with the first quantization, just the standard quantum mechanics. You introduce artificial labels of particles, and then you say that the wave function is an exchange of the coordinates, something like this. Right? So you can get a phase here, but then if you, let's say, interpret this a little bit from the mathematical point of view, you will see that these are one-dimensional, so-called one-dimensional irreducible representation of the permutation group, and we know we have two of them. This is then symmetrized wave function related to bosons and antisymmetric one to fermions. There are, of course, few objections one can raise here. First of all, that this is pretty much artificial way to do the things. Then vacuum state is kind of missing in this picture, then superposition of number states like coherent states and things like this. So there is something missing in this picture, but it's a kind of standard textbook argument. The other one comes from topology, where you embed your particles in configuration space, and then you try to identify points like this and like that, and you adopt, for example, Feynman path formulation of quantum mechanics, and if you do that, so then you will see that in dimensions higher than 3, only two types of statistics appear, bosons and fermions. In 2 dimensions, you have fractal statistics, anyons. In 1D, it's kind of ambiguous. There are no solutions and so on. So one can also raise certain objections here, is like that this is kind of background dependent. So it's really very much fixed to the background space. It's coordinate representation, and also some ambiguities that arise from this approach. And finally, something comes from quantum fields where you really ad hoc postulate these kind of things. So canonical commutation or anti-commutation relations. So you introduce ladder operators and you say, okay, I'm working in 2 models, either they commute or anti-commute. And then you introduce a unique vacuum state and you take your ladder operators and you are able to build up your Fock space. And that's the way how it goes. However, it's unclear where does this come from, right? So how do I get this mathematics? And as a matter of the fact, there are simple generalizations of that, like a 3 linear relations. So these guys, they contain these things here. So this is Green's ansatz, which brings us to parastatistics. That's an example, one example of the generalized statistics. And then the question is, why do we not observe parastatistics in nature? For example. About the generalized statistics, so as I said so far, we have not seen this thing appearing in nature, and one can interpret this in at least 2 ways. First, that we need perhaps more precise and more sophisticated experiments, that's option number 1, or some generalizations are in collision with some basic laws of physics that we believe that they are like universally true, like for example, no signal principle. And because of this situation, majority of the generalization to get some generalized statistics, so they resort to somehow to some kind of arbitrary assumptions added to the formalism, the standard formalism, like you modify commutation relations and things like this. And you have no idea really where is this operationally going and why would you do that? So it's fun maths, but it's somehow unclear whether this is physically justified. And then, so what we said, so well, let's try to take this instrumentalist approach that we already learned from the reconstructions from quantum foundations and try to start with a typical quantum experiment that involves particle statistics, and then say, okay, let's try from the very beginning, so somehow to answer some very basic questions. So how do we define identical particles from the operational point of view? How we can establish some clear operational differentiation between particle types, and how to characterize finally mathematical formalism needed to encompass these two things. Because this is the kind of way we want to go. And as I said, so this is really greatly motivated by many successful reconstructions of quantum formalism, where, so Flaminia had this in her presentation, where we started with a typical quantum experiment of preparation, transformation, and measurements, and then you try to, let's say, to assume something reasonable about these things here. These are like operational axioms, and from there you try to derive, to get back the formalism of abstract formalism of quantum mechanics. Nevertheless, in this approach, so what is the main focus is on the reconstruction of the abstract quantum system, right? So without any physical context. And what is missing here, if I want to do particle statistics, I have to add some physical attributes to these abstract systems, like the notion of the indistinguishability and things like this. Start with some operationally well-motivated assumption, which eventually would lead me to classification of quantum particle statistics. So that's the idea. So how do I start? So what do I know? So at least I know one thing, so that one particle is insensitive to particle statistics, right? So if I do just the ordinary quantum mechanics with a single particle, be it an electron or photon, it doesn't really matter. I can just perform a typical interferometric experiment where I can inject my particle in, let's say, d parts. Let's stick to the finite dimensional system. I perform some unitary operation here, and then I measure statistics at the end. So this is what it says here. So the space, the ambient space of my states is just a complex span of these vectors here. And then if I input some state psi, it undergoes a transformation, which we know is a unitary group, is d times d unitary matrix. And then if I would like to calculate the probabilities for the outcomes, I apply the Born rule. So input state transformation, and then I project on some of these outcomes. Here's also like a simple note that I would like to emphasize, that the measurement gets somehow, they belong to a dual space, which is in finite dimension same as this one. But this will be kind of important, let's say, for my reconstruction afterwards. And then now the question is, so if I have designed this, let's say if my colleagues in Vienna go to laboratory and then they design a typical interferometric experiment and say, this is our setup, we have a complete tuning of this unitary here. We know what's happening if I inject one particle here. All of that applies. Now the question is, what would happen if I start ejecting many particles here? Okay. So I have a rigid setup. So I know how the setup is described. Now the question is, what is the mathematics? What will start to happen if I start injecting many particles into the same setup? So that's the idea. And then there are some lessons that we learned from quantum optics, some typical quantum optics experiments, like this one. So suppose you have just a 50-50 beam splitter, and then you can send your particle, let's say, either this way, and then you prepare equal-weighted superposition. Then, of course, you know that the probability to detect particle here or there is 50%. The question is, what happens if I inject one particle here and one particle there? So what's the statistics of the outcomes here? And then the answer really depends what kind of particles you put at inputs. So if you put distinguishable particles, so it turns out with 50% they go separate ports, and with 25 and 25 they go like two like that and two like that. if these are bosons, then we get just the standard Hongo-Mandel photon bunching. So that means photons, they will never go separate ports. They always bunch, either go this way or that way. While if these were fermions, they would just go like this, without bunching. Why there is no bunching for fermions? Because of Pauli exclusion principle, they cannot sit on the same mode, so they have to continue like this. So what we learned from this simple example, here is the mathematics, I will not go through that. So what we learned from this simple example, that somehow simple experiments can in principle distinguish types of particle statistics. Okay, so now I go back to the picture that I introduced beforehand and say, okay, I'm going to start with this setup that is already predefined for a single particle, and I start injecting multiple particles at the input. Now the question is, what is the condition for identical particles? Well, I mean, so at these locations, this guy should register only particle numbers, but should not be able to distinguish which one is which, right? So in other words, so at location, for example, N1, this detector will say, oh, I detected 5 particles. This one says, okay, I detected 0, nothing. This one, for example, says I detected 50 particles, and so on, right? So that's let's say that's the way to define the set of classical outcomes. Now comes an important thing. So if I believe that set of these classical outcomes fully specify all possible configurations, there is nothing more to the story, then it means, well, there was some input state here, there was some transformation here, but be aware I should not put really u here, some d of u, I will come back to this point. And then I simply project on some ket that is associated to all classical outcomes. Modulo squared, this is what is Born rule telling to me how do I calculate the probability for these outcomes. So this is how it goes. Now again going back, so if these guys, they specify the set of the measurement outcomes, they are from a dual space, so that means that the input wave function lives in a space of this type, which is like a Fock space. This is like a complex span of these particle numbers. So in principle, you could introduce that the, the particle number is limited to some extent. Let's say for fermions, we would have p equals 1, maximum 1 particle per mole, but this is not so relevant. For bosons, that would be p equals infinity. But now, what is important, I have to put on this space an action of the unitary group. I know the nature of this object because I know how to assemble this. This is like a bunch of beam splitters and phase shifters. They form a unitary group UD. But now this guy acts in this big space. So it clearly cannot be here D times D matrix, but some representation of the unitary group that acts on this big Fock space. So that's the idea. Well, I mentioned already that. So the max occupation number, we can, as I said, introduce some integer. That will be a characteristic of statistics. For example, for fermions, we will have P1, for bosons P infinity, but that's let's say not super relevant for our reconstruction. Okay, so let me just quickly comment on the Fock space structure, the one that I introduced here. It is things like this. It spans of the set of all possible classical outcomes. These are single mode spaces. So that means that this guy can be seen as a tensor product of D modes, some p-dimensional complex space per mode. However, this guy should not be a priori confused with the standard textbook Fock space. For me, this is an ambient space that I'm using to embed my multi-particle states. Of course, they're going to coincide for the case of bosons and fermions. Let's say what I call here Fock space should not be, let's say, a priori confused with the textbook Fock space as a direct sum of the particle sectors. Now, the question is, and probably here, operational, what I could say the operationally stops, is that how this Fock space structure combines with a unitary group, right? So it's a mathematical question. It's a representational problem. Given this space, I would like to embed some representation of the unitary group acting on this space. And we know that there are at least 2 solutions for bosons and fermions. Perhaps because of the time, I'm going to just skip. How do you get the solutions for bosons and fermions? Okay, so let me give you a few remarks from the representation theory. Now, let's say I'm switching slowly towards mathematics. So I would like to put few remarks. How do I deal with the representation of the theory? First of all, it's sufficient actually to classify all equivalent representation if you just calculate trace of all matrices of group elements, right? You calculate the trace of that. This thing is called group character. And this one uniquely up to equivalence specifies the representation of the group. Okay, so this is going to be one of the main objects. It's very helpful to deal with this if we speak of representations. Second thing is that if I calculate the trace, so it's invariant under this similarity transformation, if you do that, so the trace wouldn't change. Third thing, since I'm speaking of a unitary group, every unitary group can be diagonalized in this way, where the diagonal is just some phases, some diagonal matrix of the phases. That means if I want to evaluate a character, it's sufficient to evaluate a character on a phase group. Mathematically speaking, this thing is called the maximal torus. For a physicist, this is just a phase group. It's just a bunch of phase shifters sitting in different nodes. All right, so all what I said here, if this was a big unitary here, I can kind of diagonalize this and evaluate my character only on these objects. So that's the thing. So this is my target. All right, so how do I calculate the character in the entire Fock space? Right, so this is what I have to, with my Fock space that I introduce, I have to find a way to evaluate this character on the phase group. Well, I mean, if you look at this, one can, let's say, envision this as a dozen of phase shifters sitting in different locations. Now, these are kind of local phase shifts. That makes sense to call them local phase shift. Why is that? So if I inject n particles here, they should just get some local phase here that depend on the particle number. Likewise here, likewise there, and so on. If I put all of that together, what I just said, that means this phase group here, this object acting on a Fock space, is just introducing a local phase shifts here. So that's how torus, how phase group acts on the Fock space. If I have that, so I have representation. Yes, that's the trickery here, mathematical trickery. There is an extra trick here. Instead of dealing with phases, I can introduce phase variables. And if I have that, when you evaluate this guy, what I said about the local phase shifts, then character just becomes a product of these single variable functions. As a matter of the fact, this becomes an integral polynomial. And this is our main object to study. All right, so another thing that I would like to mention here, so if you're familiar a little bit with the irreducible representation, sometimes like the target would be to decompose, if I have a representation of my group sitting on this space, to see how this decomposes into irreducible subspaces. So this is some irreducible subspace, and this accounts the degeneracy of this guy. For the unitary group, these guys are labeled with Young diagrams. These are these boxes here. You don't have to know about this stuff, but here is an example. These are fermionic boxes, these are bosonic boxes, parastatistics, or eventually something else. Now, all of that, what I said beforehand, completely translates into characters, which now become just some polynomials of the variables, and the irreducible characters, these are called Schur polynomials. Okay, this is just the mathematics behind this. Oops. Right. And here is an example of these Schur polynomials, for example, for fermions, like single particle sector, two particle sector. That would correspond to this decomposition, which is really the composition of the Fock space into particle sectors for fermions. And again, you end up with some kind of product formula here, which comes from the locality assumption. Now let me recap of the concepts that I introduced here. If you go to Wikipedia page and say, let's see what does it mean particle statistics, it says it's a particular description of multiple particles in statistical mechanics. Good. So what's quantum particle statistics? This means this is a particular description of quantum states of multiple identical particles. This is what it means, particle statistics. Now, given my operational setup that I introduced beforehand, on one hand side, from the measurements here, I really deduced my Fock space structure, which is this thing there. From the transformation, from single particle transformation, I know that this is a unitary group. Now comes the question between the compatibility between the two, which means I would like to study representations of this guy on that guy here. And we know, let's say, from the case of bosons and fermions, from these simple Hongo-Mandel experiments, that the Fock space decomposes in a very particular way for bosons, in some different way for fermions. In a general, what we expect that this guy decomposes in some other way, and classifying all possible ways how this guy decomposes, that defines particle statistics from the mathematical standpoint. Right? So this is what we want to do. We want to classify all possible ways that this guy can decompose into irrep sectors of the unitary group. So that's the mathematical. Again, about the methods of mathematics, as I said, so character traces of this representation, that defines a representation that's sufficient for me. And as I said, it's just sufficient to evaluate this guy on a unitary group. I said there is a locality assumption that these phases act locally on number of states. And all of that combined together, that's a super strong assumption, mathematically speaking, means that this guy, in terms of this d variable, becomes a product function. And all of that, so these single mode characters, these are just some integral polynomials. But now, this, if I formulate this in this way, that means, well, what kind of integral coefficients I could have here, such that this formula becomes a valid character of the unitary group. This is the mathematical problem that we are dealing with here. And for example, for bosons, you have this expansion like this. For fermions, you have something like that. I mean, you will never guess if you are not trained in this way that this means a bosonic character, this means a fermionic character, but this is what it means. All right, so what are the equivalent formulations of this problem? What Nicholas came up with, let's say, well, we are looking for this kind of coefficient such that this is a valid character. Then he constructed the Toeplitz matrix. This is matrix of this type. It says, well, positivity of all possible minors of this matrix, that means that this is a valid character. It's very difficult to deal with this formulation. So then we got a hint from Richard Stelly, who is an emeritus at MIT, who insinuated, Nicholas posed this problem on the Stock Exchange, say, look at my book. Look at my book and examples there, and that eventually lead to the famous theorem by Eisen, Schoenberg, and Whitney of classification of totally positive sequences. I will not go into this, but this theorem guarantees, when we, let's say, all the equivalent formulations, how to get these guys such that we get a valid character. It's completely equivalent to the classification of total positive sequences. So this brings me to my main theorem here, which says if you are dealing with a character of this type, then this is a valid character of the unitary group, if and only if it comes in two flavors. It's of this type or that type, where these two guys are integral polynomials with all positive or negative roots. That's a technical detail. I don't have to explain this in details. But if you, let's say, would like to write these guys in some kind of, these are just polynomials, these expansion coefficients, if you put them into a list, indicate here plus or minus to indicate if you are here or there. So this thing here, list of integers, defines a particle statistics type, right? For example, this 1, 1 plus minus 1, that would mean ordinary statistics, bosons and fermions. But you could have more if this list is larger than this, right? So then you have like a fermionic type of statistics where Paul exclusion principle applies, and we call these things transfermions. Or bosonic type, and we call these guys transbosons, and there is no Paul exclusion principle. Now the question is, okay, so far so good. What makes bosons and fermions a particular case in this classification? Well, it turns out is degeneracy, right? So if you if you decompose your Fock space, you have an action of the unitary group. The degeneracy here that appears in the decomposition, it's a signature of some new quantum numbers, of some hidden symmetry. If you say, well, I don't like this because I have no idea where this hidden symmetry is coming from, so I would like to have some statistics where all symmetries of my system of indistinguishable particles are determined by this group, then you will get only ordinary statistics. If you abandon this and say, okay, maybe I can have something more, then you necessarily deal with some hidden symmetries of the system. And this brings me to transtatistics to say this generalized statistics is necessarily occupied with hidden symmetries and new quantum numbers, and what is known, let's say, from the standard textbook physics, that it always leads to some kind of spontaneous symmetry breaking. I'll come back to illustration of what I said. So we said, okay, let's study thermodynamics of ideal gases, and let's compare how this transtatistics is related to Fermi-Dirac or Bose-Einstein distributions and so on. Here are some plots. There you cannot deduce too much from this. But then what it turns out, let's say if you calculate thermodynamical quantities, it turns out you can do in simplest case of this transtatistics, in the very simplest case, if you do a shift of the chemical potential by this Boltzmann factor up to log Q, where Q defines a type of statistics, then almost all thermodynamical quantities remain the same, apart from entropy, which has a residual entropy at temperature 0, which is a signature of spontaneous symmetry breaking, and degeneracies at temperature 0. This is one of the artifacts, for example, how you can see you can see this in the context of the thermodynamics of ideal gases. Good. With this, I'm slowly coming to the end, so I will just bulletize some points of the summary and some outlook for the future. Okay, so what did I say? So I said a few things. I said, well, I'll try to introduce operational setup. How do I do this? Well, I know how to build an interferometer general transformation on D modes, on these states for a single particle. This is the thing. I'm not changing this. Now I start to inject many particles into that. Well, I mean, how, let's say, these phases act on particle numbers locally. That's the most reasonable assumption, right? From there, I put in like a machinery of the representation theory, very difficult problem. That's why I had so many technical stuff on there. What comes out as a solution is the classification that encompasses two known particle statistics type and something else, which we don't know what it is, but still interesting to study. Question is, do we have in our classification the things that I introduced at the beginning, parastatistics, all the other one? The answer is no. Why? Because they always speak of a different symmetry. That's the main point. So somehow our classification is in a unique way paired with a unitary group of a single particle unitary group. We were not able to identify any other meaningful way to go beyond our classification. For example, parastatistics is not there, once or something like this. It's a different symmetry. This is what I said, that our statistics is one-to-one correspondence with a unitary transformation. What makes ordinary statistics special in this classification? Well, no hidden symmetries. If I insist on irreducibility, it's not a strong assumption, but that's let's say that's the description, could be used as a description of the ordinary statistics. What are the comments for the outlook? Why is this what we found physical or not physical? I cannot speculate on this, I don't really know. Could it be that it violates no signaling? It could be. Could it be that I can save this with some super selection rules for fermions? Might be, I don't really know, right? So it could be that this is somehow inconsistent with some basic laws, or maybe it's not. What is very interesting, what we found is really beautiful math. So it's like Nicholas is a true master of finding equivalent formulations to end up with something that particle statistics is related to positive sequences. You will never guess this from the beginning. I introduced some relation to thermodynamics to see like some artifacts that comes from this classification in the context of thermodynamics. Interestingly, we found also, at least in the thermodynamic context, one solution that corresponds to Maxwell-Boltzmann distribution, classical type of statistics. However, that's only in TD context. If you go to representation, this doesn't make any sense. But it appears as a solution, which is very interesting, so I don't know why. This might be used, so you know that, for example, many body Hamiltonians can be diagonalized by a Jordan-Wigner transformation, transforming this to free fermions. Now, I have something new here, which might be used in the similar context, maybe to discover novel integrable models. And then I would like to point out also quantum computing perspective. You have these three things, so for intermediate models. For example, we know that boson sampling, so bosonic linear optics, is very hard to simulate on a classical computer, right? As a matter of the fact, this was one of the first demonstrations of the genuine quantum computational supremacy by the Janeway Pans group. So bosons are hard to simulate. On the other hand, fermions are easy. This is match gate computation. So fermionic linear optics, that's easy to simulate. Now, the question is, if I put our statistic in this context, that would be still interesting to answer what can potentially come out from here in the context of quantum computing. So with this, I'm coming to the end. I would like also again to thank Nicolas for the great work he has done here, and thank you for your attention.
Just a tiny curiosity question. Well, first of all, thank you for the talk. I really enjoyed this, how you built up this narrative of sort of starting from the measurement and trying to come to the same conclusion of these particle statistics. This measurement, if it's this tuple of how many observations you make in each port or whatever, can you do you have is order important? Like if I have, I don't know, that I see 1001 or 1010, do you distinguish those two situations?
No.
Okay.
So in our case, the order is unimportant and likely should not be important.
So then you have this relationship with the permutation group as well, right?
You do, but in a very different context.
So where am I coming from? I know nothing about particles, right? But in, let's say, quantum information, there is this, the symmetric subspace thing is a representation for both the symmetric group, the unitary group and the permutation group.
Yes.
And then you get this whole Schur-Weil duality business.
Yes.
Did you guys try that?
We did, Nicolas, where are you? So just, yeah. So we did, so as the matter of the fact, so entire business of the EREPs, how you build them, so it's very much related to the representation of the permutation group. That's why you have Young diagrams and so on. But now, from there, you have to build up really it's different if you are dealing with a UD group or SOD group. Things can get different. Or quaternionic group. For example, these ansatz could be used to try to build up a quaternionic quantum field theory, which never existed before. But there are technical issues there, right? So it is, and also be aware, let's say what we are speaking here is D modes, permutation of D modes, while normally in the first quantization when people speak of the permutation of particles, they mean permutation of N particles. Permutation of modes versus permutation of particles. One should not confuse the two things. Okay.
Owen?
Okay. So yeah, just on this question of the D modes or the unitary group, does this mean that you effectively have a different theory or a different class of theories for each dimensionality that each single particle dimensionality that you're...
No, because somehow the way you decompose the Fock space, it's kind of independent of the number of the modes. However, interestingly enough, this happens only for this group here. If you put a quaternionic group, right, Nicolas? If you put a quaternionic group, then it would be dimension dependent. So the things could change from dimension to dimension. So it's so this one, I would say, has sufficiently good properties.
Yeah, thanks also for the very interesting talk. So physically, if I, for example, take two fermions together, they form again a boson. So I could say the composite has a bosonic relation. Is such a, let's say, composition structure also true for these parastatistics? And if not, could that be a criterion to say why these are physically not realized in a sense?
It's a tricky question. I have to say I never understood very well what does it really mean. One has to be very careful in saying two fermions, they form a boson. What does this really mean?
Yes, it's not.
And that first time, it's not clear in my head what does this really mean. That's point number one. Point number two, no, I don't know in this case how that would. But it's a good point.
Chris?
Thank you. Again, I enjoyed that very much. Just a suggestion, really. You gave an argument from quantum field theory as one of your standard accounts of where the Bose-Fermi alternative came from. You said, well, it's a bit ad hoc. I suggest you might want to look at some of the literature on superselection theory in quantum field theory, which might bear on what you say at the end, because there is this very deep Doppler-Haag-Roberts analysis of superselection for general quantum field theories. And as far as I remember, in there, a Bose-Fermi alternative came out. I was trying to look it up during your talk, but at the end your talk was too interesting, so
Thank you. Yes, that's true. As I said, we are just at the beginning of this. And however, I think you cannot disqualify completely some other generalized statistics on superselection. I think there is a superselection for parastatistics. Maybe even by Green or some other people.
They talk about that. So they give a general classification, and of course what they do is for quantum field theory, and I'm not trying to say...
You're not talking about the specific, but if you say quantum fields, does it really mean either bosonic or fermionic field? I mean,
So they have you start from the algebra of observables, and this is something where you would expect commutation at space-like separation, and then you try to work out from the representations of this theory what might lie behind it in terms of unobservable fields, and then what statistics they might have, whether there might be some unobservable Fermi fields, for example, or parastatistics. And as far as I remember, they find some parastatistics in low dimensions as a possibility. But I think it would be complementary to your viewpoint.
Are there more questions? If not, thanks.
Logical propositions. So most of the
this is just a sheet of that's the tree. So that's how
like the historic version. But I know that this was so
Something happened.
So are we going to
imagine that's why we need this level of measure. But I have this list like let's that's why I have snakes here like no, go back to where it was first time.
I mean, for sure there is some provided you have to preset the kind of project there's half of things positions make sense.
Anyone who just came for his talk.
And then still
It's automatic. Basically,
They automatically does this. So, for the question. Slow zoom, fast zoom, very difficult, and it will going for 2 days. And everything is recorded.
did you
The microphone. We said the first things we learned.
Okay, so welcome back to the afternoon session. And so we'll start again now. We have the first talk by Olival Freire, who will talk about Bell's theorem and the scientists who worked on it. Stage is yours.
So, first of all, thank you very much to the organizers for the invitation for this nice conference. As you know, my paper is more historically oriented, and evidently it is about the history of Bell's theorem. Anyway, if one person is going to write the full history of Bell's theorem in this extension of 6 years, I think that it's clear that we need to divide at least in 2 different stages. The last one, you know well in this audience, it began in the early 1990s. It was the time where there was available a new source of entangled photons, parametric down conversion. It was also the time where uses of entangled photons for cryptography began to rise. And in 1994, 1995, the term quantum information became, I would say, the label of a huge flourishing and hugely a new field of research. It was a field of research with a mixture from foundations of quantum mechanics, quantum optics, science, computer science, and so on. So, my talk is not about this last stage, this second stage. It's about the first stage, the first 20 to 30 years from 1964, 65 to the late 80s. And the historical question I want to address is that why a scientific result like Bell's theorem, scientific result which is on the basis of this so influential field of research nowadays, quantum information, quantum computer, quantum technologies, and even a result which led a number of important prizes, Bohr Medal, Wolf Prize, Nobel Prize. So, why, at the beginning, this result was so poorly, badly received by the community of the physicists? Or, in other words, why there was kind of a late understanding of Bell's theorem. and even why there was kind of a survival of misunderstanding about the meaning and the implications of Bell theorem. So this is my focus. Why this happened? When I began to work on this, the main hint came from a paper by John Clauser, 2003. I think it was the first time, as far as I know, that somebody wrote about the stigma against hidden variables in quantum mechanics. Evidently, there was a debate on hidden variables in the 30s, homogeneous proof, but Clauser was not speaking about this old issue related to hidden variable. He was speaking for sure from about his own experience as a physicist working on this field. When I saw this, this seemed to me a very plausible explanation, because in my doctoral work, I had worked on the reception of David Bohm's proposal of causal interpretation from 1952, and the main book of my doctoral dissertation was to analyze why David Bohm's idea was so poorly received in the 50s. Then I was a little bit familiar with the idea that there was a kind of prejudice, a bias against hidden variables. And I had a second hint about how plausible Clauser's statement was. I teach in a physics institute. My graduate studies are in history of physics. My research is in history of physics. But I live surrounded by physicists. And when my doctoral dissertation appeared, I could, second question, David Bohm lived in Brazil for 4 years in the early 1990s, and my doctoral dissertation was in the University of São Paulo. And a number of people who were alive had lived with David Bohm. Anyway, a number of colleagues just said, why to dedicate a doctoral dissertation on Bohm's ideas? These are dead. These are something without future. So, with this introduction, this is the outline of my talk. The first two talks is exactly about the early reception of Bell's theorem. And next, I will do, if I have time, what I promised in the abstract. A draft of a portrait, a collective portrait of the physicists who first realized the importance of Bell's theorem. And if I have time, I talk a little bit, very quickly, about the last three talks, just short sentences. So, we had this hint from Clauser, 2003. Now, what I'm doing now is to show you what I found during my research. This means that as a historian of physics, even if Clauser's suggestion was very plausible, I did not take it for granted. As a historian, you cannot take for granted what an actor, a historical actor, say for you. If you are going to write a biography of Nicolas Gitton, don't trust on everything he will speak about his past. Don't trust about personal history. Take this history as a source for your historical research, but try to check these oral histories, this oral testimony against other information. That's what I did. And what I'm doing now is to present some of the evidences I have found about this. Probably the oldest one it's very interesting because it's a letter Bell received in 1996. As you remember, at that time, he was a very influential high-energy physicist at the CERN. And the guy who wrote to him, at that time, he was considered the philosophical defender of Niels Bohr's tradition. He was in Copenhagen at that time, at Gitton, and he was this guy. So what he wrote to Bell? I quote, I need not tell you that I regard your hunting hidden parameters as a waste of your talent. I don't know either whether you should be glad or sorry for that. It would have been nice if the Nobel Prize Committee in their report, cited this. Yeah. So it was a waste of talent that eventually, unfortunately, Bell could not survive to see this and led to a Nobel Prize. And you see, Rosenfeld was perfectly aware of Bell's work on hidden parameters, which means that he had read the two papers, or at least one of the two papers Bell had published. And from the, I never was able to check if he read the two papers, but from the hunting hidden parameters, I think that he had read the two papers, not only the review of modern physics papers, which is a review. Now, Bell was very aware of this problem, because, and here I did not follow Bell later recollection that in 1952 I saw the impossible dawn. Everybody here knows this quotation. I was very happy when I discovered a paper published by Bell and Neuenberg in 1966, which means the same year he had published, 1 year after he had published the paper in physics, and then the paper in Reviews of Modern Physics, and the same year he had received this letter from Rosenfeld. So what he said, I quote, we emphasize not only that our view that quantum mechanics is at the best incomplete is that of a minority, but also that current interest in such questions is small. The typical physicist feels that they have only been answered, and that he will fully understand just how error is think about it. My comment. In addition to be a very strong statement published in this book in honor to Victor Vaskov, you say Bell is not speaking only about hidden variables here. He is speaking that the majority of physicists are not interested in discussions about foundations of quantum mechanics. That's the question. While the first letter is limited to hidden variables, here it's a larger statement. And they appeal for the scientific authority of Vaskov in the same text to cite this. It's a pleasure for us to dedicate the paper to Professor Vaskov, for whom intense interest in the latest developments of detail has not duly concerned with fundamentals. Okay, this is Bell, 1996. 10 years later, 1975, we have another evidence about this awareness of Bell. It's a testimony from Alain Spey, but Neuenberg also confirmed to me the same story. And the story is that it is well known because Spey had said this many times. The first meeting he had with Bell asked him, do you have a permanent position? And it happened that Spey had at the École Normale Supérieure Technique de Castres. And after his positive answer, Bell encouraged and urged him to publish the idea. This is very important because you remember Spey published in 1976 a paper announcing he will make this experiment with the variable analyzers. And it took 4 to 5 years to finish the experiments. But Bell warned the aspect that all this was considered by a majority of physicists as a subject for crackpots. Now, as I remarked, the text by Bell and Neuenberg is not limited to hidden variables. It's related to a kind of a bias against the realization foundations of quantum mechanics. A bias in the sense that physicists consider that these were solved problems. So, this bias against the subject on foundations of quantum mechanics was related to the idea that these problems were already solved. Then we have here another topic. What is the topic? It's not the pragmatical attitude to say there are problems in foundations, but we are not discussing these problems. Let's go ahead and let's, for instance, in the tests, I can understand, let's try to understand what is the nuclear physics, something like that. So the kind of attitude towards the foundation of quantum mechanics, which was a dogmatic attitude, this attitude is still Rosenfeld, but I couldn't find any other evidence. I have a limited time here. I only brought this one. It's a letter to Gilles Brassard, who wrote a book about hidden variables in 1972. And Rosenfeld said not only it's too tight to speak of two Copenhagen schools, but it is even wrong to speak of one Copenhagen school. There has never been any such thing, and I hope there will never be. The only distinction is between physicists who understand quantum mechanics and those who do not. This idea that there was a bias against debates on foundations, we can find a number of different evidence. I will just bring a few more evidence. This is a letter published in Physics Today by Michael Hammer. When Physics Today published a paper by Brice DeWitt on the problem of the interpretation of quantum mechanics. When Brice DeWitt presented his support to the many worlds interpretation. So what is important here in this letter? He said, when I was an undergraduate reading physics 20 years ago, thus 1951, the Copenhagen line was scientific. Anything else was meaningless, mumbo-jumbo, or at best a mistake. Now the curious thing is that, as far as I am aware, there has been no major field of theoretical insights that could be held to demolish or supersede this interpretation. Nevertheless, there is now considerable satisfaction with it and a willingness to regard other forms of figures, for instance, hidden variables, as being at least respectable. Now, what I cite now is not exactly an evidence of bias, but evidence of your late understanding or a misunderstanding. So, take July 1969. This conference was held in Cambridge. It was dedicated to foundations of quantum mechanics, the title, Quantum Theory and Beyond, organized by Ted Basson and Bohm. And the attendants were Aharonov, Bob, Bunge, Grunewald, Riley, Peterson, and others. The important, none of them cited Bell's work. At that time, when I didn't have this on PDF to check, so I read each page of this book to see if the Bell's name appeared in the book. We know now that one person who was invited to the conference, Henry Stapp, he had circulated a preprint, but this preprint was not published. And in this preprint, Stapp cited Bell's theory, and Stapp realized that there was no available experimental results to check Bell's inequalities.
Was that a place where he said it is the most profound discovery of science or something like that? I mean, it wasn't a staff we once said that.
Yes.
Was it there?
Was, exactly. Exactly.
And it did not make it to the proceedings.
Yes. He did not go to the conference. That's the problem. Yeah, but the proceedings was not a proceeding in the strict sense. If you were the editor of this volume, you would invite staff to publish the paper about that. The problem, I may offer other evidence. At the same time, Bob and Bob had just finished his doctoral dissertation, and they knew the second paper by Bell, the Reviews of Modern Physics, but they did not know the paper with the theorem. This is a testimony from Jeffrey Bartlett. So no reaction to Bell's theorem came from exactly what it would be expected. The partisans of hidden variables, such as David Bohm and Louis de Broglie. After that, there was a positive reaction, a very positive reaction from David Bohm, but it was later. And I said this with profound respect for David Bohm. I wrote a biography of David Bohm, but it's clear that in 1969, Bohm did not realize how important Bell's theorem was. Immediately, 2-3 years later, he understood and he changed his mind, and he wrote a paper with Basil High in 1974 saying that non-locality was the most profound quantum physics feature. Now, if you take the group of the supporters of hidden variables, they had different attitudes. I spoke a little bit about Bohm and Bob, but if you take de Broglie and collaborators, you had a kind of a split among them. Jean-Pierre Vigier immediately understood the question, but others who were more loyal to de Broglie, as Georges Lochac, still maintained 1978. Bell's attempts, as interesting as it is, does not say and cannot say anything decisive about the existence of hidden variables, local or non-local. And sorry, Gilles, I need to make a small provocation. He wrote this. He was not defending a variant of many words interpretation. This was just because Lochac did not understand anything about Bell's theorem. If you check, for instance, the epistemological letters, a publication of the time, there was an important debate among Louis de Broglie, Bell, Armin Tavakoli, and Lochac. And it is clear in this experience that Lochac and de Broglie did not understand what was Bell's theorem about. As I said, at that time, in 1974, Bohm and Basil Hiley had realized the full implications of Bell's theorem. Now, just a little piece about the survival of objections. Let's take a minor statement against a hidden variable. A minor compared to Rosenfeld's statement. So you take this very influential textbook, Quantum Mechanics, what we find over there, the controversy on hidden variables has finally reached a point where it can no longer be decided by any further experimental observation. It henceforth belongs to the philosophy of science, rather than to the domain of physical science. The last edition I checked on this, from this textbook is from 1974, without a revision on this topic, as far as I know. Okay, maybe you may say you are being too strict because maybe he had not time to revise the book. It's possible, I don't know. The fact is that a book published in 1974 without one word about the Bell theory and one word about the experiments at that time, 1974, the last edition, we had two conflicting results. of the theory. The minimum you can say is that Messier was not careful with the revision of his book. Now, it's not a question of omission. No? Abraham Pais, this very physicist who became a historian of physics, he wrote this wonderful Einstein's biography, Soto is the Lord, 1982. He stated that the EPR paper, he was writing about the EPR, 1982, the EPR paper had no bearing on physics and did not cite Bell's theorem as a development of this issue. Okay, but you see, physicists were being formed under this tradition because the undergraduate in physics, they do not read original papers, all original papers, but they read this very good, very influential biography. Now, the second part of the same problem. If there was a stigma, if there was a bias, there were victims of this bias. And in my book, The Quantum Incidents, I discuss a number of these victims. They were not few. Some very poor known as physicists, like Taussky, a Brazilian physicist, or as Jensen, not Jensen, Zé, or Everett. I could give another talk about these other guys, but as they are not directly related to hidden variables, I left aside. But the case I am taking, it's a conspicuous case because Clauser was, by any standard, an outstanding American physicist. It's not because he won the Nobel Prize. Nowadays, to speak about Clauser is a problem for us. You probably know. Every time I talk about this, somebody in the audience, oh, this is the guy who is against the climate change. And you need to explain how complex science is. What I am saying is that Clauser was a student of Patrick Tadeus at Columbia. Clauser made experiments on the cosmic background radiation. Clauser who wrote the CHSCH paper. He made the first experiments on Bell's theorem. He got involved with the debate about new classical electrodynamics. It's a very important talk in 1974. And he did a second experiment because there was a dispute. I do not have time to enter in detail. He went to redo Holt experiment. And he wrote the most influential review papers on this subject in 1978 with Shimon. So, by any standard, he would be a good person to be contracted by an American university. He was not. I know that 1970 it was the time of the job crisis in the American university. It was not an easy time. But anyway, he was a very good candidate. And here I have two parts. First, because he never got a permanent job. If you check the Nobel Prize citation, it's his personal address. Because, because he has no institutional address. He made a life because in American physics, when you made an application and you won the application, you put a salary on the application. That's how Clauser made his life. But the evidence I found is that some of the restrictions to Clauser were due to his engagement with hidden variables. The most important is that 1972, Shimon was in France, and Armin Shimon was in France, and he met Bernard Espagnat, that for some reason was very engaged with the subject, and Shimon wrote to Clauser this. When I saw the Espagnat last week, he had a letter from the department chairman at San Jose. As you well know, the money to hire people in the American Academy, the recommendation letter are the most important part. So, what was the question? the chairman was inquiring whether what you have been doing is real physics. I do not need to read the end. 1972, a head of a physics department in the United States had doubts if what Clauser was doing was physics. I have other letters. 1 year before, another letter from Shimon to Clauser, where Shimon tried to bring Clauser to the Boston University, and he did not succeed. Now, about Clauser, we have other evidence about the difficulties we had. One of the difficulties is our guru, Feynman. Clauser said, when he wrote this, that while he was performing the first experimental test of the CHSH prediction as a postdoc, he went to talk to Richard Feynman. Feynman was very impassive with him, and Feynman's position was, quoted, I quote from Clauser, well, when you have found an error in quantum series, experimental predictions come back there, and we can discuss your problem with it. Okay. Now, in defense of Feynman, I had a testimony that in 1974, as early as 1974, to another guy who was doing a test with Bell experiments, Ed Fry, Fry reported that he had a very positive reaction. And later, 1983-84, Aspect visited California, and Feynman openly acknowledged the relevance of Aspect experiments. Now, it's about you, Joseph. The interview you gave to me, this is the source. Bell theory also faced what we call friend fire among those working on foundations of quantum mechanics. You need to understand that the first people with whom Bell worked on this subject was with Jauch and Piron. Piron or Piron? How do you pronounce?
Piron, yes.
Piron. Because Jauch and Piron were working to reinforce von Neumann's proof. That's how Bell came back to this subject. Studying seminars by Jauch and Piron, and Bell was convinced that the approach by Jauch and Piron was not enough. As a matter of fact, Piron got upset with the success Bell obtained with these papers and reacted badly. Gitton, on the contrary, at the time, it was a very young physicist here.
Piron was my PhD advisor. It was not easy to go against.
Okay. You see. And Gitton was always fascinated by Bell's papers. It was with him that I first listened this information that after I saw in other piece, that Bell opened a talk here in Switzerland saying, I'm a quantum engineer, but on Sundays I have principle. Now, the problem is that Bell's theorem was a taboo subject in Piron's theorem. And when Gitton came back from the United States to here, he was not well accepted in Piron's work group, and he just needed to make a different way to be here today with you working on foundation of quantum mechanics. Now, just quickly about the physicists who first understood the importance of Bell's theorem. I think that it's impossible not to be emphatic about the role played by these four guys, the CHSH paper, but I would say especially about Clauser and Shimon, because Clauser and Shimon, they had independently arrived at the conclusion that Bell papers was a very important paper, and they arrived at the same conclusion that there was no experimental evidence to check those inequalities. And they decided to collaborate instead of compete. Then, Michael Horn was a student of Shimon, and Holt is very important because he was not a student of this. Holt entered in this story because Shimon looked for Papaliolius at Harvard to make different experiments that could check Bell's inequalities. Papaliolius did not work on the subject, but suggested that Holt, who was a student of Kant, could deal with this. And that's how Holt entered in this story. So, a lesson for young physicists. Holt entered in this story, but Holt is the guy with his advisor who did one of the two first experimental tests with Bell's inequalities, and he arrived as a result that quantum mechanics was violated. They were not convinced that the results were correct, and they were not convinced that it was wrong. That's the worst situation. You have a result, you don't trust enough to publish, and you are not aware, or you don't think it's the case to abandon. So, Holt had his PhD dissertation at Harvard. Nowadays, he works in Canada. And the results circulated as a preprint, but it was never published. Anyway, these were the most influential physicists, and it's important to see that the place where Bell's theory was better received, it was in the United States, because this was Cambridge, Boston University, Harvard, Columbia, Berkeley. Now, it's important to say that when you have this controversial topic, to have people who are senior are very important if they support you. I do not have time to enter into details, but these three were very important to support the physicists who were working on this. On the left, we have Wheeler and Wigner. Wheeler, you know very well the book here you published with Zurich in a manner to collect all papers and on foundation of quantum mechanics and the quantum. I am speaking about the quantum measurement book. We have other evidence of Wheeler. But Wheeler is a very special case. I do not have time to discuss. But Wigner was very important because he was always supportive of Armin Shimon's engagement. Either with the measurement problem, a problem Wigner was very interested, or the Bell theory. And Bernard Espagnol. Bernard Espagnol was not so old as the other, but he was very influential because he was the director of the first great major meeting dedicated to foundation of quantum mechanics. It was organized in Varena by the Italian Physical Society, dedicated to foundations of quantum mechanics. You have here a bunch of young physicists, a little bit like this audience here. And here you have Bell and Wigner. Wigner is the only one with a tie. And the history of this conference is very interesting. I wrote something about this. Flavio too. Indeed, we became friends when the first time I received his paper about this subject. And this was a very important conference. I called this conference the Woodstock of the quantum dissidents. And the director was D'Espagnat, and D'Espagnat invited Bell, invited Shimon, and this was the first time that Bell's theorem was openly discussed in the scientific community. So, if I made a list of the first people who worked on Bell's theorem, they are this. we need to add Friedman, Frey, I told, Thompson, Stappen. They were supported also by Towns, who was the advisor of Clauser at Berkeley. Then they were followed by Alain Aspect, and later by Darling, Schied, Zahn. And we also need to say that Bell's theorem was discussed by Seller, Paty, Bon, Hailey, and the other people at that time. These are the people I have called the quantum dissidents. Now, why this name, quantum dissidents? If I try to understand what were the common ground among these people, you do not find easily one feature which was common among them. If you take, they were interested in foundations, many of them, but not all of them. They were skeptical, critical of the solutions the complementarity interpretation offered. Many of them were critical, but not all of them. For instance, if you take here Alain Aspect, it's unfair to say that Alain Aspect was against complementarity. By contrast, Clauser was always against. Chamonix too. They were interested in crucial experiments and foundations, some of them, not all of them. Good. They were experts in optics, some of them. Now, in my opinion, what were the real common ground among all these people? They were engaged with the idea that there was good physics to be done in foundations of quantum mechanics. And what I call quantum dissidents is only this. They were dissidents not because they were against complementarity. They were dissidents because they were against the dominant view in the physics community that there was no good problem to be solved in foundations of quantum mechanics. Now, let me jump to the other points. It's good to remember that at the beginning, Bell, Clauser, and Horn, they had the expectation that the results would be favorable to hidden variables. You see, there is this letter from Bell to Clauser, 1969. Moreover, there is always this slim chance of an unexpected result which would shake the world. There is another letter from Horn to Clauser, April. Do keep imagining that you come out against quantum theory. That makes it very interesting. If you take letters from Chamonix, he was more cautious. And Chamonix had very good literary skills, as you know. He wrote to Clauser in 1972 when the results he received and he revised the paper by Clauser and Friedman with the results favorable to quantum mechanics, violating Bell's inequalities. He wrote this. Your paper finally arrived today. It is a classic, but unfortunately a classic tragedy, since the hero dies. And he dies now. Now, my lessons from this story. I do not have time to develop these lessons, but I think that they are evident from the things I have talked here. Scientific practice in the most developed science coexists with bias and dogmatism. And if I may tell one lesson for young physicists, and I say this because I know that Flavio is very interested in the role, Gitton too, Aspermeyer also, what history and philosophy of science can help physicists, scientists, young scientists. I would say it's to understand what science is, because you need to be prepared to become a good scientist in this field, and not in an ideal field. So, dissidence in science may play a factor role in scientific development. This is the case. This is the case that an heterodox view led to a very great success. And finally, from my point of view, the most important, tolerance towards heterodox views needs to be reinforced in science, and not Now, I finish with a little joke. It's a suggestion for the historians of the future. And the future dated 2072, when the Nobel Prize will be, the Nobel Archive will open the letters concerning the 2022 prize. It's a very interesting thing. There are some things. First, who were the guys who were nominated to this Nobel Prize? I'm sure that Gitton was one of them. Some others were indicated. So, in Brazil, we had this strong discussion. Why César Lattes did not win the Nobel Prize by the Meson Pi, the Meson Pi. The Meson Pi was so neither him, neither Orchialini. So, who were the guys who were indicated? This is one of the questions. Okay, I jumped just a minute. Because we had strong suggestion that this Nobel Prize was on the piste, on the road, at least 15 years in advance. Because, for instance, the Wolf Prize, if you take the correlation between Wolf Prize and Nobel Prize, it's a strong correlation. So, since 2010, you can say that the Bell's theorem or entanglement was on the road. Now, 3 suggestions, in addition to know who were denominated, who were denominations, who were the nominee, and who were denominated. 3 other questions. Why did it last so long? First, was it a survival of that stigma? Second, was the existence of remaining loopholes to set entanglements as a physical effect? Many people say, and I agree with them, that in 2015 you had, I would say, a kind of almost final conclusion about the closing of these loopholes. But it was 2015, and the Nobel Prize was 2022. What was the competition with other achievements in science? We need to recognize this was the time that general relativity and astrophysics observation and complex system became fashion in physics. But this is not a question for the current historian because we cannot have access to the archive. I finish just saying that all the references I cited are from my book, The Quantum Incidents, and some evidence from David Bohm are in this biography. And just the third one is just a collective work, and I make a little publication. We have over there a paper, a contribution by Flavio on the debates on quantum foundations in Italy. Okay, thank you very much.
Thanks a lot for the very interesting talk. We have time for one quick question because we are out of time. So if there is somebody, yes.
Just a clarification. So I didn't get it. So did de Broglie react to the Bell theorem or not? Because I know of a paper by Bell where he says reply to critics, and I believe he replied to de Broglie as well. So was de Broglie ever reacting to Bell's theorem?
De Broglie reacted, saying that Bell's theory was not so relevant. So it was a bad reaction. Just forgot the name of de Broglie's collaborator, who said it.
Vichy.
No, it was the other.
Japanese guy.
Rorschach. What Rorschach said, you may take as what de Broglie thought.
Okay, so do not leave, but first let's thank our speaker again.
30 seconds, let's listen to John Bell himself with his voice.
So I'm a realist.
I think that idealism is a kind of, I think it's an artificial position which scientists fall into when they discuss the meaning of their subject and they find that they don't know what it means. I think that in actual daily practice, all scientists are realists. They believe the word is really there, that it is not a creation of their mind. They feel that there are things there to be discovered, not a word to be invented, but a word to be discovered. So I think that realism is a natural position for a scientist. And in this debate about the meaning of quantum mechanics, I do not know of any good arguments against realism.
So now, break.
Fully steeped in it for the first time. We'll see how I come out of the experience. Is there anything else I want to say? Yes, my name is Max Lock. As said, I'm based at TU Wien, also affiliated with IQOQI Vienna. And this is work mostly based on this paper up here with collaborators Manuel Schwarz, Hans Felix Binder, and Markus Huber. But I will talk a little bit about some things from this second paper here. So, what's the sort of qualitative picture we have of quantum measurements, right? There's this sort of quantum world over on one side, where things are sort of fuzzy and indeterminate, and one has a lot of arguments about whether things are non-local or real, or some very subtle version of non-local and real that allows you to sidestep Bell's inequalities. But then at some point, you show your classical measurement apparatus, and then we arrive at something that may or may not be objective reality, depending on who you ask. So there are a lot of problems that are described with this. As Trashlab very nicely described in this paper here. One of which you might hear often is how is a particular measurement outcome chosen? This is a very difficult one. I don't really know how to formulate this as a physical question. Your opinion may differ on that. Another one can ask about this is how do we choose which situation should be modeled by, for example, a unitary process, and which by measurements? And I think this is, for me, is a much more well-defined question. So Kastler formulated this very nicely as if you have an optical table and you insert some element into your optical table, into the path of your beam, how should you decide whether or not, when you're modeling this mathematically, that this should be some unitary operator or a projector? This really is the question, what is a measurement? What defines a measurement? So on top of that, we have the problems that Marcus described in his talk before, namely that, at least if you take it very naively, a projective measurement breaks all three laws of thermodynamics. I mean, I probably don't need to go through these, but I mean, it's clear. The average energy has changed. You can have an arbitrary von Neumann entropy, go to a von Neumann entropy of 0, and whatever outcome you get is some finite amount of rotation away from the ground state. And there's this very cute quote by Arthur Eddington, who famously demonstrated Einstein's general relativity for the first time, saying that effectively, if someone points out to you that your pet theory is in disagreement with the second law of thermodynamics, it's doomed to collapse into deepest humiliation. But I mean, so quantum mechanics has collapsed into deepest humiliation, right? Right? No, of course not. So why not? So why not? Well, this story that I told you is clearly a fiction. I mean, this projection here, I don't think anybody really believes in it as it stands without some kind of extra mechanism, without some kind of extra philosophical baggage at the very, very least. But one solution that one might take, and indeed that was taken by, I keep trying to, that was taken by von Neumann, before the ink was dry on quantum mechanics, to say, okay, well, what is a measurement process? It's you couple to some kind of probe, you perform some kind of carefully controlled unitary interaction, and now your probe will be correlated with the system of interest in such a way that those measurement statistics are now encoded in those degrees of freedom instead. One issue with this is that it requires a timed interaction and therefore doesn't conserve energy. But another issue, this isn't really enough, right? This is now I have, let's say, one qubit and I've coupled it to, say, some other qubit. It's not yet a measurement. What we need to do is somehow to take this information and multiply it and spread it out throughout the world, such that it's accessible. And so you can consider this sort of measurement chain, so to speak. So first of all, coupling to some probe system. If we want to be concrete about this, let's say it's your silver atom, it's spin half. You put it through some inhomogeneous magnetic field and couple it to the momentum degrees of freedom.
Only one question. So in what sense is that a solution, what von Neumann did?
Oh, to the issue of the, sorry, this is responding very strangely. To the issue of the breaking of the laws of thermodynamics. One might hope that one can couple that this comes from pretending that you're not doing anything to the system, but in fact you are intervening on the system by coupling something to it. So perhaps you can solve these problems by considering the total picture, and then asking the same thermodynamic questions of that total picture. But yes, so if you want to really, turn this into something that's multiplying this information up to a scale that's genuinely accessible to us, you have your spin half coupling with your momentum degrees of freedom through your magnetic field, say, and then this is hitting some detector and initiating some kind of cascade of electrical energy within that, which goes on and so on and so on and so on through the wires, through the cables, all the way until you get to me being maybe sad because Schrödinger killed my cat, to prove some kind of point about metaphysics, or happy because it survived his sort of perverse experiments. This picture is, again, I'm clearly, going a little too far with this, unless you're a many worlds theorist, full on. In my case, I'm going exactly as far as one should. But this 10 to the 27 here, why this? Because I'm using approximately the number of particles in my body as a standard for the degrees of freedom necessary here, right? And what I'm effectively doing, if I say that I can do this, is I'm allowing myself a Maxwell's demon. I'm allowing myself to the many amounts of very well-timed control in order to make all these things happen such that I'm either happy or sad. So, there's a less stringent requirement in this idea of the multiplication of information, and that's quantum Darwinism. And there, you consider some system and some environment that it's coupled with, and you instead make the demand that instead of demanding this controlled interaction with every single individual piece, you say, I want this information to be spread out redundantly throughout the environment, such that whenever I consider some fraction of my environment, I very, very quickly reach this so-called classical plateau, where I have all of the information really about my system, on a measurement basis, and then getting more pieces of the environment doesn't really tell me anything more about the system. So this is supposed to somehow capture the idea of quantum information going from classical to quantum, that's right, other way around, quantum to classical, excuse me, where classical means redundantly encoded in the world somehow. But this is a property of states. It's not dynamics, right? It's not a dynamical model of measurement. And one also crucial fact that we observe that it doesn't explain is the objectivity of outcomes. That is to say, if you say the spin was up, for you the spin was up for me too. There's no any disagreement that we have there comes from some noise in the discussion between us rather than some fundamental statement about the world. Yes?
This figure, why does it, after being flat, pick up again?
That is a very good question to which I don't know the answer. It's been a long time since I did this.
Some point is that I don't get it.
This is to do with the did you put your hand up?
I think the reason is that the mutual information, for example, between the qubit and the rest, will, as long as it's classical, will be 1, and then at some point all the environmental qubits will be in the same state as the qubit you measure, so it will be fully entangled again, and then the mutual information is 2.
Yes, that's of
this
course.
happens at the very end.
This is why this is the classical plateau, of course. This is effectively the extra kind of quantum information you get from the entanglement beyond the classical correlations in the measurement basis. Thank you. So yes, the question of objectivity, although as there are some philosophers in the audience, I should probably use the word intersubjectivity to be more precise. That is to say, we require that a measurement can, or that multiple observers can simultaneously access and independently determine the measurement outcome. They can do so without disturbing the system in the measurement basis, that is. So that if I say the spin is up, and that they will agree when they do that. So if you take these 3 criteria, as the authors of this paper did, and as is very nicely summarized in this review here, this implies a certain structure of your quantum state, where you can effectively describe the Hilbert space of the system you're trying to measure, and then these other systems, which we can call observer systems. For someone who believes in the many worlds interpretation, this is the system of the observer themselves. For someone not, this is simply the part of the world that they have access to. that they will then perform some whatever magic that you do other than that to understand a measurement. Yes, so if you take these three requirements, which in the literature unfortunately is called objectivity, then you're forced into a structure of this form, where it's quite easy to see what this says. It says that with probability I, your system will be in the state I, and then your observer, any given observer system will be in some state also labeled by I, such that the fidelity between two possible outcomes is 0. So in a more sort of quantum information language, we would say in a state discrimination game, you can perfectly distinguish between these two states. If you have a structure of this form, this implies quantum Darwinism, and is equivalent to a slightly stronger form of quantum Darwinism, but I won't go into that. But I mean, again, this is something about the state space. I'm making a statement about the state space. It is not a dynamical model that shows how we go from an initial state where you have a quantum superposition to somehow objective facts that we can interrogate and do so redundantly, and do that in a way which is spontaneous and irreversible and doesn't require the microscopic control of all of the constituents. On top of that, there's an intuition that we can, if we're asking the question, what is a measurement, there's an intuition we can bring that I haven't discussed yet, which is that not every system is an observer, of course. If I have a qubit interacting with a qubit, it's clearly not an observer. But if Marcus Huber looks at the qubit, he's definitely an observer in that circumstance, you know? So I can kind of summarize what I've said so far in these desiderata. What I want from a model of measurement is that it doesn't violate thermodynamics. I want that observation is only induced by large systems where the question of what constitutes a large system is something we can debate. And thirdly, that the relevant information is going to spread out in this kind of redundant and hopefully objective way in a manner that is spontaneous, irreversible, and doesn't require a kind of absolute control. So, sorry.
So I don't want to break the flow, so if it's not what's your definition of like Marcus Huber in the sense that when is it clear for you when you when does it count and when it doesn't count?
That is actually that is a brilliant question, and I will come to a version of that answer in a toy model later. For now, let's just let that be the quotation marks. So I have these desiderata, right? And you'll be entirely unsurprised from the title of the talk when I say that if we think about equilibration, of which thermalization is one example, then you can see that this, of course, if the measurement process is going to arise from equilibration, there'll be no violation of the thermodynamics. It's only going to be induced by large systems. And the dynamics will be spontaneous, irreversible, and won't require exact control. Although there's one part I haven't put a thumb yet, which is, of course, that the relevant information spreads out. And this is the key part, and this is what we'll come to in a second. Before that, I was discussing with Marcus this idea of the entropy, that the measurement process, the hypothesis that the measurement process necessarily is an increase in entropy, a tendency of the universe towards equilibrium. We discussed why there are numerous examples of people talking about this in the literature, but it doesn't seem to feature in any of the conversations that people have about measurements and what they are. And so we thought, how do we make this stick in people's minds? And we hope that by giving it a name, hopefully then there's something to point to, and it won't just keep forgetting, as it does every time it comes up through history. So, as I say here, measurements, the idea of measurement corresponding to an increase in entropy is a very old idea, a very, very old idea. In fact, those of you familiar with the Szilard engine, this is used as a sort of primitive Maxwell's demon, and it is. But the purpose of the paper was to demonstrate that a measurement must increase the entropy of the universe, which is something that when we now teach the Szilard engine as a tool, as a primitive for Maxwell's demon, this part of it was at least discussed in a murky way. So let me maybe try to be a little bit more precise about what I mean in this, at least in this context. What I mean is that measurement is an entropy increasing transition from a system potentially in superposition, uncorrelated with its environment, to a region of the state space, which is commensurate with probes or observers or whatever interpretation you like, finding a well-defined outcome for the system in an objective manner. So we have a closed system and we have this hypothesis. It naturally leads to two questions, right? How can an isolated quantum system equilibrate? And how can unitary evolution increase entropy? And the answer is given by a field of research called equilibration on average or equilibration of observables. And this review here is a very, very nice summary of a lot of work up to that point on the topic, to the point where in our group we sometimes refer to it as the Old Testament. Tim?
Can you just explain the standard statement of the measurement problem is how do you get an actual outcome? Like how does the cat end up either definitely alive or definitely dead? If the fundamental dynamics is linear, A, the wave function is complete. And the answer is you can't. That was Schrodinger's point.
Okay.
So are you, which one of those are you denying? Are you denying the linearity of the fundamental evolution, or are you
I believe the first line was that I'm not addressing exactly that question. I am a skeptic. I don't know. The issue I have is that I'm very pedestrian. Like,
address the measurement problem without addressing the problem that Schrodinger raised.
Did I say I was addressing the measurement problem?
I don't know. I'm trying to understand what problem you are addressing.
I'm trying to understand. I'm trying to.
Maybe put this is, what is the information that's supposed to be broadcast? It's not the information, oh, the cat's alive or the cat's dead. Is that the information that's supposed to be broadcast?
Now we're going to have a conversation about what information means. But
sure, you're using it. I mean, you have it on your slide. Tell me what's the relevant information.
What is the relevant information?
What is the relevant information?
Let me define it this way. Information is correlation. I don't think that's going to satisfy you, but when I say the word information, if you could replace that in your mind with correlation, then maybe you'll be able to follow with less.
That actually occurs.
What is actually occurring? What is real?
What actually occur means I don't know how to have a conversation at all.
What I'm going to try to lead to, if I get there, is an idea of measurements arising kind of in the thermodynamic limit, in a sense, as an effective description of the world. And that's not the same thing as saying that the outcomes don't really occur, because emergent phenomena are still real. If I fall out of an airplane above the ocean, I'm not going to be thinking on the way down, it's all right, surface tension is an effective description, right? So we can have an argument about what reality means, but maybe we should do that at the end, if you don't mind.
Question about cats.
Okay, where was I? Yes. So, closed system equilibration on average. So what does it mean for an isolated system, quantum system, to equilibrate? Well, the first time someone told me an isolated quantum system equilibrates, I thought this was kind of crazy. It doesn't make any sense, right? You have unitary evolution, you can kind of see its rotations in this very high-dimensional space. So how does a rotating sphere come to rest without friction, you know? But then the idea of equilibration on average is really about the equilibration of particular observables. And so this is illustrated fairly neatly in this simulation from an upcoming paper with Jake and Flo in the audience there and other collaborators. This is the bulk magnetization in a spin chain, the Ising model. So you have this fairly degenerate collective property of the spin chain, its overall magnetization. And what this shows you is that if you have a relatively few spins, that is to say 5, you start from your initial bulk magnetization, and you continue to fluctuate around a lot. But as you increase the number of spins, you'll find it's maybe not so visible here, but this light blue line very quickly starts exhibiting behavior where it's, for most time, very, very close to this dotted line. And so that's the sense in which I mean equilibration. I mean equilibration on average. I'll make this a little bit more rigorous in a minute. But this might seem strange to you. I'm kind of, after I learned about this, I was amazed that it wasn't more of a thing that we're taught for people who claim to be experts in quantum theory. And it's incredibly well established. There's experiment after experiment after experiment after experiment showing these things. But nonetheless, that doesn't, for example, stop reviewers saying things like the problem is that unitary evolution does not equilibrate no matter how many times one says it does. This reviewer, unfortunately, has been demonstrated incorrect by numerous experiments, practically on a daily basis. So then there's question 2. Which is how can unitary evolution increase entropy? And the question is, what kind of entropy do you mean? If you mean the von Neumann entropy of a system, then of course unitary evolution is not going to increase the entropy. But if you consider constructing the entropy with respect to the observables you actually have access to as a large-scale entity, as a human being doing an experiment, that is to say the bulk observables, then you will find that actually just as with the equilibration of the mean value of this thing, you'll find that it's the Shannon entropy associated with this will, in general, if it starts from a low entropy state, increase to a high entropy state and stay there.
Mats, can I add? So I guess there are many other observables that do not behave so nice. So is there a preference why you choose those that do behave?
So this is the question in some sense, was the question, sort of foundations of statistical physics, say 15 or so years ago, 20 or so years ago. If equilibration occurs for some observables and not some other observables, what is it that determines that? And the answer, very broadly speaking, is degeneracy. And there are good entropic arguments for that. Kind of come to that, but generally speaking, the observables that tend to equilibrate are ones for which there are many microstates that will give the same value. So bulk magnetization is a very nice case of this because, okay, this is the sort of minimum of the bulk magnetization, if you like, and there's only one way that can be the case, all of the spins pointing down. But then, for the values here, where these things equilibrate to, those tend to be in the middle of the bulk magnetization range, where there are many, many different states that correspond to that value of the bulk magnetization. And so that's precisely the way that you can have this incredible hypersphere continue rotating, and yet the value of an observable stay basically constant. And so making that more rigorous, the equilibrium state in this picture is defined by the infinite time average. One way that you can understand this is by making a state that is invariant under any time translations. This is so for those interested in quantum reference frames. This is a group averaging effectively over the generator of time translations. And then what equilibration on average says is that if you have an observable which equilibrates on average, you might as well use this state and not the actual state at a given moment in time for most times. Of course, immediately if you start in a low entropy state, immediately as you start, then this is a bad description of your state, right? But if you allow the clock to run, put all of those moments in a bag, and pick one of them out at random, the state that you're picking out at that moment is on average incredibly close with respect to the values of this observable to the same value you would have got if you had just used the equilibrium state to describe the situation. That's precisely what this inequality is there to show you. This thing here is the difference between the maximum and minimum eigenvalues of the observable. It just sets the effective scale of the thing. And the crucial quantity here is the effective dimension. The effective dimension tells you effectively how much of the state space, what's the dimensionality of the state space that you're going to rotate through in the course of your evolution. So if you start in an energy eigenstate, your effective dimension is 1, because you'll simply accumulate a phase. So yes, another way of saying that is, as I said before, is if you know this is effectively, this proves that on average you'll equilibrate under the right conditions, and this proves that if you equilibrate on average, that is to say this thing is small, the probability of a fluctuation more than a certain quantity is very low. There's another version of this. This doesn't require you to describe the system as a whole. Of course, if whole systems can equilibrate, subsystems can equilibrate too. So there's a version here where now it's not just observables, it's actually a distance measure between the state. So I said entropy maximization. I gave a plot of that, but just to be maximalist about it, this equilibrium state is precisely the state that takes your initial state, sets all of the constants of motion constant, and then maximizes, subject to that constraint, the entropy, the von Neumann entropy now. Furthermore, equilibration is a subset of thermalization. There are many, many equilibrium states that aren't thermal states. Thermal states are the equilibrium states which only have one conserved quantity, namely the energy. Okay. So just really to highlight, the state continues to evolve. There will be states for which, there will be observables for which the equilibrium state is a terrible description of the system. It's not the appropriate way to do this. Only if you consider equilibrating observables. And what are the equilibrating observables? They're the ones that are highly degenerate. And what that somehow captures is the idea that I, as a large ape-sized thing, I'm trying to interact with this incredibly complicated quantum system, and the likelihood of me being able to resolve, let's say, 2 to the n possible quantum states is very, very low. There'll be some coarse graining that I'll have to do in order to describe that. It's precisely the coarse graining of that observable that will lead for it to equilibrate on average. And then there are all sorts of caveats. There's equilibration time, how quickly do you go to the equilibrium state? Degeneracies, I implicitly assumed degenerate Hamiltonians. You have to play around, massage the equations a little bit when there are degeneracies. Of course, recurrences, there is a Poincare recurrence, but just as in the classical systems, for any system of any reasonable complexity, this is going to be something like the age of the universe. And then there's the need for the large effective dimension. Okay, so that was a foray into quantum statistical mechanics. So when we say that a measurement occurs as a consequence of equilibration, what we're really saying is you start in some out of equilibrium state, your system has some possible states associated with some probabilities, and any observers, systems that might belong to them, are uncorrelated with such that they don't know what the state is. The system undergoes an equilibration, and then now there's a correlation between the observers and the state. So one can then ask, as a first step, when does the equilibrium state have this spectrum broadcast structure? This nice, perfectly intersubjective, redundant state? The answer is actually never. In fact, there's a form of states of which SBS is a subset, which are also impossible, perfectly distinguishable classical quantum states. The asterisk here is, I mean, you could carefully construct a Hamiltonian for which the SBS state you can use the eigenvalues of your Hamiltonian to construct an SBS state. So in that sense, you would equilibrate to an SBS state, but only because you're already starting. So yes, so what this says is that under this hypothesis, taken in its most primitive form, which is simply the state must equilibrate and purely through that action spread the information about the universe, an exact projective measurement is impossible. It's not surprising that it's impossible. Actually, having in various conversations throughout the time here, a lot of people believe that exact projective measurements are impossible for different reasons, which is quite interesting. But it's not surprising that it's impossible on thermodynamic grounds, but where the difference here is that even having a zero temperature bath doesn't help. Even allowing yourself some infinite resources effectively doesn't help. And what about the von Neumann measurement scheme, the thing I showed you before? Well, that's when things get a little confusing, because if you simply throw this thing into, start with some uncorrelated system, apply this Hamiltonian, and then allow the system to equilibrate, it's going to completely lose the correlations. So therefore, we've falsified the hypothesis, right? This can't work. Measurement is not simply equilibration. But we've asked a little bit too much there, right? We've asked for exact equilibrations of this SBS state, and we've not even allowed a little control. So relaxing the first point, you can consider an interaction that says, if the system is in some state I, I'm going to do something that corresponds to some Hamiltonian HKI, where K, remember, labels the different systems involved. And I mean, it accords with our intuition about what a measurement should do. If this, then that. If something else, then something else, right? And crucially, also, if we coarse grain our environment into clumped systems, then the justification for this, of course, is that every single quantum degree of freedom of your detector doesn't need to encode the spin measurement. I don't need every electron in my photodetector to tell me that a photon was there. I just need the current to tell me that a photon was there. Then you arrive at something that looks a lot like an equilibrium state that looks a lot like an SBS state, with a fidelity that exponentially vanishes as you gather more systems into your sort of macro observers, if you like. So this cross graining actually seems to be necessary. So if you take that Hamiltonian structure and just use a random matrix model, start throwing Hamiltonians at it. If you take them from a Gaussian ensemble, you'll find that as you increase the dimensionality of your environment, but keep it as a single system, the error in your lack of objectivity, if you like, doesn't go to zero. It concentrates to set around a single value. So this coarse graining really does seem to be the thing that at least this implies. It's of course not a proof. This coarse graining seems to be something that's absolutely necessary. Okay. So in summary, this hypothesis resolves the thermodynamic, is one way of resolving the thermodynamic problems associated with measurement, and also on some level helps us to address a conceptual issue of when to model a measurement of a projection. In our model, it's if there's a big conditional interaction with your system, then the equilibrium state will look like something that has the information redundantly, so to speak, classically encoded in the world. And also the ideal projective measurements are a fiction, but a useful one, because they can be approximated exponentially well, as long as you don't demand that the information is spread through absolutely every degree of freedom, but rather say, if I clump things into domains, then the information should somehow be encoded in there. I mean, this is an incredibly simple and restricted model. I can't highlight that enough. One thing that you could do is to allow some unitary control. Of course, we have some unitary control. It's not, you don't just you don't say, I'm going to measure this thing, I'll throw it out there and hope the information comes back. You carefully construct an environment such that you can amplify the information that's there. But nonetheless, the arguments that I made, I believe, still hold, in that at some point you're going to run out of control, and you have to let nature take its course, so to speak, and the irreversibility of the process will kick in. So one thing that we're actively doing now is looking at models of actual measurement devices, photon detectors. That is to say, devices which are very carefully engineered in an out-of-equilibrium way, such that a small kick, one way or another, will rapidly amplify the information as the system comes to equilibrium. And then there's the question of non-projective measurements, updates. All of this, another caveat that I should have said but didn't, was that this was all finite dimensional. And so how do you talk about continuous variables, field theories, infinite dimensional systems? And I mean many more. There's many other things in the works. So just to show you the other people that worked on this, this is Manu Schwarzhans, the then PhD student who's now in Malta. Me, Marcus Huber, and my colleague Felix Binder in Dublin. Word from our sponsors, so to speak. And a quick advertisement for a conference that we're sorting out in Dublin in July, if anyone's interested. And also, another advertisement is that we have a PhD student position available. The main supervisor will be Eva in the Institute for Theoretical Physics, but co-supervised by me and Marcus Huber. So, thank you very much.
So, perfect timing, so we have a lot of time for questions. Yes.
I just want to ask you a question about, well, yeah, I guess the philosophy of this spectrum broadcast structure or quantum Darwinism or whatever. I mean, and because you put up Zurich's famous picture, right? So my understanding of why Zurich was talking about quantum Darwinism was why systems which are macroscopic, like things which are, like he talked a lot about the pointer basis. Okay, so it's already talking about a system which is an apparatus, and then why does it continue to behave classically? Why can we then treat this thing which is already macroscopic to behave classically, rather than the question of how does a microscopic, qubit information get amplified up to the classical scale in the first place? So yeah.
So yeah, I mean, Zurich has through his long and illustrious career talked a lot about various aspects of the problem. One of which is the question of the pointer basis, most famously in this 1983 paper, very interesting, which is effectively about the symmetries of interactions necessary that will define the pointer basis. And then from that, which environments and their interactions with the system will then sort of preserve, it will pick which information is preserved and which information is kind of killed through decoherence, which then leads to the Darwinism language. And then from that on, the information gets spread out and multiplied in the environment. So I wouldn't say that Zurich's work on what's now very broadly termed quantum Darwinism is really one aspect. It's not restricted to the pointer basis. It's a chain of questions somehow that connect to each other.
Okay, but I guess my point was, I mean, so maybe there was a change in perspective then, that at some point this idea started getting applied to a microscopic system and asking how the information, is that what happened? Like, when did that happen?
I believe so. Filling in the lines from all I have is papers and dates. So conversations that happened between those things, I don't really know. But the vast majority of the work on sort of, so to speak, objective state structures comes out of Poland and people with whom he worked at some point early on in their careers that then went on to do things. So they are somehow the torchbearers of Darwinism. But yeah, I mean, the sociology of it I leave to or the history of it I leave to the historian.
Yes.
So I'm going to go back again to the question we were discussing yesterday because it's still not clear to me. When you say that projective measurements violate all laws of thermodynamics, I think, at least let me go to the example of second law of thermodynamics. If I have, for example, forgetting even about quantum mechanics, just a bunch of, say, dices here, no? And they are all with a phase 1 up. And I put them inside a machine that the machine, what it does is flipping them to a random phase, and that's what it does.
Sorry, wait, phase 1?
Phase, well, you call the phase of a dice.
Oh, phase, sorry, I thought phase.
Phase,
Sorry,
yes. Phase, yeah.
Yeah.
So I can pick them back again. I think this machine has increased the entropy of my dices, even though it has taken each and every one of them from one state to another given state in a probabilistic manner. The fact that now later on you may decide to pick one of the dices and look at the phase, it pops up and you say, oh, I was describing the dice as having a lot of entropy and now I know it's resolved. Oh, this entropy has decreased. I don't think this is a correct way of accounting for what is going on. So I think the measurement, if you take the measurement postulate, an option, as saying, no, it is a machine that brings this system to a concrete state, but then you make the computation of the second law of thermodynamics with an ensemble of those. I think the measurement and the process of bringing each and every of them to one state and not the other does not decrease the entropy, rather it increases the entropy of the ensemble. The fact that you later on may need to check one of them and see what it was the concrete result for each of them is a completely, so for me the measurement process is the ones that takes away all the off-diagonal terms and leaves you the diagonal, and this increases the entropy.
Yeah, I mean that's how the equilibrium state comes about. Basically.
Yes, but this is no, but the process that you put there that decreases the entropy is one bringing a mixed state into a single state. And for me, this is not the projective measurement.
A projective measurement doesn't turn a mixed state into a single state.
It does it but no. This is a check-in. This is, I mean, the state is already there of a single system. This is the process by which you go there inside and check what was the concrete result coming out. But if you do a statistical description, the measurement process is the one that takes a phi and in a psi, a pure state, and brings it into your best description of it being a diagonal basis a diagonal matrix of the basis you're measuring.
So what you're saying is the state update rule should not leave you in the state that you found the system, but in the mixed state as though you haven't looked at the outcome yet.
No, that's for an ensemble, but the point is that thermodynamical laws should be thought in ensembles. So in each of the concrete system got a well-defined concrete state and got a well-defined concrete outcome, but the ensemble got an increase in the entropy.
So if I don't know the state of the system and I observe it, that by itself has decreased the entropy in a sense. This is Schiller's argument, right? The purpose of this is to say, okay, I have a particle that can be in one half of a box, a single particle, and then as he proves through that, it's just like Landau's principle, you take a toy model, prove something about that, and then say it's a general principle. You can argue about how good, but nonetheless, taking him at his word.
Yeah, sure.
Exactly in that paper, he proves through a series of ingenious arguments that the act of having observed this thing and knowing that it's in one or the other necessarily has to correspond to an increase in the rest of the universe, given a specific outcome. But what that means is that if you don't consider the rest of the universe, and you only consider that, then it looks like a decrease in entropy. So my point is not that entropy decreases when you get an outcome. My point is the opposite. My point is that you observe a given outcome, and in doing so, reduce the entropy of this and increase the entropy of the rest of the universe.
Yes, I understand that point, but I think that the fact that it's a discussion.
I think we should postpone this to drinks later. So, any other question? Yes.
So, despite being in the same group as you, I don't work on this, and I once heard you say a very provocative statement. a while ago, like over a year ago, before you finished this work, and you've been working on it for some time, so might as well ask you now. He once said that his hope is that you can derive the Born rule from the second law of thermodynamics, and that this is the most succinct way to describe this effort. Having worked on this and sort of given us this spiel, what do you make of this?
I mean, I've seen multiple attempts to derive the Born rule, but never really found any of them particularly satisfactory. But then, I mean, as Flo was saying some time ago, it doesn't really make sense to talk about the probability of the event that has happened. Like an event happens, you have this experience, you get an outcome. There's no post hoc probability of that. The probability is what you assign to that, and there are good probabilities you can assign to it. That is to say, the ones that will accord with you performing the thing again and again and again, and bad ones, which are the ones that won't accord with you performing the thing again and again and again. I know frequentism is not a popular opinion about probability, but as we've discussed many times, it's how you have access to the world. So, I don't really know. I don't really know what it means to derive Born's rule somehow.
But there is, for example, in the Paris book, this kind of toy models in which you assume that for given states, they are more distinguishable than what the Born's rule will allow, or what the scalar product tells you, and you can run on machines that do violate second law. So it's the opposite. It's not driving.
This one I don't know.
It says if you don't obey this, you can get into the problem.
Ah, okay. Yeah, I'll check out the reference. Thank you.
More questions? If not, I think we can thank our speaker
No, it's a good starting point.
So there's a paper about this.
I tend to play.
I'm not sure. I just don't know.
Parents, yeah, of course. Also the clocks, right? Even before us.
It was like somehow they were making it to renormalize it. I don't think I can see how to look at the imperative, but whether it's like the scale was not.
The system is too. I forget this. Right. Okay, but not the idea.
Exactly, because at this spectrum, so you can only apply it
Can you hear us, Tony?
Okay, great. Okay, so let's welcome the next speaker, who is the last speaker of today's session. This is Antonio Acín, who will talk about Bell's theorem, randomness, and secrecy.
Okay, so you can see my slide and you can hear me, so
yes.
Correct me if wrong. I don't know how you're going to do it if you don't hear me, but I should you do. So, yes, so thank you very much for the invitation to come to attend the workshop. Unfortunately, I had to cancel at the very last minute, so I'm sorry for that. I having some busy time, so this also I wanted to attend a few, or most of the talks, but I couldn't. But I'm here, and I will. I also thank the organizers for giving me the opportunity of presenting my slides online, and this is what I'm going to do. Okay, so this is more or less a sort of general talk in which I will share some thoughts with you, and then I will also tell you about some of the recent results we got in the group. So I will start by stating that, well, I mean, you see here in my title there are 3 ingredients. I will go through the ingredients and I will present results on the way. So I will start by the first ingredient, Bell's theorem. I think you all know this, so it's a theorem that was introduced in the context of local hidden variable theories proposed by Einstein, Podolsky, and Rosen. And basically, what Bell inequalities do, they provide bounds on the correlations attainable in the theories. Okay, so you are thinking of an experiment in which you're thinking about an experiment with the so-called that refers states, and these states are measured. And then you are confronted with some models to explain the experiment in which the output of each station is determined by a deterministic function, taking the input and the possible classical instructions coming from the source, and this determines the output of 2 sides. The source produces instructions lambda, and that can be correlated or can may vary with the probability distribution. And otherwise, I think the other like there is nothing quantum in the derivation of the inequality on quantum parallel on later is a retaliation. I mean, now I think.
Okay, continue.
Okay. So I think now we have a more modern understanding of the scenario, and what we have is basically a sort of framework in which we can study statistics, correlation structure of physical theories under causality constraints. Okay, so basically these are rather natural language to represent experiments in a black box picture. So for instance, if I want to represent this experiment here in which there is a device that prepares some states, and the state that is being prepared is assign a label to this state X, and another device will prepare some other states in which preparations are independent. This is why I represent them with 2 separate devices, and these 2 states that are prepared are being measured in a central box, and here I don't make any measurement, so I only compute the output R depending on the preparation. Well, then I can associate causal network to this experiment in which they have the 2 independent preparations, and this information goes to the central station in which random variable depending on the 2 preparations is produced. And I think one of the things we understood with Bell theorem, and I guess this message is obvious and also in other disciplines, is that when you have a causal connections or causal constraints, not everyone is connected to everyone, then the statistics you can observe is not arbitrary. Okay, so for instance, this is an entanglement swapping experiment that you don't recognize. There are 2 states that are being prepared, they are sent to 3 parties, and then you make measurements. Okay, so this is a way to represent. And once you impose these causality constraints, I'm not going to discuss how you impose them. Okay. You might have ways or reasons to assume that these causality constraints are respected by your experiment. Then from these causality constraints, you have some non-trivial conditions that your observed probabilities have to observe. For instance, here, you see here, if you sum over C, what Alice and Bob see should not depend on Z. Okay, and this simply follows from the causality constraints of the network representing the experiment. And in the same way, if I sum over B, okay, then there is no connection between A and C, so the probability that the A and C should be perfect. Okay, these are things that follow simply from the causality constraints in the picture. And of course, we also understand that if I see an experiment and I associate a causal network with it, like what I was doing before, of course, I can also associate other causal networks with it. For instance, I can add more causal connections, okay, like the one here. This possibility can never be falsified, okay, in this. I mean, even if, let's say, the 2 causal connections in your experiment were the ones given by this network, you can never falsify this network in which you add an extra constraint, okay? This is logically possible, there is nothing wrong with it. You may argue that it's weird because it's a bit weird that there is some information coming from Alice and Charlie that reconnect causal connection. But we don't see when you do the marginal probability distribution in Alice and this product. So it's some sort of causal connection here that is not reflected in the observed statistics. Again, it's possible. Okay. So, but I would say it's weird, but it's possible. Okay, so what are the models, these local hidden variable models, or these the causal models that are considered in the scenario? Well, what we do is like we take the network with the causality constraints and we associate to any variable produced in the network a deterministic function. Okay, so if you look at what is happening here, there are the lambdas and mu that are produced, and these are classical instructions, and then what is produced on A depends on X and what came from lambda in a deterministic way. Okay, so these are models in which I explain everything through deterministic functions. Okay, I have some probabilities for this what it is here, but this is statistic behavior, stochastic behavior. Okay, then it's rather I would say simple to put the labels for the deterministic functions because they follow from the causal connections I imposed. Again, I don't know where they come from. I just imposed them. Okay, assuming that they represent my experiment. So this is what happens in the Bell scenario. I was in a general, so now if we go to a Bell scenario, we have a source that refers a state of two particles, and these two particles go to two separate locations, and these two separate locations you make two measurements, or you make different measurements and get different outputs. Okay, and here I can reason in this language and with these arrows and represent objects by black boxes or by circles for the observed variables and squares for the later variables, the hidden variables. I can reason like this without making any reference to any particular theory. Okay, so this is nice because I'm saying that this is a quantum experiment, a classical experiment. I'm not saying anything. I'm not saying whether these particles have a given energy. I'm just putting some labels to actions in my experiment and in a way you can see this as this is the Bell scenario, Bell framework. So now you can think of you in the lab making this experiment in which you prepare these two particles and you make these two measurements and then you associate this causal model for the experiment. Or you can think like, okay, I want to prepare this model, so and you try to enforce the condition in the experiment so that you believe that the experiment satisfies the causality conditions that you are aiming at. Again, this is a valid causal model for a Bell experiment. Okay, I can exclude this. People try to exclude this invoking space-like considerations. I mean, like Einstein causality considerations. But as we all know, I mean, you can never be 100% confident about this. Okay, so because even when you make space-like considerations, you have to define the moment in which the event starts, let's say, and ends, and this is not well defined. So there's some arbitrary component there. So we try our best to make sure that this is not happening, but we cannot exclude. Okay, so these loopholes, locality, free will loopholes will persist. We try to make them less plausible, but they are always there. So again, it's important to understand that in all what I'm going to say, in what follows, I'm not going to discuss about how you enforce this causality, okay? I'm going to assume them, I will extract conclusions, and of course these conclusions are no longer valid if the causality constraints I imposed at the very beginning are not true. Okay, so I don't want to enter in this discussion because it might be a never-ending discussion, precisely because you cannot exclude extra causality constraints. Okay, so now coming back to the inequalities, we have this language of the causal networks, and these are the models that the inequalities care about. So now I put some extra content in my theory, so right now I will demand that the outputs are defined by deterministic functions under the causality constraint. Okay, and Bell inequalities are just constraints satisfied by those correlations, those statistics you can generate under these causality constraints and deterministic functions. Okay, and then you can see that there are linear functions of the observed probabilities, and they satisfy some bounds. And it's clear for many people. It was not clear to me when I was a young researcher, and I even wrote a wrong statement in papers. But there is nothing quantum in this. Okay, it's just something that you could have done without physics, and people obtain Bell inequality without any reference. two measurements, two outputs, you construct this expression, and you can see that this expression, when the outputs are predetermined, so the result makes this function, is converged. I don't think I have to spend a lot of time here. So how do we construct Bell inequalities today? I mean, historically, if you look at the CHS paper, they were constructed by intuition, by hand, okay? So people had ideas about how to impose the constraints coming from these formulas and define Bell inequalities. But today, we have a recipe to do it, okay? So we just, we want to find a set of local correlations or causally deterministic correlation within the causality constraints that I assume for the Bell scenario. And we know that this set of correlation is convex, so this set is known as the local polytope. And the extreme points of this local point, of this local polytope, are just given by the deterministic assignments. Okay? So, and the point in which you specify the output of each measurement is one of these vertices of this convex set. And now there is a recipe that if you have the convex set defined by the vertices, you can find all the facets. Okay? Programs will do that. And these facets are precisely the Bell inequalities. Okay, so these are the boundaries of your set of classical correlations. You don't have to think about it, okay? Just you program and you get all the Bell inequalities for a given number of measurements and output. So if you do this for the case of CHSH, you get CHSH. Now, the interesting inequalities, of course, are those that are called typed. Okay, so these are the facets of the Bell inequality, but of course, these are also Bell inequalities. Okay, these are hyperplanes, and the set of classical correlations is on one side of the hyperplane. And if you are here, you don't have a classical explanation for your correlation. Okay, what I'm representing with my screen is the space of the statistics. Okay, and something is classical if it's within this convex space. And then, okay, so if you define this extreme points, I mean, if you increase the number of measurements and outputs to these extreme points, you need a big computer to do that. So the problem becomes quickly hard, but in principle, we know how to do it. And then you have all the facets, which are all the type Bell inequalities, and you can play with these Bell inequalities to falsify one of these deterministic models under causality constraint. Okay, so you run this, you get CHSH for the standard case. You can also run this for the case of two measurements of three outputs, and you get a Bell inequality that was derived by some of the people in the room, like Nicola and Sandu. And okay, you see it's another linear function of the Bell inequalities. Here you have two measurements, 1 and 2, and you have three outputs, 0, 1, and 2, are three. Yes. And this is also something that you can now derive running this polytope somewhere and getting the Bell inequalities. I mean, I would say there is nothing super relevant here. We don't know how to do this. Okay, so in all what I say during my talk so far, talking about Bell theorem, I just presented what Bell theorem is about. Then I quickly moved into the Bell scenario, and I was not making reference to any physical theory. Then I made reference to this this causal deterministic model. Sorry. And I write the Bell inequalities, and now finally I can put quantum physics, okay? Because the nice thing is that you have quantum states and you make measurements on the quantum states, respecting some of the causality constraints, again, in a cautious way, this respecting, you can violate the Bell inequality, okay? So what did we learn from that? What we learned is that in quantum physics, you can get correlations under the same causality constraints that are not possible in the traditional model under the same category. So if you look at the space of correlations, it's larger. We have this larger set of red correlations, which is again convex by non-polytope. Okay, and this is CHSH, and what happens in quantum physics, you can get up to square root of 2, and this is the Simpson bound. Okay, so the only thing you have to do then, if you want to find the maximal quantum violation, you have the same hyperplane, so the same slope. And you only have to shift the hyperplane so that it becomes tangent to the quantum set, and this defines the maximal quantum relation in quantum physics. Now, also, if you, in more, say, modern terms, what we also understand is that causality is affected by quantum information. Okay, so if you run a Bell experiment, you get some statistics, and now if you think that this statistic has been obtained by this causal network, you conclude that with classical information, this is not possible. Okay. that the same causality constraints are enough to explain value correlation if you are in the question of quantum information. So in a way, the causal inference, which correlations are compatible with some causality constraints, the answer to this question depends on the physical theory that you use, and some correlations that are valid in classical physics under some causality, but are not valid in classical physics under some causality constraints become possible under the same causality constraints in quantum physics. Okay, so this is another consequence of that theory. But also now we have other ways of understanding the Bell scenario, and it's one in which, again, the Bell scenario as it is general. It can be applied to any physical theory. So in particular, you can work in this Bell scenario in quantum physics. So Bell scenario was then applied to deterministic models, and you obtain Bell inequalities. So you can equally apply the same type of framework, and then assume simply the idea of quantum physics and see what you can argue about this. Okay, so then devices are seen as black boxes, quantum black boxes. So you don't question the validity of quantum physics, you assume it. You assume the causality constraint, and you try to see what you can get out of this. So basically, you are interested about the set of quantum correlations. Okay, and then we can then interpret this in a more flexible way beyond the Bell scenario. Okay, for example, you can think of situations in which you have these different states that are being prepared, and then they go to different observers, and these observers make different measurements. And in I would say the quantum Bell scenario, the statistics you should expect, you don't make any reference about the states and the measurements are implemented. They exist, they are quantum, they have a quantum expression, and the only thing that this picture tells you is somehow where to put the tensor products. Okay, so you see here, here go to copy if you want to impose, but usually we don't do these things. So for sure you have tensor products in the states here in 1 and 2, 1 and 3, 3 and 4. And you also have tensor products between the measurements in the different parties. Okay, this follows from the causality constraint. I'm assuming you don't like them, you don't assume them, and then the conclusions you get under this form are no longer valid. Okay, so in a way, the causality constraints here they tell you where to put the tensor product. But now again, I'm not taking quantum physics with respect to classical physics or with respect to synonym theories or anything like this. I'm a quantum physicist who wants to reason about models in this black box scenario with causality constraints. And this is the device-dependent quantum information processing. Okay, so you want to find protocols in this scenario, and then the nice thing is that your devices can then be seen as black boxes producing classical outputs by getting classical inputs, and the object here that you are interested in is the observed correlation. Okay, and of course you want to do something beyond classical information theory. You should better have correlations that are not explained by the deterministic classical models under the same causality constraints. And the nice thing is that these protocols have somehow self-certification because the good performance of the protocol depends only on the same correlation. Okay, so this is a long story. I will tell you, I guess for many of you these things were known, but I thought it was, since we are somehow celebrating the inflation rate of Bell, it was good to somehow put these general considerations before starting. Now, if you are interested in the making protocols in this black box approach, one of the first protocols that was proposed was one of the first was by Cloud. So in this black box approach, even if you don't assume anything about the state and the measurements implemented, you can then derive properties of the with quantum physics about the state and the measurements implemented only from the observed statistics. Okay. In fact, this result can be even traced back to the papers by Silson, but basically it tells you that if you observe a CHSH violation equal to square root of 2, so if this is the point where CHSH becomes tangent to the quantum set, well, what you see here in a two-dimensional space is really what happens in a way. This point is quite unique. And it's so unique in quantum physics that there is basically only one way of getting this point, which is by the way we know of, to get the standard 2-qubit way of getting 2/3 of 2, okay, which is the state prepared by the source modulo some symmetries is 2-qubit maximum entangled state, and the measurements are the ones that we are familiar with, the XZ and B1, B2 according to this block sphere representation. Okay, so this is In a way, this is telling you that if you buy some device from a provider, you can check the validation. It is 2 square root of 2. You know that what you're getting is maximum time state of the qubit. This is very nice. Now, there is interest in the community to go beyond this nice result, and then you start, then you have to see whether similar properties hold for other Bell inequalities, and in particular whether you can, for instance, self-test the maximum angular state or a Wigner dimension. And then there was a result that at that time that I got more than 20 years ago with Nicolas Gitton, Tomabio, and José Ángel Latorre. And I remember at that time we were quite surprised by the results. So what we did at that time, we took this Collin-Gitton-Lindemann-Popescu inequality that is defined for 2 settings of 3 outputs, and we looked for the maximal violation of this inequality with 2 qubits, and then we found that it was not obtained by a maximum entangled state, and we were surprised, okay, because we were very used to the CHSH picture in which the maximal quantum violation is obtained by the maximum entangled state of 2 qubits. I remember Nicolas, it was maybe one of the first results I told him as a postdoc, and I believe he thought that I was wrong, and I also thought that I was wrong, but at the end the result was quite easy to prove. I mean, at least find a larger violation. But then when you think about it, I mean, this is not at all surprising now with our modern perspective, because this Collin-Gitton-Lindemann-Popescu inequality is something that you derive, they derive intuitively, but we know how to derive. You only have to construct the local polytope, list the deterministic points, run, and look for the facets. So why should the maximal violation of this classical object, let's say, single out the maximal entangled state in a given dimension? Okay, so I think it was a nice coincidence of CHSH, but we should not expect this to happen in any other situation. Okay, so now we understand that it's not surprising that this inequality, which is a tight facet of the classical polytope, why this should identify a state that you define using Hilbert spaces. Okay, so this doesn't make any sense, I think. So what you have to do if you want to do self-testing, you have to think on Bell inequalities in sense of how you are interested in finding hyperplanes tangent to the quantum set, independently of whether they are tangent to the classical set or they are facet of the classical set. So this is what we did in this paper. So what we try to follow some sort of intuition. So in this paper, we are somehow back to the CHSH time for Bell inequality for classical physics. Okay? So CHSH, they had some ideas about how to smartly take this combination of probabilities, and they found a Bell inequality. So in this paper, we somehow, I would say in a rather rudimentary way, we had some intuitions about how a Bell inequality for the maximum entangled state could look like. And then we, of course, explored some properties that we need for the maximum entangled state, the fact that it's U times U complex conjugate invariant. And we use this to choose the coefficient of the Bell inequality, of course, the Bell functional. And then we massage a bit things, and we got a Bell inequality, and we proved that this Bell inequality, the bound was a Bell inequality, and the maximal quantum violation was obtained by the maximum entangled state. And then we also ran some techniques that were introduced by Scarani, Navasquez, and co-workers, something called the swap test, and we could numerically prove with an SVP that this Bell inequality self-tests the maximum entangled state of dimension 3. Okay, and I think a numerical proof came later by Sarkar, Wushak, and co-workers. And of course, when you look at this, the Bell inequality, is this Bell inequality tight? Of course it's not, but what should it be? So we never, the construction of our Bell inequality is simply guided by quantum considerations. It's never guided by classical concentration. And you should, in the same way, you should not expect that the maximal quantum violation of a Bell inequality is obtained by a given target state. You should not expect that if you design a Bell inequality thinking, say, quantumly for a given quantum state, you should not expect this to be Bell facet of the algorithm. Okay, so I think here we have something which is nice, which is try to think about how to probe the quantum boundary, because this is interesting to self-test properties of either the black box quantum device-independent quantum scenario. To be honest, I mean, at the moment, my answer to this problem, as I said, is quite rudimentary. Okay, so we got these inequalities value for any maximum entangled state of dimension D, but now, and we also did this with Flavio Vaccari, Remigio Zabushak, and Ivan Sukic for graph states. So we have sometimes some techniques to find Bell inequality to our target state. but we are very far, I think I'm very far from having a good understanding of the general recipe. And also this step, the external was implemented in Bristol, and they could also get a rather large violation of the inequality from which you could also certify a given fidelity with a maximum attacker state in a black box scenario. Okay, so this, I spent most of my time talking about that theorem. Now I will go to the second ingredient in my title, which is randomness. And also here, I think our understanding of randomness has evolved with time, also thanks to that theorem, among other things. And this is a sentence that I took from a paper, which I wouldn't say is wrong, but I don't agree with it. I mean, it's a paper by me, so I think people evolve with time. So what I say here is randomness is something fundamental. I think we all agree with that. That is of interest in cryptography and numerical simulations. I think now I will never write anything like this because I think here we are using the same concept to describe two different things. So numerical simulations, what you require is statistical randomness. Okay, you want to have sequences in which there are no patterns. Okay, in a way, for you, it's irrelevant if someone can predict these sequences. Okay, what is relevant is simply that these sequences are highly entropic. Okay, and with this, you can then run Monte Carlos, or you can run Monte Carlos, have numerical simulations, and the quality of the numerical simulation really depends on the absence of patterns in the sequences. Again, here for you, it's irrelevant if someone can predict the result of the sequences that you use. You can even use public randomness for that. And then what people use randomness is missed tests. So these are tests that look for statistical patterns in your sequences, and they make sense. They make sense here, okay? Because I mean, if you have something that does not pass the missed test, there are patterns, and this may have an impact on the quality of the calculation. And here there is a second thing, which is So here there is a second thing, which is private randomness. So here is something that you want to have unpredictable, but of course you don't want anyone to predict this result, otherwise it's not useful for cryptography. And here the fact that there are patterns or not is much less relevant compared to the fact that someone can predict. Okay, so these type tests, they don't look at private randomness. And then the figure of merit is no longer an entity, but should be an entity conditional on your enemy. And we know that this bound is of course an upper bound to the private randomness, but this randomness bound is often not tight. So just to give you an example of why we talk about two different things. So imagine you have a business model and you have two products. One of them is you have a virtual casino, and the other one you have randomness for numerical calculations. And you come to me, I'm the provider. So what I do, I have a very good random number generator that I think is also going to this figure of transmissibility half. Everything is perfect. So what I do, I generate these random numbers and I put them into a classical memory and I send you this device. Okay, this device is perfect for numerical simulation, but of course it's completely useless for cryptography or for virtual casino because I can predict all the outputs produced by this device. Okay, so the fact that you have, and by this device you can run perfect numerical simulation with this device. I'm assuming that you don't see the end of the memory in this. Okay. So the fact that you have a device that perfectly works for an application and not for the other, it's really telling us that we are talking about two different properties. So what is then private randomness? Let's define it, and let's define it as I was doing before in a theory-dependent way. Okay, so we have a user, you have a device, this device produces outputs, and you want these outputs to be unpredictable, either not only to you but to anyone. So you put this as an extra, as the eavesdropper, the enemy. And you want these PIs to be unpredictable to not only to you, but also to this super E that has control with everything that is outside your lab. And I think this definition is satisfactory because, I mean, it's very hard to argue that something is random if someone else can make a perfect prediction about this process. Okay, this clearly is not random if someone can make a deterministic prediction. And then also the good thing is that if no one can make a prediction about what is happening in your lab and your lab is secure, then it is a source of privacy that you can use for privacy verification. Okay, so basically then if you want to make quantitative statements, what you will do, you will quantify the randomness of this condition of your enemy. And this is a problem that in principle you can pose and you can try to solve. And you can pose in any theory. You can propose in classical physics, in quantum physics, in any theory you invent, you can try to argue in this black box picture and reach conclusions about randomness. Okay, so this is randomness. Now let's go into physics. In classical physics, you can see that there is no way you can certify private randomness. I mean, any classical experiment produces zero randomness. But in quantum physics, you can design experiments with zero randomness. And well, the cleanest situation is given by a Bell test. Okay, so precisely because of what I was telling you, under the causality constraints that I assume for the Bell test, there is no deterministic model, hence a Bell violation certifies the presence of randomness. Now, if you are a quantum believer, you don't need to enter among these things. You may simply say, okay, I think the correct modeling of my experiment is by a tensor product measurements on a state, and then you can see that this certifies the presence of randomness if these correlations are non-local, because there is no probability distribution in quantum physics whose marginal is non-local and where E can predict the outputs of the experiment. Okay, there is no such a thing. It's impossible in quantum physics. Again, I might now forget all the discussion about comparison of theories. I'm a quantum believer. I can state this problem. I can prove that this probability does not exist, so no one can have a perfect description of my outputs. Okay, so this is the 500 randomness. Now I will, yes, I still have time. So once this is clear, we can relax this, and if we are quantum believers, we can even have different ways of certifying randomness. We can do it in the device-driven approach, in which I see my devices as black boxes, and I can certify the randomness of the produced output under the physical model of my experiment with causality constraints. Or I can see put more trust on my devices. Maybe I would have trust on some of the elements, or even in all the devices producing my experiment, so I can really say that I know which states to prefer and which are implemented, and this is the device-dependent approach. Okay, so I think here is a matter of assumptions. You may be, of course, here the fewer the assumptions, the more confident you may be in the randomness of your experiment. But all those experiments require causal constraints and also require, in some cases, extra assumptions on the devices and the measurements that are implemented. So I'm going to now tell you about some results we got in the device-dependent randomness certification. And this is a paper that we had in collaboration with several people here. I don't read the names. So the question is very simple. Actually, I was surprised to see that this question was not known, and I hope no one here contradicts me. So it's very simple. So assuming you have an experiment and you know that you are doing the state wrong, okay, it's device dependent, you know the state you are given. So how much private randomness can you extract from this state? Okay, so it's very simple. I think it's very fundamental, and it's even of relevance for quantum random number generators. So what I'm demanding is that you have to perform the optimal measurement on this state. So you're given the state, you can do whatever you want with this state, and you have to extract randomness. So you have to find the optimal measurement to extract randomness. And of course, I'm interested in private randomness, okay? Because statistical randomness, any state has perfect statistical randomness, even identity. Okay, you make a measurement that is unbiased with respect to the eigenbasis, and this gives you fully entropic data. Okay, so this is trivial. I want private randomness. So then, what I will do, I will include E in the feature, and I will do this by putting a purification. Okay, so you see here this is the state of the user, and you see the state becomes pure, and I want to know the user implements the measurement, and this is the resulting state. I want to know what is the maximal entropy I can get. Or I can also say, I will make the measurement and I want to see what is the optimal measurement that Eve can implement so that she tries to predict my output. Okay, and this is another big figure of merit that's called the guessing probability. Okay, for the sake of time, I don't have time to go into that, but for the examples, sorry. Okay, we solved this question with full generality. Okay, so the maximal amount of randomness measured by the entropy that has a state is given by this simple equation here. Log 2b minus f rho, so the state is pure, you get maximal randomness. If the state is mixed, you get zero randomness, and in between, you get some private randomness. And for the guessing probability, you also get this nice expression, which is given by the trace of the square root of rho. Okay, so this problem is solved. Last thing I want to tell you, quickly, secrecy. Well, this can be much faster. So what is secrecy? Here I'm thinking more about quantum distribution. Well, secrecy is nothing but shared private randomness. In a Bell scenario, this comes from free because the randomness of your outputs comes from Bell inequalities, but of course the measurements are correlated, So you have correlated randomness, okay, and this can be used to construct a key. Okay, so this is what, for instance, we propose. So you have the CHSA equivalent experiment. You can add these third bases and construct a key out of A1 and B3. A1 is random, it has to be, and it's perfectly correlated to B3, so it's a secret key. Okay, so what is the role of Bell locality? Is it necessary? Secret key distribution is independent, whether it's sufficient? I don't know. Okay, so what we prove is that for what we call standard protocol, it's not sufficient. So one of the authors of this paper, Micheletta, is there with you, I believe, and well, she can also tell you more about these results. Okay, so basically what we did, we took standard protocols. These are protocols in which you make the key out of some bases that are announced in the reconciliation, and then most of the protocols have this but not all of them. Okay, I can tell you this if there is time. And basically what we did, we proved, sorry, I'm going to be faster here, that from this, we could get nonlocal correlations, the private abelian inequality, and then prove that these bases are announced in this nonlocal correlation. There is no way you can get a secret key. Okay, so at least for the standard protocol, like the standard CHSH protocol, there is a region in which there is no secrecy despite that your data by the abelian inequality. Okay, so come to the conclusions. I told you many things. Some things were known, some others maybe not. So what I was trying to tell you is that then here, oh sorry, wait just a second. Yeah, sorry, there was some more music comment. Okay, so yeah, so then here implies the existence of correlation properties that have no deterministic model. It also applies like causal inference effect by quantum information. Now, if you forget about these questions, this same scenario is basically what is behind device-independent quantum information protocols. I then told you about the amount of randomness in states, and I think it's a very interesting open question whether the non-locality is sufficient for security. It's nice also because here you can reason about foundation and information science with the same language, and I didn't follow all talks, but I guess I'm not original saying that I'm looking for proposals. Thank you very much for your attention.
Okay, so questions? Yes, Renato.
Hi, Tony. Thanks for the talk. Can you hear me, or do I need to come?
Yeah, sure.
You hear it? Okay. So I have just a question about, so first of all, I like this distinction you make between statistical randomness and private randomness, because I mean, indeed there's a lot of confusion and people sometimes think that these statistical tests are actually useful in the context of like gambling or cryptography, which they are clearly not. But now I'm not sure where does the term private comes from, because if, for example, we have gambling, then clearly we don't mind the privateness. I mean, in a lottery, we want the randomness to become immediately public. So I would like, would the term unpredictable randomness or something be more accurate? I mean, I don't know how widespread these terms are, but if one, let's say, wants to make this distinction to statistical randomness, because the property that statistical randomness doesn't have is precisely the unpredictability.
Yes, I agree. To be honest, I never thought on which to use, okay, but yes, I agree. I mean, privacy also, of course, these are private, you can store them in your lab, no? But I mean, gambling, actually, you announce it, no? If you have a bit of data, you announce it after producing it, so, yeah.
Okay.
I will change it for my next talk. Or I will go and speak on this type of thing. But I agree, yes.
More questions? So let's thank our speaker again.
best, Tony.
Bye, Tony. Thanks.
Bye, Tony.
Largo ai giovani.
Magari c'è una 9 Stiamo impazzendo, è stata una settimana molto lunga. Deve finire. Ah, posso.
Thank you for me. Hey, I see, yes, yes, yes. This whole quantum engineering and quantum industry
Come straight from pretty much.
3 hours leave, but you signed already.
You were also partying. So you cannot compete with this level. Yes. Are you starting?
Wait.
Dancing all the night.
I made one of the most clever decisions
Okay, it was very nice meeting you in person.
I hope so. Very good.
How many hours of sleep did you watch?
So, in that sense, good morning to this very last session where we have Veronika, who will be talking to us about Wigner's friend's perception and the no signal principle. Yeah, you have the stage. Thanks a lot.
Yeah, welcome everybody to this very last day of the conference. I had a great time so far, so thanks to the organizers. And today I will once more talk about Wigner's friend in a slightly different way than we have heard before. So Wigner's friend talks at this conference already. So I will have a brief about basics. You know Wigner's friend, the source, meaning state, and I will only talk about qubit theory. Then the observer called friend measured this thing, and what is the crucial part of Wigner's friend is that we basically put this imagined box around it and have a super observer who then performs a measurement of everything that is inside the box. For the sake of simplicity, for us, this is just system and friend. And Wigner's friend now
highlights that there is a tension in, if you want to describe this scenario and stick to what is called standard quantum mechanics, because you can make arguments for two different descriptions of what happens in the quantum. According to the friend, this state of the system collapses when she measures it. According to Wigner, however, this box is somehow provides enough isolation that he would describe everything that happens inside there militarily. Wigner's trend is interesting for various reasons. Personally, I think it's nice because it's a tool that allows you to investigate your notions of measurement and observation. When I talk about measurement, I think about something that is a classical result, it's irreversible and macroscopic, like we heard in Max's talk yesterday. And if I think about observation, I'm usually talking about perception and, more importantly, some thoughts and some reasoning that I can do based on this perception, like which is important, for example, for the NASU's setup. The good news is in everyday physics, these are all fine. So whatever idea you have about measurement and observation, you can basically, for practical purposes, if you look at any of them and then talk about measurements. However, from a foundational point of view, that's not the case, and you can kind of use Wigner's friends to investigate what you think about it and how you want to describe measurements and observation. You can do this all together, or, as we've also heard in this conference, you can kind of separate the two a bit. So if you are more interested in the measurement part and how things become classical, irreversible, and what is macroscopicity in some precise sense, you're asking what is a measurement? Exactly like Max was talking about yesterday. What processes describe measurements which are unitary? On the other hand, if you are more interested in the perceptions, so for in this case, in the measurement case, your Wigner's friend is a fancy Schrödinger's cat, basically. On the other side, if you talk about, on the other, so your cat, the cat is your friend. On the other side, if you talk about perceptions and thoughts, and especially then imagine that your friend is smart and knows how to use quantum theory, you can talk about reasoning in these setups. And you can investigate that somewhat separately, regardless of what you know. Basically leave the measurement part a bit out of the equation, but really talk about perceptions and thoughts of this entity that you put in the box. And this now concerns observation and the question whether something like an observation can happen if you put the thing that is supposed to observe in a coherent superposition of observational states. And while I think both are interesting, and I'm actually working on both, today I want to talk about the observation side of things. So I'm going to talk about perceptions and thoughts, although physicists and philosophers then never get tired to point out that this is vague and ill-defined and whatever. As I said, the Wigner's friend is a tool to investigate ideas you have around this. And in that sense, I'm using it today. Good. Very concretely, we look at Wigner's friend, and I am interested in the friend's point of view across time in this setup. So I say at time t0, my source emits this qubit state. Then there is time tf, where the friend performs this computational basis measurement. And now in her, I imagine this is memory registers, right? So this system F, there is a result encoded that is in perfect correlation with the computational basis state of the system. Then there is a time t1, just after the measurement, where we now assume the friend has this definite perception of one of the two results. Then Wigner measures on the whole box, gets another one of two results. And then there is a final time, t2, where all the measurements have been performed. And throughout this talk, I'm going to assume the following two things, namely, Wigner's unitary description of this box is empirically adequate, meaning any measurement he can perform on the box has results occurring with these probabilities. So again, just using pure space for simplicity here. So you project onto the eigenstate or on the unitarily evolved state of whatever is inside the box after you measure. And I'm going to assume that the friend has a definite perception corresponding to the computational basis state of her register at all times after she has performed this measurement. Good. As I said, so I don't, this cat I write down there is not a friend, but it's her memory register.
Can I just ask, for all times, even after Wigner is done, even though his would have to be a measurement that interacts with every single...
Yes, and it's not, I'm not saying it's a constant thing. That's what I'm interested in. I'm going to come to this in a moment. So Wigner's measurement messes up this memory, but the friend can still try to, but we can think about of how this happens, what happens there. And that's exactly what I want to do. Yes, so the information that, or the results you obtained is somehow stored in this memory. As you can easily calculate and argue for, of course, Wigner's measurement will mess up this memory, right? So the probability that the friend sees a result at time t1 just after her measurement is different from the one, from a computational basis measurement that you would perform on her register after everything has been done. Meaning,
sorry, I have to come. Can you come back to the previous slide? Because, so a definite perception, but definite means here not definite because it could be changing.
At a certain time. So that means while you might, so Wigner assigns a superposition or state, right, to the box. What I'm saying is...
Why call it a definite? It has always a perception, but it's precisely not a definite perception.
I mean, that a superposition state of these two perceptions is not, as assigned by Wigner, is not a state of suspended animation as Wigner originally proposed in this. But I'm saying there is a matter of what the friend sees, even though the whole box is in a superposition state.
So you might avoid some of this by
Yes,
writing at each time rather than for all times.
Yes, I should have specified. Yes, at each time. So a single one, like there is...
It could be different at different times.
Yes. That's what I'm talking about. So that there is not some blurry state because the memory, because the whole thing is in a superposition. That doesn't mean that the friend has some really, I don't know, some blurry impression or cannot talk about what she sees at all.
Yeah, but I think what Tim is saying is exactly what I want.
Yes, I should have put at every, yes,
Each
a single
time.
one at each time, yes.
Okay, thank you.
Good. Yeah, so, and this, whatever this result encoded there at each time, now, of course, has to change over time, as you pointed out. And what Czaslaw and I were interested for some time is, well, how does the memory change? And can the friend, in some even very vague sense, be aware? So let's say, okay, so I'm here, I measured, something happens to my brain. Could I maybe have some notion of, I don't know, how bad it is, for example? So the first thing we did in that direction is that in this paper here, together with Philippe Langerin and Flavio, we formulated a Nonlocal theorem for the two-time probability of what is in the friend's memory before and after Wigner's measurement. Namely, what we showed in the paper is that a two-time probability can fulfill the following. So, first of all, you want to assume there is this two-time probability, and it gives the single-time probabilities as marginals. Then you assume unitary dynamics of the whole thing. So, basically, you involve everything that's in the system, friend and Wigner, unitarily up to the point of when you're interested in, and then project on the memory register you want to talk about. And that the joint probability should be a convex linear function of the initial state. I'm not gonna bore you with the details of the proof. You can check it out in the paper if you want. Important are the consequences. Okay, so like
can I still ask something about the assumption? So the first one looks to me like more a definition of definition of a marginal distribution. In what sense is it an assumption?
Not that. That this joint probability even exists. You can make arguments that such a thing doesn't make sense anyway.
Yes. Okay. So the assumption is P F1 F2 exists.
Yes, and from that
this formula, how we calculate PF1 is not so relevant.
It's relevant then for the proofs.
Yes,
so that
but
follows.
it's not part of the assumption.
No, the assumption is it exists, and then by probability.
Yes.
Calculus,
Okay.
that's what you get. We just write it like that because that is important. So as I said, you can reject one and say assumption one and say, yeah, okay, there just is no such joint probability. You should not define it at all. And you can argue for that. I think there have been arguments for that within many worlds because of unitarity. If you're not in a since you're the friend, right? If you're not in a decoherent branch and you can recombine, which is a certain variant of many worlds, you should not talk about the past if you recombine branches. You can reject two, so unitary dynamics is just not what you use. So the probabilities are not given by this now is the Heisenberg projector if it has an eye on the initial state. Then you have a collapse, and then you have all the trouble of explaining exactly does a collapse happen. And even if you have a model, does that mean you have completely excluded Wigner's friend? Because, as I said, you can pick apart this measurement and observation thing. So you would say, might there still be a notion of perception or awareness with systems that have interacted with the system they want to measure, but not yet completely collapsed state, for example. So basically, if you're fast enough in your collapse description, you can still have a Wigner's friend situation. Or reject assumption 2, says the linear dependence on the initial state is just too much to ask, which is something the authors of this review paper, which is in the audience, have suggested you should do because they think this assumption was not super well motivated to begin with. Anyway, the message here is if you really want to describe exactly what happens to the friend's memory, in this scenario you need to put in a little more than standard quantum mechanics. That's the important message for the purpose of this talk. Good. So we try to do this, and in order to tell you how, let me briefly formulate this Nonlocal theorem in a way that we did not in the original paper, but in another one, and that will be useful for the rest of the talk. So, if you want to talk about changes in the memory, I'm more interested in the conditional probabilities, right? Of what happened, like what's the conditional probability after Wigner's measurement, like given what was there before. So, write my joint probability in terms of a conditional one, and then take the marginal to get the probability after everything has been done. Now, the linearity assumption basically boils down to assuming that the change looks like this. So there is one parameter, which I call the flipping probability Q, that describes what happens to the memory. That means if the friend initially, for example, saw 0, so the green part here, with this flipping probability, the register gets inverted, and after Wigner's measurement, there is a 1 encoded there, and with 1 minus q, it just stays the same. And then you plug in unitarity, and equate the two basically. And then you find for general states and settings, you cannot solve this equation. So there is no such parameter, meaning you cannot fulfill all the 3 requirements, because they all went into this description. Okay, that's just another way to phrase the Nonlocal theorem. But then in this paper here, we wanted to answer the following question. Well, okay, that doesn't work.
Sorry, that is still assuming convex linear dependence on the initial state. Right, okay. So all the same assumptions.
Yeah, as I said, it's just a reformulation of the Nonlocal theorem in a way that is useful for what's going to come now. Good. Now in this paper here, Joseph and I tried to address the following questions. Well, okay, that doesn't work, so can we still describe it? As I said, we need to put in a bit more than quantum theory now. And I found more interesting questions. As I said, can the friend be at least in some sense aware of what happens to her memory? Well, the answer to the first question is yes, obviously, because otherwise there would be no paper. And so you can, of course, solve this system of equations by increasing the number of variables, which amounts to a model like this. So these flipping probabilities now are different depending on what the friend initially saw. Right? So if she saw 0, there is a certain probability that the entry gets flipped, and if she saw 1, there is a potentially other flipping probability. So great, you can describe it. But as I said, you need to find a bit more because now these solutions are, of course, not unique. And if you want to uniquely determine them, you need some third principle. I don't know, you can require them to be minimal or as symmetric as possible, whatever. That's up to you. I think you need some good motivation to do that. Okay, so like whatever you want there. The interesting thing, could the friend be aware of what happens there? The answer is no, because that would violate the no signaling principle. And I will tell you.
Sorry, I'm still confused. So when you say yes, we can describe this, then how is it?
What I'm saying.
How is it resolved the previous theorem which you put up?
You would go off the linearity requirement, so you don't have one parameter, you have two, then you have another description.
So
you cannot do it with Q0 equal Q1.
Okay,
Yes,
so I'm
not
then
for
so
all
why does
settings and states, that's all.
right, so why? Yeah, okay. I'm not saying why is Q0 and Q1 breaking the assumption? I just don't. Yeah, I don't understand.
And because no, I'm just saying that like what we had before with one parameter was the original three assumptions. So
Yeah, that's why I don't understand. Why is that equivalent to the original three assumptions?
I mean, that in the paper, but so the origin. So the first. This is first assumption 1. This is boils down to the linearity assumption.
Okay. So right, it relates to linearity.
You need unitarity to get this system of equations. So this system of equations with one parameter equals the original assumptions of the no-go theorem. Right?
Yep.
And now we do something different, so we let go of one of them. That's all I'm saying here. Right, so we have a different model, one that needs to be specified further if I want to describe it non-ambiguously. And the issue is this will violate the no signaling principle if the friend is aware of this. How and why? Okay, to see this we need to finally go to Wigner Bell setups. Howard already introduced this. So very briefly, we know that Wigner Bell setups now combine Bell setups would be so I have a bipartite source, and the two subsystems are sent to two different Wigner's friend experiments. And there I can define a notion of local friendliness and show that the local friendliness inequalities, very similar to Bell inequalities, are violated for these setups. That means that this object here, so a joint probability of the results of all four observers involved, conditioned on setting choices that I now have for the Wigners, cannot satisfy the local friendliness assumption. Cool, but I'm interested in something different here. Namely, what I want to talk about is a probability of what is stored in the memory of the friends after they have been measured by their super observers, conditioned on what was in there before that measurement, and now also on the setting choices the super observers have. To make our lives easier, we take a simplified version. So we just take one Wigner's friend and the third observer. And now we look at the sequence of measurements that are as follows. So at T0, source of the state, at Tf, friend measures, at Tb, later time Tb, Bob measures. Even later than that, Wigner measures at time tw, and I'm interested in the in-between times, the friends and Bob's measurement, although not so much. More importantly, T2 between Bob's and Wigner's measurement, and T3 when everything is over. And then I look at the joint probabilities of the friends and Bob's results, and do something very similar to the simple setup, just one box. Express this in terms of conditional probabilities, and since Bob is a regular observer, and nothing that Wigner does on the other side should do anything to his brain state, this conditional probability should actually, as far as Bob's result does not change, but like in the simple case, the friend's result gets flipped with some flipping probability. Then you do exactly the same spiel as before. The other expression equated with the unitary probability formula, and then try to solve the system of equations, which you can do. Again, you get non-linear solutions of flipping probabilities that now depend on the outcomes of both the friend and Wigner. Good. So again, you need to impose some other criteria in order to uniquely fix them. However, there is a problem with no signaling. So while it's fine that these probabilities depend on Bob's outcome, it's not fine if they depend on Bob's setting, right? Because then whatever Bob does influences how the memory changes for the friend when Wigner performs his measurement. And if the friend is aware, you eventually see it. So if you take just general qubit states for Bob's measurement, and for example, this source state or some other, do the whole thing, what you then find is if you vary over the parameters in there, and especially vary over all measurements, fix some measurement, and then vary over Wigner's measurement. And in addition to that, you see that the solutions depend on trivially on mu and nu. So that already looks like signaling. However, you might hope that the non-uniqueness can help you to salvage this, right? So that the non-signaling requirement is the one thing the additional requirement you make, and then everything works out beautifully. Turns out it doesn't. So we found a counterexample in the paper. There is a certain initial state, and then, or not just one actually, quite a few, that if you then vary over Wigner's measurement, you get solutions that are no longer probabilities, which means the no signaling assumptions you plug in was too strong. Too bad. So we then also did in this paper, I think it's nice. Okay, say what does this mean? I mean, this is a problem. When is it a problem, and how? So we imagined something a bit more complicated than this original proposal. So now imagine the friend has a large number of memory registers and performs her measurement just multiple times. Meaning these ready states that are there before her measurement get turned, like in code, either 0 or 1. All the way to n. And this sequence should match the probability of the P of F1 that I have determined. Good. Then Wigner performs measurements on the respective systems and memory registers all in parallel, all n of them. Messes up the whole thing. So afterwards, there is another sequence. So some of them have been flipped, some of them stayed the same, but there is another sequence that now corresponds to P of F2. And now we just wanted to ask, so let's now assume the friend has some awareness of how much her memory has been flipped. So I'm not talking about like her keeping track of individual registers or even knowing exactly the flipping probability, but let's look at some simple things. So she just knows the memories have been rather flipped or rather stayed the same. So some notion of how much Wigner has messed up my registers. Well, Then you put the same thing in an extended, like in a Wigner bell setup. Use a maximal intensity state, and what you now do is you subdivide this large number n into sets of another still large enough number m. And now Bob's choice of measurement can be changed for the different subsets of m, right? So, and Bob flips a coin and performs one or two of the two measurements. Oh no, he doesn't flip a coin. If he really wants to single, he actually has to choose. So he has a sequence determining which measurement he performed, and then according to the first bit in the sequence, say it's 0. For the first m measurements, he performs the 0 measurement. The second thing might be 1. For the second m, he performs the y equals 1 measurement, and so on, so forth. This m is again large enough that the sequence for these runs in the friend's brain is a good representation of the probabilities, of the single-time probabilities. Then Wigner performs yet another measurement on the system and the friend, like again on every single system and memory register, all in parallel. And then you get, if Bob performs, and into you need to fix them, so we assume that the influence on Bob's result, the dependence on Bob's result is minimal. Just for convenience, you have to make some assumptions. So and we just put that, right? You can play the whole thing with another assumptions, then you have to look for another state, but it works out just as well. And then you get for y equals 0, a flipping probability of 1/2, obviously, of 1/4, which is smaller than 1/2, sorry. And for setting y, you get this flipping probability, which is larger than 1/2. So if we stick to our original assumption, the friend being aware of her memory having, like the entries having, rather having been flipped or stayed the same, she can distinguish the two. Then you have sigma.
Again?
As I said, we assume that the friend has this very vague notion on whether her registers have been flipped rather than stayed the same. She can distinguish these two cases, right? So you have signaling. Good. I'm almost done already, so the conclusions of this talk, if you were up to remember. What I told you is that if I want to talk about the changes of the friend's memory across Wigner's measurement, I cannot fully describe this by just using standard quantum theory. I need to put in some requirements or assumptions. However, these flipping probabilities are signaling, at least for some states and settings. And therefore, if the friend is aware of the changes, you have a violation. In some sense, you have a violation of the no signaling principle. Thank you.
Yeah, thanks a lot, Veronika. And now we have plenty of time for questions.
So, Bell, there's an interesting connection here, right? Bell got going because he had heard that von Neumann had proven this theorem, no hidden variables theorem or whatever. Then he sees Bohm's paper. He says he couldn't have done that because here's a counterexample. If you start thinking about this case from the perspective of Bohmian mechanics, you easily get the following results. A, there certainly is a joint probability distribution over times. You just assume that the mental state supervenes on the actual particle locations, right? And it's unitary, right? So you immediately say, okay, it must be the linearity that's violated. Furthermore, you say, is that pinned down? And you immediately see, well, no, because there are different guidance equations you can use that have the same overall statistics, and depending on, the flipping will depend on which one you choose. But then you see something else, which is that in Bohmian mechanics, if you know more about the initial state than is allowed
right? You can violate no signaling, but you can also violate Heisenberg uncertainty, which has nothing to do with non-locality, right? You could so my guess is you could get the same thing here, and you don't bring signaling into it. You just say, if she could do that, you could violate the Heisenberg uncertainty relation.
Yes, you can.
Okay.
So it is exactly as you said. So the Friend's result, this computational basis entry placed for Wigner Bell placed the whole of the hidden variable. Then basically, so what I'm asking here is, of course I cannot know the hidden variable, but if I have some even very limited information of the dynamics of this hidden variable, is this already a problem? Yeah. Yes. There is the Heisenberg uncertainty principle is violated as well. Okay, but as I said, you need a bit more quantum mechanics anyway. So we were less bothered with this in some sense. So if you kind of course you wouldn't want it to be screen, right? But if the thing that goes beyond quantum theory doesn't really respect this uncertainty principle, that might still be fine. But violating no signaling never is. Even if you say you go way beyond quantum theory, right?
Well, okay. Anyway, I would disagree. I don't mind violating no signaling, but at least that's your judgment that's forbidden, right? Yes. Violating no signaling for you is forbidden, but Heisenberg would kind of be okay.
Yes. No. I'm not sure you will be okay with. I'm not. That's why the awareness of the flipping probabilities is. I'm fine with the flipping probabilities being signaling, and then say, okay, that means that the friend can absolutely not be aware of them at all. That is fine, the combination of the two, because that is actual signaling. That is not just...
I'm okay with actual signaling.
It's really super lumen if you put that in space like superposition. You will be fine with that.
Oh yeah, I expect it. Oh.
Okay.
I'm surprised you can't, I would be surprised if you can't implement it. Because there's non-local causation. You'd expect there'd be a clever way to promote that into non-local signaling. It's weird that there's not signaling. It's not weird that there would be signaling.
Yeah, okay.
You just got to know where to look for it.
Okay.
I'm
waiting for the first bell telephone then.
Ask Sidhan.
Any other questions?
I guess just sort of a comment question, slash question, that that essentially the assumption we make in one way of thinking about the local cleanliness theorem is that it's our locality-like assumption is sort of no signaling, but at the unobservable, non-empirical level, because like things change for the friends, but it can never be discovered by the super observers at the same time. And whereas you're assuming that things change and that can be known, and then that elevates that up to like no signaling in the strict sense.
Yes, that is exactly the thing, because if you imagine, as I said, the friend has some awareness there, you can then imagine, okay, at the end of things, he can immediately communicate this to you, and then, that's exactly it.
Yeah. So then I guess the comment I was going to make is that I suspect that like any local friendliness inequality or something that we derive with that assumption, you could probably just transport into your theorem and reinterpret it in terms of...
Yes. I mean, I'm convinced you can. However, we thought about it a bit. It's not that straightforward. The thing you want to talk about is kind of different. I mean, you can. I think it should be easy to show the equivalence.
Right.
But then, like a real transference rule, like say, okay, as I said, you need to add some more assumptions to fix this. And say, okay, now assume I have this flipping probability. Like this is what happens. How does this translate?
No, I see. I mean, you sort of get a much. Doing it the way you do it. You have this, I don't know, much more visceral number Q, which is how much your memory is disturbed.
Yes.
And I guess that gives you a feel for. It's another way of looking at it.
Yes, but sure. I mean, these are very closely connected, and I think you can in some sense, as I said, show an equivalence of the two. Like
Yeah.
At least a violation of one implies a violation of the other, something like this. But like a direct link is not that easy to establish because you have this much freedom in actually describing the flipping.
Right, if you want to state it in terms of the flipping probabilities,
exactly.
yeah, sure, okay, yeah.
Modeling of awareness is not obvious. How would you do it? We have
No, well, right, but the awareness of having a memory changed.
Yeah.
No, okay.
There was another question before, is that still?
Yeah, so actually it's the same, exactly as what Howard asked. So now I just want to say thanks for the talk, thanks for advertising my paper.
Great, then if there's no more question, we can thank again.
Just one information, so we are supposed to check out at 11. I guess it will be very difficult. But let's check out during the break at 11. And you can then leave your luggage in the other small seminar room, which is just the outside on the left side. The first thing to do at 11 is to check out. Thank you.
Same for me, I don't want to leave it. Thank you so much. Yeah, it's been a pleasure. Thank you. Very stimulating.
Then we welcome Mirjam for her talk on monogamy relations for relativistically causal correlations, and the stage is yours.
Thank you. Well, thanks a lot to all the organizers for the very nice workshop. I'm very happy to be here, and yes, I'll talk about monogamy relations for correlations. And well, I put this in quotation marks here because I know that what causal means and all these things are a bit controversial. I don't want anyone to worry yet. I will define in a few slides exactly what this means, and it's a notion taken from previous work, and that's what I will do is based on. Okay, so this specific set of correlations, you can expect it's a generalization of the usual non-signaling relations to more parties. One of few options how people have okay, so the background of the talk is really, okay, what have people been doing previously on non-signaling relations, non-signaling conditions, and I just take the opportunity, because we're in a workshop beyond Bell's theorem, to just kind of, well, put some balloons, and then also, okay, to just start essentially with the usual experiment we have when people do Bell experiments. So assume we have two parties, Alice and Bob, who in the quantum case would do measurements on a quantum system. They are space-time separated, and what we know is that in these cases we get behaviors. So if they just collect statistics and later go together and compare them, we get such behaviors, and we know that these differ if we do a quantum experiment, if we do an experiment just with classical systems. And then we could also think that maybe there is a more general theory, we do more general things like the GPTs that Flaminia mentioned in her talk. In this case, we could get more general types of behaviors. And the most general we could get, for instance, in the GPT framework are the non-signaling ones. Okay, and so all these GPTs are consistent with special relativity in the sense that you cannot. This is the usual way people phrase the conditions that I'm sure everyone is familiar with. You don't want Y to affect Bob's input to affect Alice's outcome, because if you would, you could use it to send a signal. Okay, and now people have done is then asked, well, what does this mean if you have more parties? So assume now, instead of just Alice and Bob, we also have a Charlie here. And now all three of them want to do an experiment on some system. Okay, so I would say standard way how to generalize this is just to say that the input of none of the parties should signal to any combination of the others. Okay, and this is here, and I think this has been considered for a long time. This is a paper where these are stated. But considering that the other references are not moving, probably it's the original one, and I actually don't know who was the first to state this. Okay, but now there have been other proposals, and this is one other possibility, and it was originally introduced as a notion of jamming or tampering with non-local correlations. Okay, so essentially the argument is that, okay, depending on how the parties are arranged, maybe you don't want to impose all of these conditions. So for instance, the example that was given in this paper here is that if you have parties that are arranged like this, so they're really kind of on a line, so this is supposed to be somewhere in space, and then in principle, maybe it is not a problem if you would give Bob a mechanism that can affect the correlations of Alice and Charlie. Because really they can only come together and check for the correlations here in the future of Bob's choice. And so in a way, this might not necessarily lead to contradiction or really to an ability to send superluminal signals. So this was the argument. And what is in this language is just that you would essentially be able to draw this little constraint here if you have this specific setup. And of course, if you have arranged the parties in a different way, this would not be the case. Okay, and the original example that was given, well, it was in a different language, but essentially was this. It started again from Alice and Bob doing a Bell experiment, Alice and Charlie, sorry, and then Bob having this mechanism that tampers. Okay, so if they start from kind of the usual Bell experiment, measurements, essentially the correlations that they have are given here, where, okay, the notation is just that as you go down, the settings of Alice change, and as you go over, the settings of Charlie, and then each of these blocks essentially is a probability distribution, where, okay, it's just outcomes 0, 0, 1, 0, 0, 1, and 1, 1, okay? So this is kind of a standard notation. And now what, in their example, Bob can do, well, he can decide to do nothing, which I encode here as an input 1, or he can decide to tamper with the correlations, and one thing he could do is he could make the parties, instead of have quantum correlations, for instance, have outcomes that are perfectly correlated. Okay, so what this means is, that what such a mechanism could do is essentially turning correlations that are like the usual quantum ones into some other ones where this depends on his choice. Okay, and of course, okay, we're not restricted to quantum theory if we do this. We can also do this in principle classically even. So if instead of having the quantum correlations, the parties are just perfectly anti-correlated to start with, and Bob would have such a mechanism, he could essentially similar tampering, because essentially he just redistributes correlation and anti-correlation between the two parties without affecting the marginals. Okay, and so in this case, this would be the relation, okay, and this was called jamming correlations in this original notion. Okay, and so in this case, this was just an example that showed, okay, it could be that there is a mechanism like that still doesn't allow you to signal or lead to some causal loops or so. But in more recent work, this was then generalized. And this was generalized to essentially a framework for correlations that are compatible with relativistic causality. Okay, this is what this was called. Now, here, okay, the framework is about much more than this. And there is some controversy as well what this means to be compatible with relativistic causality and what you want exactly. I think the thick part that is not controversial is that this framework and all the works based on it, the set of correlations they set up is this one. Okay, and so I will start from the premise that we have these correlations and then see kind of from the correlations what consequences this would have for kind of the relations in statistics that we see and also for theories we could build. Okay, so this is the premise, and this is really taken not word for word, but all the ideas, of course, and everything is taken from this paper, who first set out this premise. Okay, and so I tried to give this in a relatively intuitive form, so I assume now you have n parties that are space-like separated. Again, they all have inputs and they observe outcomes. Now, if you want correlations that are relativistically causal according to this notion, what you need to have is that a set of variables the correlations of some variables can depend on any input variable where they're fully in the future light cone of it. Okay? And otherwise, if that is not the case, you have to essentially impose an independence constraint. It's exactly capturing this idea that you can affect things, correlations of things that are fully in your future light cone. And this is just kind of saying this for n parties. Okay, now one thing to note is, because it's all about light cone inclusions, actually the set of correlations that you write down like this is actually independent of reference frames. That's fine, because the light cone inclusions don't change. What is not the case is that if you make an explanation, and there have been some proposal of doing this with like faster than light communication to build this up, the underlying explanations that have been proposed are not frame independent. So because you changed order of things, and of course then that doesn't work. The other thing is that, okay, these correlations, a theory that has these has to be beyond this framework of generalized probabilistic theories that we've heard of, because their non-signaling is really built in. And so we're really would be looking for something more general that at the moment we don't have. At the same time, there have been mentions in papers that, okay, this might be an interesting set if we build future theories. And so this is a motivation to actually consider it, I would say. Okay, and then kind of said this already a bit. So here what I will focus on, because I don't have any satisfying explanation of how such correlations could come about, I'm focusing really on the correlations and what one could just conclude from these without thinking about underlying models or anything like that. Okay, and so then the question is, well, what would be the consequences of this? So what would it mean to allow really for this set of correlations? And the first thing that comes out is that there is kind of a type of monogamy relation that comes out. Okay, so we'll look at this setup with 6 parties essentially. And I assume now that they are arranged. Okay, it's not so easy to see I mentioned, but essentially you can go to a frame where they're all, if they're all at the same time coordinate, they're arranged in this triangle structure. Okay, so I have this setting. And you can see each party can have an input and an outcome as before. And actually for the argument I'm going to present, we only need the dark variables. In these cases the outcomes, and in these cases the inputs. Okay, now one thing we can get is we can essentially derive this monogamy relation in terms of the mutual information. And the mutual information is suitable for this because it essentially tells you how much information you would hold about the joint distribution of A and B. And this is kind of exactly what we want, because we want to know how a mechanism here that tampers with the correlations of A and B would affect one here that tampers with the correlations of A and C and so forth. Okay, this is why this is in terms of mutual information. And this has the nice property that it's zero if and only if a distribution really factorizes. And H is the Shannon entropy.
The set.
Right?
The set. The last.
Oh, that is W, sorry. Notation last minute, and yes. Thank you. Okay, so in this specific setup where we have binary variables and those are uniform, we can immediately see that this holds. Now, why is this a monogamy relation? Because if we have this jamming mechanism that we've seen before, then it means that this mutual information is 1. So the other two are 0, and we really see that we actually have two non-signaling constraints that the network doesn't impose. So having one maximal jamming essentially implies none at the others. Okay, now we can't just do this if we have specific cardinalities. We can also get general entropic relations. So in this case, luckily I've dropped the Z now. One possibility is that the information U holds about AV and V holds about AC is bounded by this conditional entropy there. Okay, these are just relations that you can derive. And then we can also compare them to previous relations because finding entropic constraints on these frameworks with different theories and different sets is something that has been done. We can also compare this to the usual non-signaling case. Okay, and in this case, something that has been derived is essentially a relation in this sub-scenario, where now I added the inputs. So in this case, okay, the notation is a bit different because now we don't care just about the entropies of A, E, B, X, U, Y, but about the entropy of this distribution on specific values. Okay, and this is essentially expressing the CHSH in entropies. Now what is known is that in the non-signaling case, this relation is true, and we can see that now according to this new set, this is not the case anymore. There are still non-trivial restrictions though. So between AE and AB, there is this a bit more complicated relation. Okay, so this shows that, okay, there are still non-trivial restrictions, and one can also show that this is really violated, as it's really a more general thing. Okay, and the non-signaling case here was treated in this paper. Okay. How am I on time, actually?
We have more than 30 minutes.
I have?
About 30 minutes left.
Ah, okay, very good then. Okay, then I can tell you also what the idea is behind getting such constraints. Yes. Okay, so the basic idea is to look, instead of looking at probability distributions, to look at the entropies of these distributions and of all the marginals. And this has several advantages. So on the one hand, when you have these independence relations that are polynomial, in the probability case, these linearize if you map to entropy. So they're quite easy to treat. On the other hand, when you have high cardinalities, when you have probability distribution, you have huge problems because you have all the probabilities. In the entropy case, you have one entropy, and you can easily treat that. And the drawback is it's a relaxation of what you get with probability. So some things you can't see in this approach. And it's kind of a complementary approach to the inflation works that Victor has presented earlier this week. So it's another approach to kind of characterize correlations in networks that in some cases can be successful. Okay, then the basic idea is to find constraints on these entropies. And if you have such a vector of different entropies, the basic constraints that all of them satisfy are that the entropy, the conditional entropy, and the conditional mutual information, which all three are just linear quantity, linear in the entropies. So linear maps on these vectors are positive. Okay, so these are linear constraints. At the same time, you can encode nicely the independence constraints you have in this way. Okay, and this then depends on what setup your distribution comes from. Okay, so here I've just put some example. So the green ones here are supposed to be before the others, and with the arrows here I indicate that there is really a direct influence. Okay, and U here is the one that can tamper with the non-local correlations, so I indicated that with slightly different arrows. So in principle, there is also an influence now from U to A and B, and so we have this graph, and now we know, in a sense, these are all just outcomes and inputs, so these are all random variables, and so we can actually use the classical method to describe such graphs, where we know that all the independencies are captured by saying the mutual information of a variable and its non-descendants, everything except its descendants in the graph are independent if you condition on the parallel variables. Okay, this is just called conditional independencies, and if you have only random variables in the graph, then this fully captures all the independence relations, so it's an if. Now in this case, what I did is essentially added these tampering variables into the graph with dependencies, but of course these dependencies are much bigger. Now I kind of take them out again with constraints. Okay, and these are for the two non-signaling relations that I would still have there. So, okay, for the experts, I mean, instead of starting from the non-signaling approach and trying to make it a bit weaker, we really go back to the classical approach, put additional dependencies in, but then remove them partially again. So it's an adaptation of the original technique that really originates from this paper 20 years ago. Then in the end, we may be in a situation where not all of the variables in our vector are things we can measure or infer. So there may be some, for instance, here it could be the lambda that we don't have access to. So maybe we want to know just the constraints on these probabilities. In that case, what we do is we take this cone that we've defined and we project it to a scenario that only has those variables. Okay, so we just get kind of a lower dimensional thing and we find constraints there. Okay, and this now you can do with different types of entropies. So you can do it with the original ones that I showed, but also with these conditions. This is kind of the basic idea behind how those constraints came out. Okay.
Excuse me. So what could be an example of a non-Shannon inequality?
Well, I can't write it down by heart. They are more complicated.
Among the list are only Shannon ones.
Yes, these are the three Shannon ones, and then okay, actually I didn't say that. So these are not. So if you have just three variables, then the Shannon ones give you the full cone of distributions you can have. If you have more than three, these are actually not tied. So this is a polyhedral cone that somehow approximates what you actually have. And in this case, there are, I think, infinitely many other inequalities, some of which are known, yeah, but they're more complicated. Yeah, so in addition to that, it's a relaxation to go from probabilities to entropies. There is also another relaxation in taking these Shannon inequalities or some additional non-Shannon ones, but we only know a finite number. So there's two levels of relaxation, essentially. Okay, so this is the basic idea. And so doing this, we can find compatibility constraints for this set of local correlations, where we can now come with a distribution or with behavior and see if it's compatible or not. But I would argue that we can actually do more than that. Okay, so I think that we can also draw some conclusions about what some features that the theory would have if it would actually lead to these conditions. Okay, and this is what I would like to argue now. Okay, so what is the idea? So I start, from this setup from before, and now I've again removed the W because anyway. And I only need, in fact, these to make the argument. To start with, I assume that these are independent and uniform, so I start in this scenario. Now, what we can't have at the same time is that there is this jamming mechanism that I showed at the start, that the parties can independently control, so they can make a choice whether they want to turn it on or off, and that the correlations you observe in this scenario are all in this relativistically causal set. Okay, and and of course in this it means that we cannot like exploit them to send superluminous signals. And now the argument for this one argument for this is the following. Okay, so assume the parties could really control such a mechanism. Now, if you start from the uniform case, they can decide either to do nothing or to change a bit whether they have correlations or anti-correlations, okay, or affect this. So assume now that each of the parties sitting here and here has two inputs, one just encoding whether they choose to do something or not, and then the one that does the thing. Okay. And in principle, they should both be able to do that, because in the original scenario where you have just three parties, they can do that. Okay. Now, what we find, if we look at this, is that if they choose to tamper with the correlations more than 50% of the time, actually this monogamy relation that I showed you before is violated. Okay? So this means that if we give them this control, indeed there cannot be. In this case, they are not in this. Okay, and the same is true if here we don't allow this mechanism to be perfect, but it can be essentially with any non-zero probability works, and the argument will go through as well. Okay, so what this means is, yes, in fact, if they have this control, we are not in this set, and in fact, there will be a possibility to send superluminal signals in this case, and the way it goes is essentially to somewhere here. So what happens if you set this up is that if these choices are 1, we have this relation among the variables, which means that if Bob, Charlie, and Valerie come together, in fact, the person Ulrike can signal to them. Okay, now, of course, okay, so we have to give up one of the two. We can say most people will probably not want, not all people, but most people will not want signaling. What this means is we really would have to give up this control of a mechanism. So this idea that we have that there's really a party who can tamper with correlations. So in a way, it restricts the choices this party can have. And in a way, it says that this mechanism, if we have them in such a setup, there has to be a global control for all of them. So they cannot be independent. Okay. Yes. Okay, and this is already the summary. So we'll make it for 11. Okay, so I think what I wanted to mainly say is that really if you just look at these correlations, you already get monogamy relation that I think point at features that one would have if a theory really has these mechanisms. Like this global control over different parts, which is not something we're used to, because we're used to arguing about kind of different parts of experiments separately and not necessarily having to always look at, I don't know, the whole thing or anything we do. So it really has to be quite different to what we're usually used to. Okay, and we have, I think, to give up relatively important features. So either we have to allow for even more general correlations where there's also some signaling, or we really have to, in some sense, give up our way to our independence to choose things. And I think these are relatively strong things that maybe we're not that happy to necessarily give up. Okay, then the advantage of the present approach, I think also to other works, is that really it starts from the correlations and it doesn't build a framework first, underline this, and then find conclusions based on this. But it really applies to any framework we could build that leads to these correlations. Okay, and I think it also has some implications for work that has already been done based on the set of correlations. So there's already work on causal modeling and also on the potential implications for cryptographic applications. But in this case, I think because there is this global mechanism, in both cases, actually, somehow one cannot, I think this work shows that one should not be doing this starting from the correlations. So I think to consider these more internal properties, one would really need to first build a theory that leads to these correlations or a subset, and then go into these questions. And the reason is that, okay, in the causal modeling case, I think when we do causal modeling, usually what most people want to build a framework in the classical or in the quantum case, they have in mind some kind of functional dependencies and kind of some they write their systems as nodes and do some dependencies among these. But I think because of these global properties, somehow this is not very natural. And so I think if we could actually build really a theory that has these correlations, it would give us insights about a new way, kind of how we should do causal modeling and how we should look at these things. And so I think this is a chance, if we want to stick to these correlations, to try to understand more. The second thing in the cryptographic case is also, there is this mechanism that parties cannot independently control. So I think it's very unclear. So it's clear that some monogamy of correlations break down, but it's very unclear how parties could use that. Because if one party can tamper with correlations and restrict the other, it's not so clear who could do that, whether it's the honest party or the adversary, whether they could shield each other in some way. I think there are many interesting questions that would actually come up from this. Okay, and also, okay, one other thing that I think I forgot to say is that, I mean, these monogamy relations, we also have monogamy relations in quantum theory. It's very different because there we have a system. We get correlations on outcomes that come from the system. The only monogomism among things that parties should be able to choose freely. So I think it's really also a strong and new type of relation in a sense. Okay, then a final question. Are these correlations really plausible for future theories? I can say I'm skeptical, but I think everyone has to make their own opinion, and I will just leave this as an open question to think about. Okay, and with this, I would like to thank you.
Yeah, thanks a lot, Mirjam, for this excellent presentation. Are there any questions before we all have to leave our rooms? Please go ahead.
Because you're using information concepts, and in the bipartite case, we know that quantum theory obeys stronger information constraints than just no signaling, such as the information causality requirement. Would there be any possibility, do you think, to build a multipartite, more general correlation theory like you've got, but generalizing the information causality principle to apply in that situation? Could that possibly give you more constrained theories, or is it just obviously not going to work?
So, I guess if I understand correctly, so you're saying rather than kind of looking at this, but with an additional quantum.
Yeah. Well, not necessarily quantum, but something analogous to information causality. But, you know, this sounds like an incredibly difficult ask, but it's just a.
Okay. So I guess you could ask for just principles that restrict this set of correlation further. I guess you won't have something like an information causality where I mean, we don't really have a quantum theory yet that does such tampering. I think if you'd have a mechanism and has some mechanism to do this tampering, then you'd have like a larger quantum plus tampering set, and you could try to say, what does this mean?
Right, but information causality doesn't rely on quantum mechanics in any sense.
Right, but okay, I mean, if I don't, but I know the quantum set, no, and I can show that quantum theory satisfies it.
Yes.
Now, if I restrict this step further, it will be difficult for me to conclude that quantum theory plus some tampering satisfies it, because I don't know what the tampering mechanism would look like. So you could put more constraints in terms of principles you find natural, which I think is already challenging, because when we think in a operational manner, which has kind of non-signaling in there often, at least in quantum information. So this you could do, but then because we don't know what these mechanisms would look like, I think the difficult part would be to show that such an extension of quantum theory satisfies your principle. And I guess this is with these principles, usually you want to go to a quantum set.
Okay, I'm just not sure why you're mentioning quantum theory, because I don't see it has anything to do with quantum theory.
Well, because I think, okay, I could come up, I mean, somehow the justification for me to, well, or one of the tests for me to see if my principle is good is that I think quantum theory should satisfy it. And in this case, so I mean, quantum theory has non-signaling.
Yeah, so
I'm not sure why, so I would think that if I do a principle where I give up non-signaling, I would also somehow have at the back of my mind that I want to test, well, get something a bit more general than quantum. Otherwise...
What do you mean give up non-signaling? I don't understand.
Well, I mean, okay, in quantum theory, you have these non-signaling constraints, right?
Okay.
And now we're weakening them.
Yeah, okay.
And I mean it in that sense.
Okay.
I mean, but yes, in principle, I mean, the high-level machinery of, okay, formulating a principle and then checking this, I think this works just the same. You can see if your principle allows to give up certain things. Your principle then has to rely on the really locations of your variables though. Because here, if let's say you arrange them in a different way, this changes.
But I guess I'm just thinking, I mean, you could start with a stronger than no signaling on the left-hand side, and then the question is how to generalize that.
Okay, I'm not sure.
Well, I mean, information causality is a stronger constraint than no signaling.
Yes.
So you could start with that as your left-hand side. And I'm not saying this is easy, but I'm asking, is it conceivable to start with that on your left-hand side and then ask the question, what will be the generalization in the same way as this? I guess it's not even that simple because it's not a multi-part thing to begin with. So
yes.
I know it's just an idea. I mean, I'm not.
I think there is work on multi-part generalizations of information causality.
Okay.
But okay. Yeah, I don't know those in detail. I don't know if you could relax something there and say. Because I think the natural. Well, I'm sure that I believe they're still giving you something within the non-signaling realm, at least what we have so far. So, okay, maybe you could do a different generalization.
Yeah.
I don't know what would happen.
You could say that the values and the extremes could violate information causality in principle, right? I mean, because they're the extremes, it doesn't matter, no? I guess really an idea.
Okay, so you want to say that some can violate it and some not somehow?
Well, they could violate it if they could communicate the results, but they cannot because of
okay.
so then there will be a relaxation.
Any further questions? Renato?
Thanks for the talk. Maybe the question is a bit similar to Howard's. So if one takes a completely I guess the whole motivation to relax these non-signaling conditions is that one wants to be completely operational in the sense that only forbid things that would really allow one to actually do something that contradicts our, let's say, intuition that comes from relativity theory, that we cannot actually signal, and you're just dropping those conditions which would anyway be useless to actually, in a sense, prove relativity wrong in some way. And so, is there, now of course one could on the other side say, okay, relativity also suggests there's a quantitative notion. I cannot signal an arbitrary amount, or like there are these natural constraints. But actually, are there arguments? I guess this relaxation has been discussed in the literature, but I'm not so familiar with it. Are there, let's say, arguments that say that relaxing that is already somehow in conflict with special relativity for other reasons, but still operational ones, that someone can come up with some clever scheme which will say, if you relax that, you can still actually cause an operational violation of something that should be forbidden according to our understanding of relativity. Because if not, then it seems that this is an extremely natural thing to do. And on the other hand, if I'm saying it's operational.
Okay. So I think what has been done is, I mentioned in the end these causal modeling things that I guess you know well because Villassini was involved in them.
These are, yes.
These are done, but I think go a step further and don't just look at the correlations. They really build something, and they say from the modeling framework they build, they also get inconsistencies. And in a sense, okay, this then says, okay, for any such framework you'd build, you'd get such problems.
Yes.
I don't know if in general, just looking from the outside at the correlations, I don't think anyone has done what.
So there is no reason why one should think this relaxation is unnatural.
I think I gave a reason why it should be unnatural, but I don't know any from before. Yes.
One last brief question.
Yeah, so the thing about non-Shannon constraints, can you just go back to that?
Yes.
Seems to be kind of an obvious analog to this, and I'm just wondering, because this is too much for me to take in, I don't know this well enough. If I'm just embedding points in Euclidean space, so for a triple of points, I have the triangle inequality, right? No matter how I do it, I've got to satisfy that. Once I get to a quadruple of points, every triple can satisfy the triangle inequality, but the full quadruple cannot be embedded. And then for 5, there's more constraints. Is that an analog when you say there are more and more infinite number of constraints as you add additional parties? Is that a good analog to what's going on here? You're thinking of the Shannon ones as just the tripartite ones, and then when you go up to 4 and 5 and 6, of course, in that case you do get more and more constraints. Is that just mathematically an analog to what's going on here?
Well, I think it's maybe slightly different because, okay, here you have these 3 types of constraints, and of course the number already increases if you have more variables.
Yeah.
So there are already new constraints coming. So you don't just take 3-party constraints and say, okay, there is now a 4-party constraint coming as well, but you're saying there are new types of 4-party.
Well, just they all derive from saying I need to embed them all in this one space, right? In that case, there's an easy way to say what you mean. If I have 8 points, I want to embed them all in Euclidean space. That puts constraints on their possible distance relations, right? And the totality of constraints for 8 is more than the totality of constraints for 7. Is that what's going on here?
No, I think there is a bit more, because if you have just these constraints for 3 variables, then these are linear, so you have a polyhedron.
Yeah.
But in general, the scheme that you get for 2 entities is not polyhedral. So you also change, already for 4, it's not polyhedral anymore. So I'm not sure I understand you 100%, but I feel like
it's still convex, right?
Yes, it's still convex.
Okay.
Then let's thank Mirjam. everyone to this very last session where Armin will talk to us about imperfect measurements for entanglement and steering. Thanks a lot for giving this last talk. It's a very nice conference to us.
Thanks everyone for sticking it out all the way to the end. Very nice conference, very happy to be invited. Very nice week. And I'm a bit destroyed since yesterday, so please bear with me and point out all my errors that I will make. Okay, so I'm going to talk about a line of research that we have been doing on when you try to make measurements in your lab, but recognize the fact that you don't have perfect control over them, and therefore make them imperfect. This is a series of works, so there have been a lot of people involved, but maybe the most involved ones was Juan, postdoc in Vienna, Simon Morelli, postdoc in the Basque Country, and Hayata Yamasaki, junior professor in Japan. Okay, so what I want to talk about is exactly that. I have a measurement device, and I want it to measure something specific. But I recognize the fact that my lab device doesn't exactly measure that thing. Maybe it's noisy, maybe all my components are not perfectly characterized. It is quite close to the thing I want, but it's not exactly that. Many times in quantum information protocols, whether it is standard QKD or entanglement detection or anything like this, we assume that we measure the thing we want to measure and then analyze everything based on that assumption. I want to drop this idealization and try to rectify it. So of course this is not new. You can do this in lots of ways. Here is just 3 ways. One way everyone knows, you can do tomography. Find out what the device does. Another option, you can just forget about what the device does and go device independent. Don't ask the questions, be safe from the beginning. And the third one is you can try to simulate your experimental errors. If you have trapped ions, maybe try to model the crosstalk and you can know something about your device. I think all of these 3 have advantages and drawbacks. Tomography, it's well known that it has problems with reconstruction. What you reconstruct depends on your reconstruction method. So you're implicitly introducing the problem again. Device independence, of course, is completely fine, but you are really, what do they say? You're killing a fly with an elephant gun. You have a small problem that you don't perfectly control your device, and therefore you say, well, okay, let's pretend I don't know anything. This is far too much, and we pay a high price for this. Device independence has large limitations in terms of its detection power. This is well known. And simulating experimental errors is, of course, completely legit, but it's not, it's a platform-specific measure. I want an approach which is operational, estimatable in the lab, and tries to sort of quantitatively address how well you can make the measurement you want to do. Okay, so the approach that I'm going to follow is very simple. I have a target measurement, and I'm going to assume it's a basis measurement, because that's usually what we want to do. The lab measurement can be anything, noisy, misaligned, the whole package. So what I want to look at is what I call the imprecision of the measurement. So I imagine that my uncharacterized measurement, I'm going to probe it with a source that prepares the eigenstates of the measurement I wanted to do. If my measurement is really the measurement I'm supposed to do, all the clicks will go in the exact same bin all the time. But since it's not, sometimes they will not, and that sometimes is quantified by my imprecision parameter. This is the same as looking at the fidelity between your target and lab measurement. So, the better your measurement, the smaller your epsilon.
You're assuming that your source is perfect and produces exactly the state you want?
Yes, so this is indeed an infinite regression, right, that you can keep rolling on backwards. So you can easily introduce the same thing in the source, but of course you will continue to have this problem. I think the reasonable thing is that you can overestimate your epsilon. So you can prepare the source, estimate your epsilon, and assign a somewhat higher value based on the trust you have in your source to be on the safe side. That's at least how we will do it here. So the properties of this thing, it's operationally meaningful. You can measure this thing in the lab. It's cheap to estimate it. You just need to do one projection for each one, far away from tomography. Just project on the bin where you want things to end up. It's tunable. If your setup is good, you tune epsilon to 0 and you do normal, perfectly idealized protocols. If it's bad, you make it larger and pay a price for it. It's valid for every platform. I don't do any specific physical model here, but it's also a worst case estimate. I like to think of it as a small conspiracy. There is a very limited flexibility that you have, quantified by epsilon. There is this point in space, you're epsilon close to it, but what happens inside this little ball is completely outside your hands. So it's a tiny conspiracy, limited in magnitude. Okay, so you can, of course, take this approach to all sorts of things. I will just talk about steering and entanglement, not non-locality, because non-locality is device independent. It doesn't matter if you have errors in the box or not. Quick reminder of what this is all about. So in entanglement, we have a state, and you make a measurement of your favorite quantity, decompose it in terms of local ones, and analyze the statistics. So here you have two idealized measurements on Alice and Bob. Both of them are going to become imprecise in my framework. Steering, very similar story. This time, half of your experiment is a black box, so there are no imprecisions there. Whatever happens is legit. But the other side is assumed idealized. In steering, you typically look at what states can the black box prepare remotely for this side. But now that won't be enough anymore, because you don't assume you have perfect control of this device. So you really have to look at the correlations. So the lab correlations with the imprecise measurements will be different from those idealized ones without the imprecise measurements. So these are the ones we'll try to understand. So here's the simplest case, war entanglement. Two parties just doing binary outcome measurements on a pair of qubits. So then you can just work with observables, sigma, x, and z, and stuff like that. Turns out you can write the imprecision condition in a simple way. So you take your ideal observable, your target, ideal observable, lab observable, and you find that they have a very simple relation to the value of epsilon. So then you can ask, well, okay, if I have a tiny deviation, does this matter? Can I just ignore it? After all, these days, people can make qubit projections with 99 point something high fidelity. Is this really to be taken any seriously? So here are some very simple case studies on witnesses that are very well known in the literature. The simplest one, 2 qubits measure XX and ZZ. It's well known that in entanglement you have perfect correlations in both. For separable things, you have limited by 1. The correction factor to this, you can calculate, it's that blue thingy. It's a little messy, but we only care about it in the limit of very tiny imprecisions. So if you look in that limit, the correction scales like the square root of epsilon. So if you have 1 in 1,000, you have to take a square root of that, and suddenly it becomes not so small. Well, you can say, well, this is probably a property of that witness, so let's try another one. You can also add a YY measurement. Again, you can have perfect correlations in all places. And again, you will be limited to 1 by separable models. But again, the correction scales roughly a square root of epsilon, actually a bit worse. You can go further and say, okay, well, what if I use the CHSH quantity, but for entanglement detection instead of non-locality? Again, okay, now it's a bit more nice. Again, you have this square root scaling. In the limit of small epsilon, this is not negligible. Here is a plot of that. So what you have on the x-axis is the imprecision, and here are the witness values. You can see that you have this sort of infinite derivative at 0, where you have your idealized protocol. The tiny deviations have a significant impact. So the question then becomes, well, how do I take this into account? In high dimension, this is for qubits. In high dimension, you have a sort of dual effect. There are 2 effects that pull in the opposite direction. At least that's how I like to think of it. Firstly, if I go to high dimension, 2 conjugate measurements, like x and z, go further away from each other. The overlap gets smaller and smaller, distances are getting larger. So if I want to erroneously go all the way from x to z, I have to travel a much larger path. My imprecision has to be a whole lot larger. So that seems to suggest that higher dimensions should reduce the problem. But then you have the opposite thing, that in high dimension, the number of directions that you can go wrong in scales like d squared. So you have a lot more ways of going wrong. And you can see, well, which effect sort of wins over the other. Here is the simplest entanglement witness that I am aware of. You measure XX, you measure ZZ with D outcomes, and you look how often you are correlated in both the bases. So I will quantify the influence of my imprecision with the influence parameter. So it basically says how much of the violation gap is erased by the fact that I allow for the epsilon. So if the influence parameter is 1, then it's all good. The influence is completely negligible. If it is 0, it's completely taking over your analysis. Here is what you find with the analytical explicit model for how to sort of hack the witness. So here you have dimensions up to 100. Here you have the influence parameter.
And you see that for very low dimensions, the first effect is winning. You're actually getting a smaller problem. But then at some point it turns and you get a very big problem where the epsilon completely takes over your analysis. This is where you put the imprecisions at 0.1%, 0.5%, and so on. Of course, imprecisions will not be constant with the dimension in real life. They will probably be increasing. So this is already over-idealizing it. So the problem is clear. Okay, so here's a fun thing you can do. You can use this to fake very large entanglement from nothing. So I take this entanglement witness. I counted at least 6 experiments using it. So I thought I will stick with that one. Again, I have the dimension up to 100, and here I have the Schmidt number, the entanglement dimension of the thing. Now, if I had prepared a maximally entangled state, then the Schmidt number would be equal to the dimension, the best thing you can have. So that's this gray dashed line. And now here what I have is the Schmidt number that I can fake from a product state, so 0 times 0, using something like, what is this, 0.5%, 1%, and 2% imprecision. You can see, for example, that my product state at dimension 80 with 0.5% imprecision can make you look like you got 20 entangled dimensions. Or worse, just as good as a maximally entangled state. I am hacking the protocol. You are assuming you measure the thing you want. I say, well, no, I have a very tiny conspiracy in there, and that deviation, I will put it well below the resolution of your device. That is your ability to actually estimate what your device does. It will not be visible, but the statistics will be completely hacked. All right, so that leads me to say, well, okay, how do you fix the problem? How do you make a criteria that take this thing into account? Turns out it's quite hard, especially if you try to go beyond the 2 qubits. This is the best we could do for high-dimensional entanglement that was really clean and analytical and fully generic. So this is a well-known entanglement witness where you have block observables, one of them, like the Gell-Mann matrices, and the conjugate one. And if you sum up and look for correlations in all these bases, it's well known that there's a separable limit that looks like that. And we managed to compute the exact correction to this. You can see that the correction comes as this big factor here, which depends on epsilon. You take epsilon to 0, you just get back to d minus 1. So of course, this is one way you can see it. Again, you have this square root type scaling, just as we saw before. This seems to be inherent to the problem. So that's at least one way you can try to deal with this. You can also go to multipartite scenarios. There you might be worried that the effect is even bigger. If I have an error in device 1 and in device 2, but now also in 3, 4, 5, and so on, maybe they're going to accumulate exponentially and get even more problematic. In a multipartite scenario, you probably care about more than just whether there is entanglement somewhere. You might want to look at something like genuine multipartite entanglement. So we tried to do that using the quite famous Mermin inequality. It's more well known from non-locality, but you can also use it as an entanglement witness. So the Mermin quantity looks like this. You have all your parties measuring either X or Y, and then you put your statistics together in the way Mermin tells you. It's known since a long time that this, for any biseparable state, so any state that isn't GME, there is a limit on it, and you can break that with a GZ state of n qubits. So the question is, what happens? Well, we will introduce our imprecisions, so our Mermin quantity just gets upgraded from measuring X and Y everywhere to measuring imprecise X and Y everywhere. All of the imprecisions can, of course, be different in all the boxes. Okay, so then we could derive this theorem, which has the good implication that your error doesn't have to exponentially go off. It doesn't kill off your ability to detect entanglement just because you have many parties. What it tells you is that, well, if you take the imprecisions into account, you get a correction factor that looks like this. If you take your epsilon to 0, it goes back to 2 to the n minus 2, which was exactly the old biseparable bound. So there is no exponential influence in the correction factor. So at the very least, you can make these constructions. I do highlight that this is an exceptional case. Most GME witnesses known from the literature, once you start adding the epsilons, they will take off exponentially, but you can find ones that do not completely ruin your detection ability. All right, so then at this point, I think it's nice to have a look at what these epsilons actually would be in real life. So this is an experiment that was done in Philip Walter's group, and they tried to make measurements of X, Y, and Z for different GME witnesses. Here are the imprecisions that they managed to get when they really tried to put it as close to 0 as possible. So you see that for the x and z basis, you are on the order of 10 to minus 4. For the y basis, slightly worse, but you're still on the order of ones in 1,000. Really small things.
Do you know how they estimated them?
They estimated it in several different ways. I'm only showing you one. So one was based on tomography, which I am against. Another one was based on the process I told you with this, where you probe the device with the fidelity projection. And then a third one was based on an explicit simulation of the experiment. They are all quite close to each other. But this is the one from the field.
I was in a project with some quantum experimentalists, and I wanted to take into account the errors, and they told me that there's no error.
There's always an
No,
error.
they told me that for measurements, the setup, there was no error.
Yes. Well, but that's good to hear, because that's exactly the point I want to make, that this idealization can be costly if you take it, if you're not aware of it. Okay, so here is my wish list for all the things I wish to solve but cannot. So here is what I would really like to have. I would like to have a method that can correct any entanglement witness. You throw me your favorite entanglement witness at any dimension, at any number of particles, and I tell you what will happen if you give me the imprecisions on top of it. And then I want this to be easy to calculate and fully analytical. No horrible STP methods or something like that. It should really work. Thirdly, I want it to work also for stronger entanglement concepts. Things like Schmidt numbers and GME and all that sort of stuff. And most importantly, the method should give you good bounds. Of course, I can easily make 1 to 3 happen by giving you terrible bounds. So I want the sort of everything, which is why I cannot solve it. I tried 2 methods that I'm not going to show you. I'm just going to tell you how they perform. I made an STP method, and I made an analytical attempt. The STP method, of course, does not satisfy number 2. It's not easy to calculate. And in fact, it doesn't always give you great bounds either, but it's pretty decent for small problems. The analytical attempt, I thought, was way more clever. And I was very happy to see, okay, it's really general, it's really easy, it works for kind of everything, but the bounds are completely awful. So awful that I don't dare to show you the method. Out of shame. But then it turns out that there is a lucky coincidence. So I don't know how to do it for entanglement, but those of you who have spent enough time on correlation problems know that everything is easier if you go to steering. So I want to move to steering, and then it turns out you can do all of these things in one single method. So I go to the steering scenario. Remember, one box is black now, the other one is white. So there is only one imprecision on one end of it. So assume now, instead of entanglement witness, you give me a steering inequality. So it's something that looks like this. A bunch of coefficients, some target measurements, the ideal ones, assumed fixed in the normal steering, and A, black box measurements. So there will be no imprecision. So then they come and tell you there is a bound on this thing. In fact, it doesn't have to be true only for local hidden state models. It could be true for a more complicated steering experiment, like for Schmidt number limits or whatever you happen to fancy. Anything where the target device is fixed from the beginning. And now what I want to do, I want to compute the corrections. So I will relax the fact that I assume a target measurement and I'll put the epsilon ball around it. And in fact, I could have a different ball, like different imprecisions for every setting and every outcome of my device. So it's like a bunch of epsilons. You can derive this theorem. I just want to tell you the main point of it. Here are all the epsilons associated with every setting and every outcome. It's a vector containing all the imprecisions. And this theorem tells you how you can compute a correction to it. It's a minimization, so it's not immediate, but you might notice that it's a minimization over a single scalar variable. You can even plot it in Mathematica and see the optimum. It's a very simple thing. So you have to take the bound from the normal steering inequality, and then you have this scalar optimization thing, and you have to compute this guy here. You see, this guy is just a very simple function. It's completely doable. If you assume all your epsilons are the same, you can even do this minimization analytically, pen and paper. It looks like this. So the correction, you have the old bound, and then you have this correction here. So you have something linear in epsilon. Again, you have the square root thingy that we have seen before. This is just some constant. Okay, so this works in general, but you have to see, well, is it any good? Is the bounds useful or not? So here is, again, the MUB witness that I talked about before, but now for steering. Measure XX, measure ZZ, look for perfect correlations. Again, 6-7 experiments also in steering that test this, so I figure it's a good benchmark. It was proven back in 2015 by these guys that you can make a very simple, fully analytical and tight steering witness for this. So you look for the probability of being correlated in X, probability of being correlated in Z, and you can prove that local hidden state models are limited by this thing, depending on the dimension. The correction from this analytical method tells you that it should look like this once you have added epsilons. For now, I take them all the same. All bound plus a correction term. And what it happens is that you can actually saturate this with an explicit model, which means that for any possible imprecision in any dimension, this sort of generic analytical model is giving you the exact result. And in fact, it continues happening if you have more MUBs, and for most of the witnesses I tried. I do underline it's probably not going to be tight all the time, that's too good to be true, but at least for some of the important cases, it does work very well. Okay, it turns out that there is a strange, for me, counterintuitive effect arising when you look at imprecisions in the steering scenario. I call it the imprecision plateau. So to illustrate it, I'm going to start with this simple steering inequality that was, I believe, introduced by Howard and his colleagues quite some years ago. XX, YY, ZZ in a local hidden state model cannot exceed root of 1, 3. And in a quantum model, you can go to 3. Well, so let's make a concrete example out of that. I will put the maximally entangled state with some white noise. And you say, okay, when can I violate this inequality? You just divide 3 and square root of 3, and you get 1 over square root of 3. That's when you cannot detect the steering anymore with this inequality. Now I want to compare it to another inequality. So my alternative inequality, for those of you familiar with non-locality, it's very similar to the elegant Bell inequality. I put Bell inequality in quotation because it's not a Bell inequality anymore. It's a steering inequality. So it's the same construction, but with an assumed measurement on one end. For those of you that don't know it, the idea is that in this inequality, you should measure on the block sphere 4 measurements that form a tetrahedron on the left side, Alice, and 3 measurements, x, y, z, form an octahedron on both sides. It gives you quite nice quantum correlation. So this one as well, if you compute for normal steering, no epsilons, if you compute what's the critical visibility for violating the inequality, you again get 1 over square root of 3. So in terms of detection power, in this noise model, it's really the same. You just have to make a few more measurements. Now the question is, what happens when you add the epsilons? What happens here is really exactly what we have seen for every witness that I've shown you so far, and almost every witness that I have looked at. You have the square root scaling, it takes off quickly, corrections become expensive. What happens here is completely different. So here is the imprecision again. Here is the critical visibility. Here is this MUB witness, the first one that I showed you here. And the red one is this alternative. You can see that there is something quirky going on here, down there. This looks flat. It's completely flat. There's nothing happening here. That's what I call the imprecision plateau. So the picture to have in your mind here is that you have this direction, the fixed target, and then you are allowed an imprecision. So there is a ball around it, and it's getting bigger and bigger and bigger. And so you don't pay any price for that, and suddenly it hits a critical radius, then it takes off. A bit slowly, but it seems like a weird effect. Surely continuous things should have no disruption. This is almost Leibniz principle from philosophy. So, question is, economists like to say that there is no such thing as a free lunch, by which they mean you cannot get anything without giving something back, at least in an ideal market, which we all know doesn't exist anyway. The question is, isn't this a free lunch? You are getting something. I am dropping the idealized assumptions, putting an imprecision measurement, and you don't have to pay anything in the model that you're now enforcing with all this. I might add that this plateau is certainly by far long enough to encompass all those epsilons that I showed you from the experiment. So it's certainly relevant on the qubit scales. So why is this happening? Well, okay, here is the picture with the ball that is increasing. At some point, it hits the critical radius, and the effect starts happening. So here is the intuition that for why this thing can be possible. So this is the simplest example. There are more of them. So what you have to do, remember that you have 3 settings on the white box, X, Y, Z, ideally, and 4 black box settings that form the tetrahedron, ideally. Now, in a steering scenario, in an LHS model, the box is black, the thing is linear, so you can do deterministic strategies. 2 to the power of 4 is 16. There are 16 of them. Half of them are just bit flips from the others. You're down to 8. So you can calculate all the 8 ones. And it turns out lots of them have symmetries. So you can bunch them into just 3 classes. The first class gives you the witness 0, which is totally trivial. You forget about it. The second one gives you something you might expect. The observables of Bob, number 1, 2, 3, summed up. Remember, they are epsilon dependent and they have to be optimized. So you compute that optimization, you get some function of epsilon taking off like a square root. But the key thing, the thing that makes this possible, is that there is a third class in which the symmetries of this elegant Bell inequality expression removes all your epsilon from the calculation. So it's really it's not really unique, but it's really a rare thing to happen in the landscape of witnesses. And this constant is above that thing in the limit of ideal steering. So here is a picture. Class 1, 0, just sits flatly here for all the epsilons. Class 3 sat flatly at 4. And then from below, you will have this thing coming. And at some point, it will cross and take over. So your plateau ends where these two strategies intersect. It's only possible because of this peculiar symmetry of the witness. And that one, identifying that in general, is a more general question that I will not talk about here, but it's the natural problem. So it's the symmetry property that makes this thing possible. All right, so that was the essence of my talk. In conclusion, the main point of all this is that small errors or tiny conspiracies can have very big consequences in terms of how they can create false positives in the lab. For example, I would be a bit tempted to try to hack a QKD protocol using imprecisions that are far below the resolution of the experimentalists, especially since high-dimensional QKD is getting increasingly popular, and errors there are increasingly large, and resolving them is a way harder. How you can make generally imprecision robust tests? Well, for steering, I at least can give a partial answer to that. For entanglement, I can only give you nice special cases, but there's no generic method. That would be very nice to have. And finally, this imprecision plateau, I think we are still trying to understand how this thing is possible, how far you can push the thing. But it feels very much like this sort of free lunch statement should have some nice consequences. It's food for thought. So thank you for your attention.
Thanks a lot, Armin, for this very nice talk. And now we have time for questions. Nicolas.
Yeah, thank you. I think what you add is really seriously important, very important. And I'd like just to elaborate. First of all, I have under my eyes a paper called Imperfect Measurements, and it ends with Entanglement Witness. And since most of the co-authors of that one are very good friends of you, you should at least know about that one. I'm going to send it to you. The other point, more important, here you take into account some noise model, but there is one thing that you still assume, namely that you know the dimension, or that the dimension is fixed. You always have this D. There is no reason to believe in D, because all the qubits, whether it is now an atom, an ion, a superconducting qubits, or time-bin qubits that we use in optics, these are all good approximation of qubits, but they're not really qubits. So the D is never really fixed. And for that reason, one should also look at that. And so with Jean-Daniel Banquial, we developed 10, 15 years ago something called device-independent entanglement witnesses, which is cheaper than tomography. And then we did an experiment together with Rainer Blatt, the ions in Innsbruck. And at that time, Rainer was claiming that he could entangle, I think, 20 qubits. I don't remember exactly. But if you analyze that with the device-independent way, you could not get more than 5 qubit entanglement. So a huge difference. And imagine now you want to do a quantum computation, go to your qubits and tell them to behave like qubits instead of going into this higher dimension. They just don't obey you. So actually all this enormous propaganda that they can entangle, blah, 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 is bullshit. It's not exactly the way I would phrase it in front of Rainer Blatt. But nevertheless, this is, you have to be very, very careful. And I think what you are doing here, including also this approximation in dimension, is something that people, you and others, we all should really address way more seriously. Our device-independent stuff is mostly completely ignored by the experimentalists because they would never get so good results. But these results are the only serious ones. I'll let you comment on that.
Let's see if I remember all of it. I'm aware of the paper you mentioned.
I wanted to send it to you.
I know it. It's all right. It's actually the one that started this business. The difference is that there they are focused on multipartite entanglement and try to make explicit false positives. So that's the thing that got us into this from the beginning, to try to sort of correct the errors. About the dimension, it's true. We do assume the dimension, and we also know how to get rid of it. But there is a problem which we don't know how to do, and that's this. Why we choose this metric in the first place, assume the dimension. So I chose this because it has a clean operational meaning. Like, at least you can imagine a way of measuring it without doing tomography. That's why I have this and not your favorite Schatten P norm. So what you could do is that, or what you can't do is to say, well, assume that you don't know the dimension, because then this becomes meaningless. I could, if I have an infinite dimensional space, I put my whole measurement, in the other part where you have no support on your target, and then I can take epsilon huge and do everything still. So that's a problem. You could do is to go away from this attempt at an operational picture and put some abstract object that works well mathematically. Then you could do it. But I want to have both, and I don't know how to make a nice physical quantifier without dropping the operational part.
How can you claim that this is operational if you assume a dimension?
Of course, there is always flaws in the thing. There is also the infinite regression, right, that you pointed out from the beginning. It's flawed, but it is measurable. It's different in the same sense that tomography is operational. You can measure the thing, but it's flawed. But if I put, I don't know, the one norm here, then you cannot measure it directly. That's the difference. That is an attempt on an operational meaning.
Can you go to the slide where you present this plateau? Do you think you can have like very long, like for example, if you go for a scenario, you're choosing a scenario like Alice and Bob, they have like three, and the other one you're 3, 5, 4, and the other one, this elegant. If you have like, I don't know, for the untrusted part, do you think you can have like your plateau basically as long as you want?
So our goal, of course, was to make the longest plateau possible.
Yes.
But we realized that this is not enough. So if you just say, I want to have a long plateau, well, then you just take CHSH, and it's device independence, of course. Your plateau is 1 by definition. Yes. So I think the thing we decided to look at was, what you want is to both have a large gap between steerability and non-locality and have a plateau at the same time. So we are looking at the ratio, the length of the plateau to the advantage in the visibility, for example. This thing, we don't know how large you can make it. It would be very nice to know that. We have some other examples of plateaus. For example, the smallest one possible, which is not trivial in non-locality, is a 3 by 3 measurement. So 3 in, 3 in, 2 out on both sides. But it's not longer than this. Sorry, it is longer, but it's less noise robust. So there is a trade-off in these quantities. I think identifying the longest plateau to noise ratio advantage is the natural question. We don't know how to solve it.
Other questions? Then I may have a very brief one of my own to somehow understand this setting where you mentioned that, given some error epsilon in your measurement device, you can't really certify that some state is entangled. So is it correct to somehow think of this that, say, I have a measurement device with an epsilon error to measure these observables, and you can now send me a state which is actually not entangled, but given my measurement imprecision, I would conclude it's entangled, or I would conclude I do not know.
Exactly. So this is that.
Exactly.
So you're hacking the thing by recognizing that your assumptions are idealized. You could imagine to try to make one where you have an inconclusive output. We haven't done that. I don't think it exists. But maybe that's possible. I think the more viable way would be to just try to include the epsilon explicitly in the analysis.
So if I were to know of my epsilon error, then I would, of course, say I have the epsilon corresponding to this blue line, then I would simply not classify anything that's below as
exactly. So it would, this whole thing would just shift down to 0, which is a product.
Thank you.
If you don't have an active attacker, then this would, of course, probably not happen, right? So have you ever actually tried to sort of put some random sample over random deviations and see how likely it is to get close to this worst case scenario?
So yes, it's indeed very correct that the picture you have here is the tiny conspiracy, right? Everything can align in the worst possible way in the tiny ball around your measurement. So the option is to put some sort of distribution. But the problem then is that if you put a distribution, you have to know what is the distribution. And you typically don't know this. So since we are physicists, you would probably want to put the Gaussian because it's nice and easy. But if you do that, the whole thing turns out to be equivalent to white noise. And then you're just assuming something very pedestrian and probably incorrect. So I don't know how to do it in a nice way.
Then I would say if there are no more questions, we thank Armin once again.
So just before we finish, two things. One, a simple one. We have anticipated lunch today, so as soon as you are at lunch, we can start. It's 12:15, because people want to take the train at 1:30. And second, and most importantly, well, thank you to everyone for making this workshop that enjoyable. I think it was very nice, both from just a personal point of view and from a scientific point of view. So thank you really very much to each and every one. Thank you. Thank you very much.
I think I get the prize for asking the most questions in the workshop. I think it falls to me to also give a vote of thanks to Nicola for supporting the workshop, for organisers, and yeah, I think everyone agreed this has been one of the most fantastic workshops in this setting, with this food, with the hospitality and the talks, the discussions.
Later.
The glacier.
The glacier. Wow.
We brought the glacier directly in the.
Anyway, so yeah, I think we need another round of applause.
I will send it to you and a few people out there. I will send you my